Okay, folks. Where's my microphone? You can't hear me. Well, actually, I'll probably just shout. We'll use that.
I think you need that for the last thing anyway.
Well, it sort of should sort of work. Remember to close it?
I think it's probably.
Oh, it's something here. Oh, no, batteries! It's at the battery now.
Don't let go.
Yeah, organised. Nice system.
So you want to post it on IoA? Is it live stream stuff?
We isn't, but somebody wants to get on the standard channel and throw in any comments. So the question is, does it work? Where's that ending? Don't want doing anything. Oh, yeah. So we have sound. Okay. Is that okay? Yeah, that's a bit better. For those who don't know, I'm Steve Randall. This is Daniel Soul. And we're running the conference this year and last year. So, welcome to the 2016 UCAS conference. We run these every year, and this year we're in Cambridge and giving it a try. Nice cheap location, very much thanks to Andy Batty for sorting that out. Always got oscillation going.
Turn it down a bit.
Yeah. Where? Any idea, Andy? It's just a bit too much, isn't it? Oh, it's on here, isn't it? Yeah. Okay. Any better? Or probably a bit too much? 1, 2? Yeah. Okay. So, yeah, domestics. Today is very much a self-catering event. And by that I mean you do the catering yourselves. There's a big pile of stuff in the kitchen, so there's coffee, tea, fruit juices, actual squashes, seed, sugar, milk, a lot. So shouldn't be short of food. There's also some biscuits, which I know people like. Lunchtime, Subway delivering, and it's just some small subs with some cookies as well. So it should be okay. I've got some fruit for lunchtime and just some Coke and stuff, so we'll be fine. Nobody's going to go hungry today, let's put it that way. From what I can see, a huge amount of carrying stuff here today. Okay, so any other domestics? Where are the loos and the fire escapes? Loos out there somewhere. There you go. So you can tell us a bit informal. Right, let's have a look at the agenda. So we can kick off with Dave Aikman in a minute. Got another presentations through the day. What we will do at the end, hopefully, is launch a balloon if the rain allows. That will be from next door at Churchill College. We've got 3 breaks today, so wait for your tea and coffee until a bit later, and lunch around about 1. You want to know anything, Daniel? Okay. So on to the first presentation then. That'll be young Dave. I'm just going to control. to Mac control to. This what I'll just check this because I need to finish editing it up. You can tell I'm organised. Dave.
Microphone, give me the microphone.
Oh, microphone, yeah. There's the microphone.
Yeah, you're going to stand next to me.
Got to stand next to me inside. There you go.
Hi everyone, I'm Dave Aikman, young Dave apparently. This talks about LoRa, which is long range radio. But when we talk about bandwidths on the mailing list, it's lots of radio arguments. Hopefully we'll do that today. What is it? It's a proprietary modulation scheme. It's inexpensive radio receivers. I think they're about £7 on your shop entry. Great. The range, actually, I think is better than RT2i, but it depends on the mode that you use. The design, the technology is owned by Semtech. It's patented. But you can get modules, these cheap ones, by HopeRF. There are other companies as well. Blovio, I think, is one that does the same thing with a serial port on it. And they do versions for 434, 868, and 915. So they're for the various ISM bands around the world. And that's a module, that's a 434, recognised by where they put the components. So compared with RT2i, it is closed. I know some people go, oh, that's not very good. There's a guy that's in Australia working on basically very fast RT2i. And I think it'd be great if people use this to go and do other things which are open, which hopefully in the end will give us the same benefits this gives us. So the emitter side is a little bit more complex. You have to do some talking to the chip to transmit. It's not just the same as wagging a pin on RT2i. But the receive side is basically the same as the transmit. So it's very simple compared to writing an RT2i decoder, which is where I got my paper in for a start. But I can do this stuff. It also means that you only need a simple microcontroller to do the receive. So anything that can do SPI and has got enough memory can do some LoRa things. And I've got a lot of things there which I'll show you as well. And the range is at least as good as RT2i. I think for chasing, actually, I prefer LoRa. LoRa has given me better results in a car. That's a circuit off of one of Anthony's breakout boards for a Pi, I think. So it's a standard SPI device. It's got an SPI bus, MOSI, and MISO, clock, and chip select. And it's got a few DIO pins which can be mapped. I'll show you that in a few slides. We connect DIO 0 and 5, and I'll explain what those are. But there's others as well. So that's straightforward. A reset pin, and unlike the RFM22, you don't really need to reset it. I've no problem, it's been fine. And that's a breakout board for the Pi with 2 modules. On there you can see labelling with the wiring Pi numbers. On the Pi there are physical pin numbers, there's the BCM pin numbers, and there's wiring Pi pin numbers, and they're all different. For better or worse, probably worse, I chose the wiring Pi numbers. But if you configure the gateway or tracker code, those numbers on there are the ones you need to allocate to DAO 0 and DAO 5, otherwise it won't work. Internally, and that's one of the simpler diagrams, but there's the main thing we need to worry about is the stuff on the right. So it has an SPI interface on the right for everything. The configuration, everything goes through SPI. The DIO pins are just status bits which are brought out to pins. So you don't actually need them. You can still poll those on status bytes in the SPI registers. There's a FIFO which is 256 bytes. And when you power the thing on, it's set to, it's got different pointers for incoming bytes and outgoing bytes on the radio. And it's split into 2 lots of 128, but you can do exactly what you want. I'll show that on the next slide. It has an FSK modem as well, so you can play with that if you want. And then bottom right, it shows there's registers. There are some common registers for the chip, and then there's a set of LoRa specific ones, and there's a set of FSK specific ones. Oops, sorry, more music. So that's just showing, and that's an example there where they show you can build up a payload packet to send and not affect the previous received packets or the previously sent packet, and stuff like that. For the most part, I ignore all that and just use the whole 256. Or actually, well, it comes to that. Mostly, I end up sending SSDV, which is 256 byte packets. So those pointers will all be pointed down to 0. The packet length will be 255. So I don't think has anyone got 256 to actually work? No, it only ever seems to 255, 256 doesn't, and then not bother with the others. What it does mean is if you've received a packet which occupies those 256 bytes, you better do something with that data before the next packet comes in, because there's no double buffering, it's just this one buffer. So that's kind of pseudocode-y thing for how to transmit. So starting by just configuring the modem, what frequency it's on and different parameters. I map there's a bit, status register bit, which says a packet's being sent, and I map that to DIO0. Otherwise, you have to keep holding that register to know if it's been sent or not. So it's better to map it to a physical pin, set that on an interrupt, hopefully, and then let that trigger code further down the road. You need to set the pointers and the packet length, as I mentioned, populate the packet buffer, configure the amplifier. There's a PA in there which you need to use, otherwise it won't be very much signal coming out. And switch to TX mode. Once you do that, it starts transmitting. And then if it's tracker, then obviously you want to be getting on with GPS and whatever else you've got. And until that DIO0 pin goes high, which then means the packet's being sent, and then you can build another packet and send that, and you'll be right. Remember to clear the flag at the end. Receiving is almost exactly the same, and it's actually the same DIO0 pin gets mapped to receivers is ready. And this time you can test the CRC. I do find that quite a few packets come through with a valid CRC when they're not actually valid, but I'm not sure why that happens. And that's the mapping. So you can map different status bits in the registers to those physical pins. So on the left, all the DIO0 to 5. I only ever bother with 0 and 5. I don't bother with the other ones. DIO5 is just mapped to mode ready. So sometimes you have to change from, you need to program the chip in standby mode or sleep mode, or either of those can work. But when you change mode, sometimes it takes a millisecond or so to change. DIO5 says the mode has changed. And then top right, you've just got the packet has been received or the packet's been sent. That's it. So I mentioned earlier about the 256 byte packets that we send. That's only part, obviously, of what gets physically transmitted over the radio. So it starts with a preamble. There's a header, which is either present or not, depending. There's a payload of your data, and there's a payload CRC at the end. So you can see there in the middle it says explicit mode only. So explicit mode is where the packet says these are my parameters. So it says what the packet length is and the coding rate, and that goes in that little header. So that means that the receiver doesn't need to be set up for the same packet length or coding rates. It can be set to anything. The header will tell you what to expect, and then it knows how to decode the rest of the packet. Yeah? In implicit mode, both ends have to be exactly the same, otherwise it won't work. And then you can see the different arrows here are showing how these sections affect the total packet size. Semtech have got a calculator on their website you can download, and you can type in what your settings are, and it'll tell you what the packet size is, and current consumption and stuff like that. So those different parameters I mentioned that affect the timing of the packet and your data throughput, and they're also going to affect your link budget. Starting with bandwidth. So I'll come on later about IR2030 and what bandwidths we can use. But obviously the higher the bandwidth, the more data you're going to get through per second. And these are some examples of the bit rates that you get on the right compared with against different spreading factors. Okay, they're all the same. And the coding rates are the same, that's useful. Okay, it shows the bandwidth effects, not the rest of it. So it goes from very slow to, well, that's quick. The spreading factor, the first one, spreading factor 6, is a special case. So it's basically the fastest mode that the chip will run in. And there are other settings you need to set to certain values if you use SO6. Now, when I started with LoRa, I never noticed that line in the manual. And I had a spreading mode 6, but I had other parameters that didn't work with it at all. So my transmitter was transmitting, the receiver just never saw a thing. And after 2 weeks, I noticed this line, fixed it, and bang, it all worked. That was quite frustrating. So spreading factor basically is how many times it transmits to send it information. So the idea is it gets past, if there's any interference, it's got more chance of getting the data through. For the coding rate, it's just the forward error correction is how many times, it goes up to 2 to 1, so it'll send the same, twice, the data that it sends will take up twice the space, or twice the time of the raw data itself. So you get the overheads there. Right, 2030, there was a discussion about this a while back. So my understanding is, or my interpretation is, that the part of IoA 2030 that we all use for continuous data rate, which is the top section there, has a channel spacing of 25 kilohertz, which I think means we need to stick within 25 kilohertz bandwidth. So that's what I do for when I use it continuously. With LoRa, you can just send much shorter packets and send them with large gaps in between and get the duty cycle down. If you get below 10%, then you can use that second line. And then you see there's no channel spacing specification. So then as far as I'm aware, you can use the whole bandwidth of that band. You probably don't want to, but you could use more than the 25 kilohertz. And that means the packet's then smaller, so it becomes easy to sit within that 10%. One of the issues with the LoRa modules is, certainly the high power F ones, is if you buy 2 of them, one will be, the calibration between them is not good. So they could be 5 kilohertz away from each other. The LoRa modem will handle, it says, in the spec, 25% of the bandwidth. It can handle that as an error between modules. I think that's optimistic, and it's more like 20. The reality is, if you get 2 modules, you've got a chance that they will not, set to the same frequency, they will not pick each other up because they're about 5 kilohertz or maybe 6 away from each other. Which means if I fly with a 25 kilohertz bandwidth on that top line, some people maybe get no packets at all, and then they just try tuning a few kilohertz up or a few kilohertz down, and bang, it starts working. But we can fix that. And one way to fix it is to use the second line and use a wider bandwidth. Once we go to anything wider than 25 kilohertz bandwidth, that 5-6 kilohertz error between modules is within the range of the modem auto AFC, so it will work. The bottom ones are on 868 kilohertz, so there are 2 areas here. The bottom one here is the one I've used for the high data rate 868 SSDV images. There's a whole 300 kilohertz band. You can use a whole lot of it. So I set the lower modem to 250 kilohertz. It doesn't tail off vertically, so it's probably using all the 300 anyway. There's no data duty cycle limit, but there is a 5 milliwatts limit to power, which is quite low. But actually, it seems to work quite well. What I have found is once it gets out of range, the data just stops. It doesn't tail off. You start getting, you go from 100% packets to 0 very quickly. But it's worthwhile. And the one in between will be useful for an uplink on 868. So if you've seen some of my flights where the missing packets then get filled in by the uplink, you press in, they get centered in. You could go up to 400 milliwatts ERP on that line there for the uplink, which is good because the balloon is seeing a lot more noise than on the ground. Any questions about that one? or anything.
Is the frequency error trimmable?
Well, you can calibrate it. Yeah.
Sorry,
Oh, you mean physically trimmable, or?
I'm thinking that I'm thinking of Anthony in actual fact. If you were to buy from Anthony, then he would.
We could do something like calibrate them and send them out with a label which you type in. You could, at the moment in the gateway program, you just set the frequency you want, and if it's 5 kilohertz high, you just set 5k low. But you could put a line in there which says frequency offset equals. I mean, that
calibration line, that's what we did.
Yeah.
To calibrate itself.
Yeah.
You could replace the crystal, but it's just not worth it.
No.
So you can do it in software.
No. But there's other ways of fixing it. I've got one on the side of it.
So what spreading factor do you use at the moment?
Varies.
Because if it's wide enough, maybe the frequency offset doesn't matter anymore.
Well, spreading factor just that doesn't change that. It's the bandwidth is what affects.
Yeah, but if the bandwidth is really wide, so it doesn't affect the frequency offset so much.
No, if the bandwidth is wide, then it doesn't. No. If the bandwidth is wider than 20 kilohertz, 20.8 kilohertz, then they will be in tune enough for it to work.
Yeah.
But then the OC will pick it up and it's fine. Yeah, exactly.
So, well,
You were saying it was closed.
Yeah.
But there is, I think there was someone on GitHub who's.
I think there are 2 people who've got software decoders.
Yeah, they've made a plugin for new radio, but I haven't looked at it recently. Last time I looked at it, it didn't fully support the forward error correction. So they might have done that now. I'm not sure. Yeah,
I should have mentioned that. That's a good point. But yeah, there are developments, independent developments on software decoders, which would be great. I mean, my feeling is, well, they're cheap, I'll just buy some. But it would be nice if people haven't got them, but everyone has an SDR these days. If you could download some software and pick up these flights without buying anything, then that's good. But the cost, the cost of making the gateway is 30 quid or something for a Pi and a module.
You said you've got an uplink working. What sort of performance were you getting from the uplink? So what kind of
Higher than the downlink,
yeah.
certainly, even though it's a narrow bandwidth and same power as it happened. So yeah, it needs more, because it's picking up too much noise up there for it to work. So I don't have a figure for you, but probably 2/3 of the way before the downlink stops, the uplink will stop, something like that. I bought big rail now. Maybe it'll work better. So opportunities, low-cost receivers. I've got a load of receivers here which I'll show you. Fast SSDV. I think Phil's going to have to put a zoom function on his page soon. Some of these images are quite large. I mentioned the repeating of SSDV packets that get missing. So Phil did an API on his server. I've got a little Python script which asks which packets are missing. That's to be done essentially, obviously, because different receivers will use different packets. And then that passes into the gateway. The gateway, next time it gets a chance, sends a message up to the balloon and says, can you resend those packets? That works quite nicely. Actually, the downlink works so well that the uplink is almost completed, which was a bit disappointing. You could do a cut down. I still don't know how to doing it, but that's an obvious thing for an uplink. You can send short videos. Phil and I had a go at doing an animation a while back, and now we've got Laura and we'll have a go at something a bit bigger. Airborne network. I did a flight you may have seen with 3 balloons chatting away to each other. And automated receivers. So I mentioned their calling mode. One of the ways to get around this bandwidth limit is to have a calling channel which is wider bandwidth, which will work between receivers, and periodically for the payload to say, I am on this frequency at this bandwidth and this spreading factor, coding rate, everything else. And then if everyone just sets their gateway permanently to that frequency and that node, and they pick up a calling message, and then they can set then to the frequencies and other settings specific for that balloon. And then there's a timeout. Obviously, after a while, if you don't receive anything, you want to go back to the calling channel because the balloon may have landed, and in order to pick up another balloon. And that's it in action there, to show on SDR. So the packet on the right is calling mode, and then the receivers then tune into the actual primary channel on the left. I've still not flown it, but it does work. Another option is, I mentioned on the network of balloons. I did a really simple time efficient multiplexing thing. So I had a 20-second cycle, which you can see at the top. I had 3 balloons, so each one was given the cyan or the blue columns there are when the balloon transmitted its own position, and the yellow ones where each balloon retransmitted packets it received from the other balloons. And I hoped that, I was hoping they'd all chat to each other in the air, but the real hope was that when it landed, we'd get the landing position, which exactly worked. On the right there, you see in the lower gateway, you can see all 3 balloons coming up one at a time. It was a really simple thing. There was no trying to figure out which balloon could see which and changing the cycle. I just wanted something really basic that actually worked. Oops, sorry. Right, so some kit. So I've got a few things here you can kind of have a look at afterwards. This is a mess inside of hot melts and wire and different modules. But that's an AVR, a LoRa module, display, a GPS. And that's really useful. That I'm going to talk this afternoon about chasing balloons. If it's a LoRa balloon, I just turn that on, gets a GPS lock, receives the packet and says, there, it's over there, 100 meters. Turn right, turn left. Really, really easy. Too easy. That one, all that is an AVR and a LoRa module, but a FTPI or whichever it is. And it just gives you the software in there just maps the SPI registers to serial commands. And then there's a PC version of the gateway ones with that. So you can take that and chase card on the laptop and receive. Oh yeah, and that's Matt's done a much nicer one than this, but that's the same thing with the Bluetooth in there. So you can link to a tablet or a phone. That's got a battery. That one there. So because you wouldn't want to put an 817 Yaesu up a mast, you have to put it down with a lot of expensive coax in between. But one of these things, which is a gateway with a battery in it, 2 aerial sockets on the bottom with a switch, I can strap that to a mast and send it up with a meter of cable to the aerial. So low loss. It was all 55 that holes in anyway. Oh yeah, that's this I stole from the Lohan project, which I quit. It's not kind of fixed inside yet, but all it is pre-programmed AVR with the LoRa, and I do that. I press the button and it says cut down. Good fun. Oh yeah, and in case the uplinks need a bit more power, that's a lead acid and 7-watt PA. It's got two radios on there, so there's a LoRa for the uplink, and there's a little easy radio modem thing, and I've got another of those plastic boxes for the PC. So the PC, I've got an app which says send cut down, send a message to the radio here, that sends it on there, and the balloon cuts down. The GPS is for timing, so it can send a message at the right time. That thing on the right is just like that, for setting the LoRa parameters and for what the message is. Oh, okay. This is for Ed's challenge. So I don't know if anyone has seen Not a Flight, because I got fed up with people asking me about the flight that wasn't a flight. It's software I've written which does landing prediction and does then servo control to say, I don't want to land here, I want to land over there. So basically trying to aim a parachute, a steerable, paraglider, power. But before I actually get automated software right flying it, I want to do it by hand. So that's just a games controller with an Arduino and a LoRa put in there, a little 868 LoRa. So the idea is I can aim with the two pots on left brake line, right brake line, and both then brake, just so I can steer the thing. But also if it's on a real flight, if it's actually working, it's going to land somewhere and there's a power line or something, I can just steer away. That's the idea with that. I think that's the last one. Oh no, okay, right. It's the best one. So, this one, I've got an identical thing in my chase car, I'll show you that this afternoon. But basically, It's a Pi display, touchscreen display, Pi 3 in there, LoRa, 2-channel LoRa, U-blocks, and a big battery. And the program there is just a Python PyQt4 program with a Star Trek type user interface. So along the left, you've got different functions for different parts of the flight. You can then check the source, and the latest stuff here, you press that and it loads up the LoRa gateway in a window, or brings it to a window, so you can see what's going on. This also links to DLFL Digi, so that thing there is a USB audio adapter, so you can plug a radio in there. And then on the first screen, then you see two LoRa channels on the left, and you can see the RT2Y channel on the right. So, and that's really nice. And it does chase car uploads as well. It does BAT-C if you've got a camera plugged in. So it's kind of all in one. And the one in the showgun, the idea there is to get rid of my car PC and all that rubbish, and just have everything based on the Pi. That's it. Any questions?
What speed parameter have you got there? Is that vertical rate of descent, horizontal?
That's vertical, yeah. Yeah. There's, I mean, I'm still working on this thing. It's not open source yet. It will be a few days when there's another one there which shows the same stuff on the left, and the thing on the right is that kind of compass thing saying, oh, it's over there, that distance.
And with the control of the power cell, I presume you've got natural control, but you don't have any pitch. Or can you control the rate of descent, or have you just got natural control right and left?
You can turn right and left, and if you pull both, then you slow down your forward speed. I mean, it might affect the descent, maybe. I've not physically flown one yet. I've written all of them, everything else, and I've flown. If you've seen it online, I've seen it. It's running an emulated Powerfoil simulation thing, and the simulation is only 5 meters from target, but I know that's not going to happen. but it goes through the motions. Physically, the servos are there, just doing right and left on the desk while it's going through the flight.
Did Lawrence ever play with that stuff?
Sorry?
Did Lawrence did have fun though, didn't he? Did you
Sorry?
play with this stuff at one point?
I did, yes. I gave up on the idea of a parafoil because as you scale down, hard to describe. If you've got a big parafoil, then it's effectively a sort of low-pass filtering of turbulence in the atmosphere.
Right.
So it's quite stable.
Okay.
As you reduce the size of the parafoil, you're picking up more and more turbulence.
Right.
And when I started trying it in sort of slightly turbulent
It got upside
weather,
down.
it just got horrendously tangled. As soon as it flips upside down, the payload falls into the parafoil. Now, it only has to happen once in the flight, and chances are, if it can happen, it will happen. And then your flight's over. And
I need to have a chat with Ed more, because I've got a rough plan of having. Because sometimes the flight lands 2 miles from my house. Well, bringing it 2 miles in shouldn't need very much.
Yeah.
You know, so a regular parachute that kind of inches forward a bit. Should be.
I gave up on the parafoil and worked on the Rogolo wing instead. I got that working really well.
It's got fixed bits, isn't it? So
It has.
it
It doesn't meet Ed's challenge,
No.
but I'm not convinced Ed's challenge is
Achievable.
doable.
Yeah.
Yes.
I'm not convinced you could call it a parachute either. I mean, whereas you might call a parafoil a parachute, or a yellow, probably not.
Yes.
I mean, before Ed puts it up, I bought a piece of a very thin carbon fibre rod, thinking I'll just put that in there and that'll give it some stability. That sounds easy.
Yeah, I tried similar things with a sort of a solid wing with payload cords going below. And anything where there's cords separating the wing from the payload, found it was too unstable in turbulence. If there's any risk of the two tangling in some way, it would happen.
Yeah, because it's not like one of our regular flights where you parachute up here at 15 metres of the line or something. It's they're only this sort of, if you had that,
it's much more vulnerable to turbulence. And I mean, on some of my Rogolo flights, we saw everything just got flipped straight upside down. All kinds of crazy things happened, even though it wasn't obviously turbulent on the ground or at the release altitude.
One of my flights, which
turbulence.
I did Sky Academy thing last year, and we used a fairly short line. I mean, it's 25 metres, but the video it did go.
You get bands where there's different air masses moving at different
Yeah.
speeds, you get bands of turbulence that are very violent, and you'd be very lucky to avoid encountering bands of turbulence during the descent.
Any others?
Sorry,
Any positive ones?
Dave, did you try any channel activity detection or channel busy detector to avoid transmitting when somebody else is transmitting?
Okay. I mean, there are some bands in our 2030 where you have to do that. A lot of 868 mega. You can transmit whenever you want, so long as no one else is transmitting. So you have to be able to stop periodically and listen and then transmit it. And otherwise, you're limited to like 1% or 1% each cycle. But no, I've not tried that. I thought to just do the flight.
I tried some, but it seems to be not working.
Yeah.
Just with static module.
Right. Okay. I thought doing a flight where you just basically just listen and log how much noise there is on each frequency and see how that changes as it comes through. That'll be fun. But no, I've not done that.
A couple of RF ones for you. You mentioned it's
I won't know about that.
LoRa is comparable, if not better, than RTT1.
Yeah, I think so.
Is that comparable system? So disconnecting a decent receiver like an 817?
Yeah, right, okay, good one. I did a chase of an 868 flight, and it was sending images and telemetry on the 868 channel, and just telemetry on the RTT1, which is 300 baud. And then because I put the camera's a pi camera on the outside, and I taped it on a bit, and I hadn't kind of covered it in tape, so the payload line up to the parachute got underneath the camera and just ripped the camera off, deposited it in Shropshire somewhere. So the end result of which is all the way down, all it's doing is black transmission of telemetry, no images. And I was sat in the car, as this thing was about 12 miles away, and I had a good position, there's a hill there where the payload disappeared behind. And every packet on 868 came through, no problem at all. And RT2I is probably about 1 in 3 came through. And that's a comparison between 300 baud RT2I and I think it's about 1700 bits per second effectively on 868, so it's working a lot better.
Is that just the raw module with no LNA up front?
Yeah. Compared with 817 with nothing either. And just and the 868 had a quarter wave and the 434 had a 5.8 that come out.
Have you looked at splitting the transmit and receive?
No, that would be interesting, yeah, because you get another 3 dB or something.
As well as you don't transmit it back to your
yeah, that's what I'm saying. The lower modules, the TX and RX are wired together, but that's not there are separate pins on the modules, so you can separate them. They give you an example, and that's not time.
How quick is the transmit receive changeover on the modules, do you know?
No, because no, I don't know. I've not tried that. For my download, I can get a 5-second slot, and it's bang in the middle of this. So less than a second. So I've got a really wide.
Huge amount of time, isn't it?
Huge amount of time.
I'm
Yeah.
just thinking about electromechanical switching relays rather than trying to do it at solid state.
Well, you could do that and wait a few milliseconds and then change. Yeah.
Yep.
Yeah. I mean, it's up to you in the protocol, but you're leaving enough gap before you change, before you need to listen. Okay.
And Mark took issue when you call this protocol fast written.
Sorry?
Mark took issue when you call this protocol fast written.
Oh, that's fine. I thought you called it something like that.
Technically true, but not correct.
Oh, that's close enough. Cool.
It's all the actually, so you're okay. Okay, we've got thanks, Dave. We've got Professor Milton Bain right now, who's talking about biology on arrival in space. So, got a microphone.
Okay, somewhere.
Somewhere. There is it. Oh, okay, some windows. That's
Okay. Right, do you want to...
Okay, thank you very much for inviting me this meeting. As you can see, I've got the intriguing title. I'm going to try to convince you that life is continually arriving to Earth from space as we speak. And the reason it's interesting to you, I think, is that it's an application, shows the application of a balloon launch and balloon sampling from the stratosphere. So basically, over the last 10, 15 years, we've been sending various balloons to the stratosphere to sample to see if there's microbes up there. Now, I'm not an engineer or a balloon expert. In fact, the previous lecture was foreign language to me. I'm a microbiologist. I work with the biology. So basically, the samples are collected, they're given to me, and I work out what we see and whether this is indicative that we're finding life in space or life coming from space. Very few people believe what we found. A lot of people say we can't say what's wrong with it, but we don't believe it. So you can make your own mind up from this. So what we're trying to do is work out a theory of what we call panspermia. This is the idea that life originated from space. Instead of the general kind of chemical origin, where chemicals are supposed to get together and bump together and we get membranes and life, we're saying that as soon as the early Earth cooled, microbes were continually coming from space, life was continually coming from space, and when it was cool enough, they could reproduce and evolution could set off, and here we are. So that's the kind of standard on panspermia view, the origin of life on Earth from space. And we've kind of put a variation on this we call neo, meaning new panspermia. So this is that life is continuing to come from space. Because when you think about it, if life originally came from space, nothing has happened to the planet. There's not been a... Sorry?
Sorry. So is this separate from microbes coming to Earth in meteorites, for example?
It's a combination of, but I'll talk about where we think they come from at the end, yeah? Okay, so neopanspermia says they're coming as we speak, because nothing's happened. There's not been a kind of cover put on over the Earth by God or anything since the life originated. If they came in originally, they've been coming in now, and if they come in now, they came in originally. Now, the idea, the modern version of panspermia, was worked out by these two great scientists, Fred Hoyle and Chandra Wickramasinghe. And of course, it's a great privilege to be in the Oil Institute. This is where Fred Hoyle worked. In fact, I think he established this institute. And here he is on your left. Famous astronomer, science fiction writer, of course, wrote the famous Black Cloud, which is one of the early science fiction books. And a student at the time, Chandra Wickramasinghe. Now, Fred died. Unfortunately, I never met him. I saw a few lectures, but I never got to speak to him. But I work in collaboration with his one-time student, Chandra Wickramasinghe, who's still very much alive. He's in his 70s. And this is them, I suppose, this is in Sri Lanka, where they used to work in Sri Lanka. Two great minds. And they came up with the modern version of panspermia, the idea that life comes from space. They received a lot of criticism, and the idea continues to receive a lot of criticism. It's not established in the mainstream of science, although it's becoming more kind of acceptable, more even fashionable as time goes by. Now let's start off with the early 2000s work. This is when I got involved with Chandra. And basically, surprisingly, there were no bacteriologists who wanted to work with him. This is so controversial that a lot of people don't want to get involved because it means you lose your grants, it means you lose your so-called reputation. I don't have either, so I can work on this. And I was so excited to get working with this because who wouldn't want to know if life's coming from space? I can't understand these people who are careerists who just want to get the money and get their FRSs. This is so exciting. Anybody, I think, should have jumped on the possibility of working on it. Now, we started off with some Indian workers, so I went to India a lot. We launched the balloons from India. When I say we, I wasn't involved. I just went to watch. These are big 30-meter high balloons, and they carry a very expensive payload. They carry this thing shown here. Now, the actual payload is the silver bit, not the carrier. This is to carry it to the balloon. And these are what we call cryosamplers, and here Chandra 10 years ago is holding one of these cryosamplers. Basically, we send them to 41 kilometers, and the atmosphere there is compressed into these metal tubes. expensive metal tubes, and these come down, and we release them, controlled release, and we wash out the tubes, and we see what we've got at 41 kilometres. Now that's of course very high. I think it's probably around the height a balloon can go. People have used sounding rockets, but they're not as effective as balloons. The Indian scientists were very good at balloon science. They got into it because they realised that NASA was doing rockets, so they wanted to work with balloons. So we set these up, and what did we get? Well, what we do is filter them through these micro-pore filters. These are micron, less than a micron filters, which hold back very small particles. And you can see here the clean ones, and what happens when we put this stuff, gunk in through the from the stratosphere. You can see it's very dirty because this is cosmic dust. This is arrived from the cosmos. And what we want to do is look inside that cosmic dust and see if there's any life, any microbial life, any signs of bacteria in particular. So we take that and we look at a very high power scanning electron microscope. This allows us to look at the surface of this membrane and see what we see. And one of the things we saw was this particle mass. This is a particle mass from 41 kilometers. That's a micron. And you can see it's around about 10 microns. Now that's important, as we'll see later. So if you can keep kind of 10 microns in your mind, you'll understand why it becomes important. Now, if I had have isolated this from a lake or from the soil outside and shown it to you as microbiologists in a microbiology or astrobiology meeting, astrobiology, the study of life in space, then you'd have said, oh, it's a bacterial clump. There's no argument, because when we're talking about coming from the stratosphere, people start to argue. Of course, the idea is that what we're trying to do is go out as far as we can and catch a material that is not coming from Earth. We're hoping that we're going to catch material coming from space. So 41 kilometers is around the height we can get, and this looks like a bacterial clump. And when we stain it with a special stain for DNA, we see that it glows. It is a bacterial clump. There's no argument about it. So bacteria do exist at 41 kilometers. They're up there. Now we published this, and there was no great deal of argument about it, because people assume that this is coming from Earth. These bacteria are Earth organisms, and generally we accept that as the case. Except there is a complication with this 10 micron particle mass, which I'll mention in a minute. See, we published it in the standard journal, so it's peer reviewed. These are the species we isolated. It won't mean much to you, I don't think, but basically these are species which were given new names. So Stratospherikus, for example, tells you where it's come from. Now, for various political reasons, we had to stop working with these balloons in India. Basically, we couldn't find enough money to help pay for them, and this launch cost £500,000 a time with the equipment. So they said, okay, if you can't provide any money, you're going to not get the samples. So for a while I was at a loss. We'd stopped doing the Indian launches to 41 kilometers. We got some fantastic work, but I needed to get back in the stratosphere, and I was biding my time. And then somebody sent me an email saying that, do you realise there are two guys in the University of Sheffield who are sending balloons up for various reasons. Now, I use the term I call biosphere, and I wrote this paper talking about life in the stratosphere. Now, the controversial studies, these are really controversial studies, started around about 2015. And they involved these two people. You may have come across them. At the time, they were students in the engineering physics department at the University of Sheffield. They've recently formed a company, Sent into Space, I think. And at the time they were students. They were making a little bit of money out of this, but now they've got their PhDs and they formed their own company. And amazing that they were in the same university as I work in. And I got them in my office and I told them what I'd like to do. I wasn't very kind of hopeful, but they said, yeah, we're sending balloons. We'll make a sampler and we'll sample using these weather balloons. Now, the sampler we came up with was incredibly straightforward, but incredibly effective. Basically, all it is a CD drawer. The CD drawer is opened in space at the height you want, in the stratosphere, the height you want. Normally with these balloons we go to 27 to 30 kilometers. We can't seem to get as high as 41 kilometers, but we can get to 27 to 30. And basically what you've got here is a CD drawer with these little holes cut out with these tabs. Now these black tabs go straight into the electron microscope. So we don't have to mess about degassing like we do with the tubes, which can introduce contamination. We just take them straight out in a clean room and put them straight under the electron microscope and see what's on the surface. So we're at 30 kilometers, say, we open the drawer, the particles fall on that, drawer closes, it's all GPS I guess, and comes down the balloon, sorry, the box comes down on a parachute and off we go. And we make sure that the box obviously isn't smashed on when it reaches the land. Now all this is done sterilely, take my word for it, there's no contamination at any stage of the process. Here they are messing with the balloon. It's pretty obvious to you what they're doing. And what did we find? Well, as I said, I wasn't too optimistic we'd find anything, but the photographs came in. They are amazingly good electron microscopists as well, because when they were doing their PhD was about looking at the surface of things like ball bearings for wear. And so they're very good at looking at surfaces with the fancy electron microscopes they have down in engineering in Sheffield. We don't have such good microscopes. And the first thing I saw was this amazing beast. Now, this got into the newspapers. The Sun called this the Todger, the little green man from space. It's supposed to be a little green man's penis. It does have a very similar, but I don't think that's what it is. I'm pretty certain that's not it. But it's an amazing thing for a biologist. This is not something you find on Earth. We can find what we call Earth analog. There's nothing like this on Earth. And you can see it has got what looks like a sphincter, what looks like these ears here, and this thing, the Todger bit, with the like nose openings here. And we think this is an organism. We're pretty certain it's an organism. There are two reasons, and I'll mention this later on. First of all, it's got what we call bilateral symmetry. If you cut it down the middle, it's the same on either side, more or less. Presumably, it's got an ear-shaped structure on the other side. Just like we are, if you put a line down us. If this were a crystal or a bit of sand or a bit of silicon dust, cosmic dust, it wouldn't have that, it would be complex. And it obviously has structure. It is lifelike. It is a biological organism. And more importantly, we can put a crosshair on this and we can analyze it by X-ray, and we know it's made up of carbon, oxygen, and a bit of nitrogen. So if it were cosmic dust, it would be silicon, and this is biological. This is an organism, and it's coming down from space. Now the other thing about it is it's about 20 to 30, so we've got some organisms 40 kilometers, 40 microns in size, and they're being captured by our sample. Here's a close-up of the sphincter and the proboscis, I call it, not Todger. You can't get proboscis through the scientific literature. Sorry, you can't get Todger into the scientific literature. But the Sun, of course, put this on their front page. They loved it. One of the problems when you're writing, kind of doing any news on this kind of work, of course, is that it has to be associated with little green men and all that. You can't take it, nobody can take it seriously. We take it very seriously. But the media want to make it into little green men. In fact, when we were doing our sampling, we did it over various places in the UK. We've also sampled in Death Valley. We've also sampled at Bonneville Salt Flats, above Bonneville Salt Flats. But when it's in the UK, every local newspaper says, little green man Todger found over Newcastle, Birmingham, Sheffield, or wherever it lands. They take the credit for it. I hope everybody knows what I mean by a Todger. This is what my artist, and a terrible artist, impression of what I think we've got here. This is an organism with the proboscis lying down. I think these things are probably to propel the organism. These things here, the yellow one on the other side. This is maybe for intake or outtake of food. This may be intake or outtake of food. So this is a very strange beast, and we don't have these on Earth. There's no analogue, as we call it, as I said. We find other things. Now this is interesting because this is definitely a diatom. Now this is confusing because diatoms we know are on Earth, so they should have, maybe this one got up from Earth, but there are various reasons why we think it didn't. It's clearly a diatom, we don't no arguments about that. The trouble with it, it's too big. I'll mention later that by modelling studies we think that nothing bigger than 6 microns can leave Earth to these heights. These modelling studies are very good modelling studies, and this thing is much bigger. It's 20, I think 10, 20 microns. So theoretically, this cannot have come from space. So it must have come in from space to Earth, to the stratosphere. Now, that is a big problem for biologists to believe, because we know this is an Earth organism. So this is a bit of a paradox. But we found other strange things. This is a beautiful photograph of 3 organisms. We have this donut-shaped one, we have this one like a couple of bones, and this one at the side. Again, we know they're biological, they're not bits of dust. They're beautiful things to a biologist. And here's a close-up of that one. You can see it's got kind of a ridge down the middle. This has got symmetry, you put a line through there, it's the same on either side. So the evidence for biology, is that EDX shows that biological entities contain solely carbon, oxygen and traces. They are organic and not cosmic dust, and they have this bilateral symmetry. So that tells us they're pretty certain they're organisms, they're not just bits of fluff. As I said, modelling studies say that 6 microns, only organisms below 6 microns can reach these heights. And many of these things are bigger than 10 to 40. So when our critics say that they come from space, in terms of theory, in terms of modelling studies, they can't come from space to this height. But there's one more kind of intriguing proof that they're coming in from space. And that is, where is the pollen? Where is the grass? Now, if these things were coming up from Earth, they would be associated on our samples with bits of grass, bits of pollen, bits of fungus. The whole Earth, of course, is covered in this biology. Where is it? We've never found a single pollen grain on any of our 10, we've done about 10 flights now, throughout, over the world, let's say we've been to the States. There's no pollen. If this was coming up from Earth, we would expect it to be surrounded by bits of pollen, bits of grass, because there's so much of it.
So there's the pollen. How big is the pollen?
Well, the pollen is from, say, 10 to 40. So it proves that nothing that size can get up there. So basically, this proves that nothing, as the modelling studies show, nothing bigger than 6 microns can get up there. And this is the real crucial evidence that these are coming in from space, because it should be obliterated with pollen and grass, and we should only see these organisms very careful, with careful study. But there they are, they're pristine, they're beautiful. Yep.
How do you know that nothing from the Earth can get higher than 6 kilometers?
6 microns, the size is 6 microns.
Yeah, how do you know it can't get higher?
Well, we do modelling studies on that, the mass versus the energy and so on and so forth.
Well, I think in pollen, the fact you can't find pollen at those altitudes is a fairly good indicator. That's why I was asking the size of the pollen. The pollen's twice the size or 10 times the size, and you wouldn't expect it necessarily to be there.
Yeah, exactly. This demonstrates what we're saying, that it should be, if these organisms came from Earth, where's the pollen?
With the rest of it.
Yeah, everything should be up there, yeah? But these are pristine. So there's no filter on the Earth's, the stratosphere, there's no filter that's keeping grass and pollen out and letting our stuff through. So this is where we kind of, I think, hopefully, shoot down the critics, because they can't answer this question. And if we look at the outside of the box, which we do, of course, we do find pollen and grass. There's some bits of...
Sorry, that's contaminants from launch, though, isn't it?
But
that's contaminants.
Well, this is contamination from launch, not from incoming or anything. So what I'm saying is, surrounding the box, as you're coming down, there's pollen, but not in the stratosphere when you sample. There's nothing on the outside of the box when we sample. Well, we don't know that, but this is coming up and down, yeah. So this is on the outside of the box.
And how do you clean the inside of the box?
Oh, it's all, trust me, it's all done very, very aseptically in clean rooms and everything. But of course, in some ways, the contamination thing is not a problem, because if it was contaminated, it would be contaminated with obvious stuff, like grass and so on. So the fact that there's none of this means it's not contaminated. So it's a kind of a circular test of what we're finding. Now, this is a very strange one. This one blew my mind when I first saw it. This is when we do the EDAX on it, it's made of titanium mainly. And you can see it's a sphere, 30 microns. So this is much bigger than the 6 microns. And when we look at it, now for some reason I asked the guys to move it over, and they used what's called a micro manipulator. Again, they've got some fantastic equipment which can move this ball across when they're looking down the microscope at it. And first of all, we looked at the surface. It was made of carbon, oxygen, and nitrogen. And here we are. This is the micro manipulator down the bottom. And here we are moving the ball across. And you can see this ball has made an impact event. We know from studies that this material here is oozing out of the ball, not from there. But when this thing hit, it was travelling at such a speed, it made an impact event on the sampler. Now, this is very good evidence it's coming in, because it's very unlikely that you could generate enough speed going up against gravity to do this. This ball must be coming in from space, and it's caused an impact event. And when we move it over, and this is biological, this goo is made of carbon and oxygen. And when we look at the surface, here is a close-up of it. So you can see we've kind of, the goo has stuck there, and when you move the ball across, it comes out of the sphere. When we look at the surface, we find that it's made up of filamentous material, very much like what we'd expect biological material to be. You can see that it's not a very good photo, but it seems to be like a knitted material, a little bit like when your granny, I don't know if your granny ever did this, I'm showing my age, used to take pullovers and pull the wool out. You can see the kind of wool, the filament is being pulled out from this network. And this is a picture under the very high magnification, so it's not too clear, but you can see it's bifid, it's like a tree twig, and this again indicates it's biological. So this thing, 30 micron ball, has got biology on the outside, it's got biology on the inside, and it's coming in from stratosphere, it's coming in from space is what we say. Now, if you look on the internet on our work, there's been a lot of criticism, mainly from trolls, people who don't really know what they're talking about, as is usually the case these days, and they're commenting on where we publish the paper. One of the problems with publishing this kind of stuff is the standard mainstream papers won't take it, the journals won't take it. So you have to go to less mainstream journals, and then people say, well, why isn't it published in Nature? Well, it's not published in Nature because Nature won't take it, whether it's good, bad, or indifferent. And but I just put this in to demonstrate that one referee, who happens to be one of the world's experts on environmental microbiology, thinks very highly of our work. So it's not badly replicated, the publications are okay and everything, but we have had a lot of misinformed comment. And one of the problems is the scientific community won't engage with this. Now clearly NASA, these launches and the equipment cost about £3,000–4,000 quid. NASA can do this tomorrow, and they may be doing it tomorrow or before to corroborate our work, I don't know. But we've not had any information from any other space agency that they're doing this. I don't understand this, it's very cheap, it's very easy, and they could be demonstrating the same kind of work and telling us where we're going wrong. I would love to know where we're going wrong, because as I hope I've shown you, I think it's pretty QED that what we're finding is right. Now, the question about where we think they come from. We think they come from comets, and we think the material is coming in small particles of ice. It starts off from comets in big particles of ice, and as this comes towards the Earth, it ablates, it gets smaller and smaller. So in fact, when it gets to the sampler, it's an incredibly small piece of ice containing the organism. And when the ice hits the surface of the sampler, that's when we get the impact event. So the impact event is not caused by the organism, it's not heavy enough, it's not going to be enough mass, but the impact event is caused by the bit of ice. So when it impacts, it releases the organism, and then you don't see any ice. So we think comets roam around the cosmos, spewing out life, and this is the idea of cometary panspermia. Now, what are the implications? Well, the implications are pretty obvious. Life has always come in from space and continues to do so. Now, a more intriguing and important, well, more important, but equally important, is that these particles, these living organisms, biological entities, will have brought information from space. Biological information, DNA. And this DNA could have interacted with organisms throughout time and added to evolution. So instead of thinking of evolution as an Earth-based phenomenon, what we're saying is we're getting information from space. We're getting new DNA coming, and this interacts with organisms already here and provides new information for evolution. So, when you go out there in the rain, carry an umbrella because you're completely covered with organisms from space. Now, a lot of people have said to me, oh my God, are we going to die? Is the Earth, is this the end? Well, some of these may be pathogens, who knows, but obviously the majority of these organisms, if we're right, have been coming in from space forever. They're as much a part of biology of this Earth as you are, nothing to be feared, and they are bringing us new information if we're right. Now, even I kind of balk at the thought that we are right. I mean, I've had about 1,000 baths about this. It's more than a 1,000 bath problem. I think about it all the time, of course, and I'm trying to find some kind of, where we're going wrong here. I can't as yet, nobody else can tell me. I give meetings like this to space meetings and in front of the United Nations Space Conference and so on. And everybody's kind of fidgeting and I don't know. And they don't talk to me afterwards, they go somewhere else. But they can never tell me where we're going wrong. Perhaps somebody here can tell me where we're going wrong.
Well, following on from that, for purposes of elimination, have you checked if there are any industrial processes on Earth, for example, which use titanium microspheres or produce these as a byproduct?
Yeah. Well, you have the same problem. They're so big, how would they get here unless they're rejected by some kind of really powerful force? I mean, some people have come up with the idea, and I've had to answer this, that maybe this is what we call directed panspermia. This gets really spooky into UFOs. Maybe this is life that's been sent by a civilization from outer space. And this is a very serious idea that people kind of do follow. So maybe this is material that's been sent by intelligence to Earth to see the universe. I don't know, I'm not saying that's the case, but it's an interesting possibility. But no, I don't think that they're from an industrial. You mean the titanium ball, I guess?
Yes.
But even if it were, that wouldn't get rid of the other ones. But that may be an anomaly, but I don't think so. Yeah.
And when do you think you'll be able to check any DNA from the stuff that you found?
Yeah. We've been trying, obviously, and it's more difficult than you can imagine because we're talking about very small things. And we're hoping to get, again, I mean, it sounds like I'm kind of asking for special pleading here, but you cannot believe how the scientific community won't engage with this. We had an organisation at Cambridge here ready to go to do what we call an isotope fractionation. Basically, if we fractionate isotopes, we should have a different ratio from a space organism compared to an Earth organism. So we had this all set up, getting really excited. 2 weeks before, it was cancelled because the head of the institute said, we don't want to get involved in this. Too controversial. You can't believe it. Too controversial. It will interfere with our grants. It will interfere with our status as a great university department. And unfortunately, this is what happens in science. This idea that science is all open and wonderful, you soon find out. When you go out of the paradigm, you soon find that these are problems that arise. Yeah.
I think people are slightly naive to think that life came from Earth in the first place.
Yeah, that's what my wife thinks. She said.
It's a bit of an insular view that the whole life is.
Yeah, this is what my wife said. She said, I don't know what the fuss is about. Obvious, isn't it? I said, well, that's nice.
It's very naive. It's a bit like the old days where we thought this was
the
universe.
Yeah, we call it pre-Copernican biology. You've got to remember that biologists in the past have been kind of stuck to the idea of Earth. They've had this idea. I always had this kind of a comparison with what's the place in Cornwall called with the dome? The Eden Centre. They thought of it like the Eden Centre, like there's some greenhouse. But now, of course, we know that there's ingoings and outgoings. Maybe an asteroid killed the dinosaurs, for example. So we are open to the cosmos, obviously. This is so obvious now. But you can imagine 20 years ago, people didn't just have this in their mindset. They thought that the biology was just Earth limited. But of course it's not. They must be coming in. Yeah.
Have you considered doing a height profile?
Yeah, we've tried that, and we've got some indication that. But remember, this is like fishing. We don't always get them whenever. It's not like going out into a pond and or various ponds. It's just a statistical event. What you get is what you get. So we might do an height profile, and then we get nothing somewhere, but it doesn't necessarily mean anything because it's purely random. What we
presumably from your simulations, you'd expect the earthbound particles to go to a certain height.
Well, we know that. Yeah, we know that happens.
You'd show.
Yeah.
a
Yeah,
reduction.
we like that, but I mean, we obviously know that happens because that's got to happen. I mean, I've been even thinking maybe we could go to the Arctic and get a layer of snow, massive layer of snow, a couple of kilometres square, and melt it down and put it through our filters, and we should see these. I'll answer your question in a minute. One sec. By the way, I did get a worrying moment when this student from the States emailed me and said, if this is true, the whole of the moon should be covered in these organisms, and we know that it is not. And I panicked for a second, oh shit. Why didn't I think of that? But of course there is an answer. The moon has no gravity. Sorry, the moon has no atmosphere. This, in fact, is the only place in the whole cosmos that we know about with an atmosphere that can slow these things down. Anywhere else on the space station, anywhere else in the cosmos with no atmosphere, they would just smash into the surface and be smashed to smithereens. It's only because they're slowed down by the atmosphere that we can catch them. And that's a wonderful thought, that humans are the only people who can actually study these, because we live in a world with an atmosphere.
There's a lot of dust on the moon, isn't it? Very fine dust and stuff like that.
Pardon?
There's a lot of dust on the moon.
Oh, we get cosmic dust on these all the time, by the way, yeah. It is surrounded by cosmic dust, which make impact events. So, I mean, something like 40 tons a year of cosmic dust fall onto the Earth or something, I don't remember the number. But yeah, we get covered in cosmic dust. We can find cosmic dust in the Antarctic very easily. There's no problem with that. Yeah? Sorry?
A point and then a question, I guess. My point was that if these things are coming from space,
Yeah.
The chances of them being living when they get down to Earth, or
Yeah.
having viable DNA in terms of all
Yeah.
the, coming into the atmosphere and the heat and all
Yeah.
the stresses on it, I think.
Yeah.
So
Yeah.
there's a difference, I guess, between things arriving and things viable
Yeah,
arriving.
yeah. Yeah, good question. Obviously, we thought about it. What I mentioned before is they're not naked. They're not coming in as individual organisms. They're covered in a snowball, an ice wall, and this protects them. This is certainly sufficient to protect them from radiation and UV light. You know, UV light is very toxic. UVC, there's tons of it in the stratosphere. But you put a shirt on and you're on the beach, and you protect yourself from UVC. Same with radiation. Being a small organism, cosmic radiation is not a major problem to them. So yeah, they could become inviable. They could be dead, but their DNA is viable. So maybe they never actually breathe, yeah, but they pass on their DNA to other organisms. Or maybe some are viable and live and so on. One of the intriguing facts, we've recently realised that the DNA in the soil outside, in the lakes and the sea, 99% of it we cannot associate with Earth organisms. Only about 1 or 0.1% can we give that DNA to that organism. So this is why we think all the rest of the DNA is from space. And it may not be doing anything, but it's here on the surface.
Isn't that just a case of there aren't DNA samples for a large number of organisms, so you can't match it? There's no large database of DNA sequences.
The database is increasingly massive, and you would have thought that, I mean, most people
do statistics on estimated number of species, size of the DNA.
Yeah, but most people are surprised by that fact. Okay, so most biologists think it would be lost less than 99%, 99.9%. When we find that,
Where can they say that it'd be less than 99% from the actual figures for
I guess,
the database?
Yeah, okay, the database gets bigger every year and so on and so forth.
What's the size at the moment?
Well, I don't know exactly, but believe me, that is not an expected result.
Right.
So the people who do this are surprised when they find that.
Right.
Okay?
Clearly, the best place to sample stuff is in space, though, isn't it? The best place for you to sample stuff is in space, like with those aerogel things where they can actually...
Yeah, aerogel, we've thought about it. In fact, the Japanese are working with aerogel.
So those people must be doing that stuff. If you're sending these CD trays up and bringing up interesting particles back that potentially look like life, surely this is...
Well,
far better being done in space where you're not even worried
Exactly. That's obviously, if we could get a balloon up to 50 kilometres on... Yeah, but one of the problems is, of course, if you use sounding rockets, then the rocket's moving at speed anyway, so you're going to get a combined impact.
Yeah. So forget all that, and sometimes that'll work in your advantage anyway, because you'll be moving with the particles.
Yeah, I mean, you can do it, but we can't. You know, we're not, and NASA could do it dead easily. NASA could do it.
That would open and close this argument.
Yeah, it would, obviously, but we can only work with what we've got, we're working with. And I think this is intriguing enough to send NASA. You'd think that they would they'd get off their arse and do something, wouldn't it?
What's it cost for a kilo in space? What's it cost to get a kilo in space?
Well, you don't even, yeah, exactly. I mean, they're spending literally billions going to comets. I mean, I think they must have done it. They cannot possibly. I mean,
It's a very straightforward experiment, isn't it?
it's so straightforward, it's ridiculous. You know.
The main issue everyone is going to have is there's no repeatability. Because I mean, I know you say things like bilateral symmetry is a sign of life, but you can have something that is abiotic that has unless you keep getting the same shape.
Yeah, we have seen evidence of the same shape, but again, when you say reproducibility, we've done 10 launches. Some of them we don't get them. We've got about, I think, only one where we didn't get them, which is very interesting because it shows the fact that you don't get them every time. Because you might be going through a cloud of these things and you're going to catch them or you're not going to catch them. Reproducibility in this kind of thing is almost impossible to say. All you can keep on doing is getting more and more, and hopefully, like you say, bump into another one. But I mean, I always think maybe I'm 67 now, another 20 years, maybe with a little touch wood, they may show a compendium of thousands of these things that have been found. You know, we're at the beginning. We've found these, and I have absolutely no doubt that they're organisms. You can tell me they're coming from Earth and I might believe you, but I don't think this is cosmic dust, because when you see cosmic dust, it's so obviously dead. It has no volume to it. You know, it's flat and dead. These things don't have that. As a microbiologist for 40 years, it's like you can see what life looks like, you know. But anyway, we may be wrong.
You said you get what you get, and you know often you don't. I guess what you really need is an awful lot more samples.
We need a lot of people around the world doing this. Yeah. Or if NASA won't do it, or the European Space Agency won't do it. Let me just give you an example of what we're up against. First of all,
in actual fact, NASA, in some of what they do, they use amateur radio operators and similar.
Well, in my news releases, I've said, can the boffins, guys like you, but you have to have an electron microscope, of course. That's the
no, you need only the collectors. And
okay. But if universities around the world, with people of interest like you, got together and did this, then we could get millions from around the world. Remember, we've got samples from, as I said, the Bonneville Salt Flats and from what do you call it, Death Valley. So it's not an English phenomenon. We know that, not just over Sheffield. So yeah, I mean, come and join us if you can link up with the university guy. I'd love it. I mean, why NASA doing it now? Just to give you an example. Again, I'm not paranoid about this, but my postgraduate who worked in this went to a meeting, European Space Agency meeting, and the head of the European Space Agency took him aside and said, "If you want a career in science, you've got to drop this. This is no good for your future." And I was I mean, this is not made up, it's a real fact. I was just obviously gobsmacked by this. I thought, what the hell is going on? And that's what's going on anyway. I gotta catch a taxi. Sorry, I can't stay for more. I'm not running away because I'm scared of the questions, but I gotta get a flight to New York, right? Okay. Sorry?
One final question.
Yes.
What sort of size and mass are we talking about for your CD tray?
It's just a standard CD tray.
What's the cost?
Well, it's taken from an old computer.
No. What's for somebody who's going to launch it? What would be the cost?
The whole thing is about 3,000 quid for a launch.
It's quite expensive. So if it
no, that's for a launch. That includes the helium and me paying the guys
for the device.
Oh, I don't know what a CD tray costs, and you guys can.
It's sterilised and all the rest of it.
Yeah, well, that's relatively nothing. Yeah.
But if it ended up in the Yoggin, what's the loss?
Oh no problem. Just get another CD drawer.
Aren't you looking in the wrong place? You really shouldn't be looking in the atmosphere. You should be looking in space. That's my only thing.
Yeah, I agree with you, but yeah, give me the money and give me the rocket. Sorry? What?
It's not expensive, that stuff.
Is it?
Not really, realistically.
Yeah. Well, nobody's offering to launch.
I'm just wondering if there's data already available that might prove your point. For example, we're talking about isotope ratios.
Yeah.
Maybe there are already samples
available
that have been collected.
Yeah.
That, although biological material might have been destroyed on impact because it wasn't collected in the right
well,
way.
I think theoretically, the whole of the Arctic would contain these organisms.
Well,
but
I mean,
who's going to do the ratios?
Things like stardust emission, for example. where they collected samples of dust.
Yeah.
Maybe you could get access to some of their samples, even if you weren't
Now, we've looked at the samples, obviously, and they're actually on the internet, you can have a look at them. But one of the problems with that, when you talk about aerogel, is aerogel will destroy organisms this big.
Yeah.
It's only made for very small organisms.
But maybe there's other ways you could analyse the data from Stardust that would show, for example,
Maybe,
the
yeah,
acetate
maybe we
mix.
can. Anyway, I've got to fly. Oh, that's your bag. Yeah, taking this guy out for something interesting. Swap bags, you know, it's the usual CIA trick.
No, I was totally it was quite convincing. It was fairly
Okay. That was really interesting. I'm on next, so it says. So it must be Yes, sir. I don't know. Do you know?
I'm partly responsible, unfortunately. Chris Rose, who's in my physics class at school, and he lives just down the street. And he kind of got the idea of getting him viewing from me. So I unfortunately claim responsibility.
I never asked the question as why is it not just washing off the top of the balloon? So I better not say. Right, okay. Operation Outward. Does anybody know what this is about? So show of hands. Do you know what
I googled it.
You googled it. Yeah. Anybody else? Okay, twos and threes. Okay, well, okay. This is going to be interesting, I think. Then. I became interested in that. Why is it not shown? Wretched thing. He's supposed to be showing me some
Catch up.
I'll try and do this by memory now. So this is something I became interested in about a year ago as a result of a discussion on trailing wire HF antennas from balloons and whether that was a good idea or not, or whether it was a problem. But what transpired then is that, well, as we'll see from this, that that sort of trailing wire idea had been done before. So what Operation Outward is it was the launch of almost 100,000 meteorological balloons by the British as a weapon during the Second World War. The balloons carried devices which were weapons. Well, the thing that knocked my socks off was that they were launched about 500 yards from my house, and I never knew about it. They were literally from
You're not that old, are you?
Sorry, I'm not that old. I don't remember that. No. But they were launched from just down the road from our house, and on Felixstowe Gulf, of course, the majority of them were.
You would have expected your parents to have known something about it.
They live in London, so we moved to Felixstowe 20 odd years ago, but I'd still not heard of it, so it was strange. But I mean, I did know about the Japanese fire balloons. I don't know if everybody else knows about those, but they were launched by the Japanese as a weapon onto the US during the Second World War. They were very clever balloons in that they had to, I think, a 2 or 3 day journey in the jet stream to get across. They weren't particularly effective. Sorry?
I believe they killed a cow.
Yeah, I think it was about that. Killed the cow and scared a few people. These were a lot more effective, and they caused lots of damage in Germany and other places. The original idea was that this was an idea proposed in 1937 that they would use RDF principles. They would launch balloons, they would track their position as they scooted across, and they would then drop things from the balloons that were the weapons using a radio signal. And that was the original idea in 1937, and they were proposing to launch those from France into Germany during that period. But that never took off, and obviously we sort of retreated from Germany and from the continent in sort of 1940. But later in that year, some barrage balloons that were, I think, around London had broken loose from their moorings and taken their line with them. And they ended up in Scandinavia, and they did a lot of damage up there, just shorting out power lines and things. So I think it got the ear of Churchill, and he said, let's have a look at that idea and see if we can weaponise something. So that's when 1942 Operation Outward was born, and the idea was to use standard meteorological balloons, tie some weapons to them, send them out across the channel and into cross France into Germany, and cause some damage and start to use up resources. Get firefighters doing that job rather than being able to be part of the war effort. So that was the original idea. So this is a picture taken the second day of operations. This is actually Felixstowe. There's a place called Landguard Fort there. So that's the fort. There's an observation post there, and there's some other bits and pieces over here. Some houses that are not there now, but that's the second day of operation. They were launching the balloons. At their peak, they were launching, I think, one balloon every 10 seconds for about 3 hours. 1,800 balloons in 3 hours. So you can imagine the sort of, the rate of filling and stuff going on. I mean, anybody who's launched a balloon knows how long it takes to be getting off at that rate.
There's gas cylinders in the background.
Yeah, these are gas cylinders. So there's hydrogen. They were using lots of hydrogen. So there's rows and rows and rows of cars. Or I think there must be trailers, lorries carrying hydrogen, and they must have been filling balloons and sort of tying them and doing stuff.
There's barriers, do you think, between them? I'm just wondering, maybe that's some kind of safety feature.
Yeah, I think these might be like shielding or probably for filling. So they're probably some form of.
I'm wondering if they're sort of fireproof or blast-proof shields.
Well, we'll come on to that. They talked about 3-sided tents for filling them, and they did have some problems with that.
Hydrogen?
We'll get on to that at the end.
The hydrogen filled?
The hydrogen filled balloon, no helium really in those days, but in that sort of quantity. There was a lot of argy-bargy going on between the RAF and the Navy. This was run as a naval operation from, they call this place HMS Beehive in Felixstowe. They were using, probably not shown here because this was the second day, but during the rest of it, the majority of the operations personnel were wrens. They weren't men, they were women. And even the women were operating overhead guns and stuff to protect the area. So it really quite interesting. I was actually completely blown over by the numbers that were being talked about. 100. I mean, just the concept of launching 100,000 balloons, albeit over 2 or 3 years, is amazing. But One thing before we leave this slide, one thing to notice is these little lumps on top of the balloons. That they are important. We'll come on to, you know, technology there. I mean, I was mostly interested in the technology. How did these work? How did the guys of the day solve the technological problem of sending a balloon across the channel, across France, into Germany, and get it to do something in the appropriate place, and, you know, cause some damage out there. So I've really been sort of looking at this from a technological angle. I went down to the National Archive and read through the file they've got there on Operation Outward. And it doesn't give a lot of technical detail in there. It's more about the day-to-day operations, the stuff, the negotiations that were going on between the RAF and the Navy and Operation Outward. Because these were seen as a bit of a hazard to outgoing planes from the UK, you know, dropping bombs onto Germany.
I guess this was all pre-NOTAM.
Yeah, they were carrying stuff that was a bit of a danger, and there was another operation called Operation Albino, which was like a floating minefield in the sky. That never really took off very much, but I think the Navy had it, sorry, the RAF had it in their head about that, and were worried that this was in fact the same thing. Therefore, you know, they were worried that this was going to be, you know, mines hitting their in the sky. Anyway, let's move on. So this is probably the best description I could find so far of what the Operation Outward balloons were like. This was taken from a civil defence pamphlet in Germany, so they found some of these and sort of like backwardly engineered what was going on. The key things to notice are this cooled inside the balloon, right? But, I mean, some people probably are familiar with this idea, but this is the first time I've heard of it being used. So what it is a cord across the inside of the balloon and a valve here. Let's just move on to the next slide because we're all described. So there's a spring-loaded valve there, and what happens is the balloon gets bigger and bigger and bigger as it goes up, and eventually it opens the valve and the balloon stops ascending. So it's a sort of like a float device. The other part of it that was key is these little canisters here, these sorts of ones with the funny sort of shaped top. What they had is a fuse inside them, which was set on launch, and that fuse used to burn for several hours and then eventually would do something. So the sort of things it would do is it was open a canister and drop out some bottles of, well, these were phosphorus, some sort of phosphorus bombs, rather nasty stuff really. I think again this is like a phosphorus bomb but much bigger. So that, again this canister here would have sort of like flipped over at the end of 5 hours and dropped out. And there was some stuff that this was more or less napalm from what I can tell. So they used to name these things, give them interesting names. Jelly, obviously for the napalm, and beer, because of the bottles I imagine. I think that one might have been called lemon, but I haven't worked out why. These were socks, and they were filled with wood pulp and dipped in sort of wax. And set off, I think, as they dropped. I'll show you another picture in a tick, but they were intended to get tangled up in trees, and that's the same, you know, device here that does that. This device also came into use in the other type of balloon that they were using here for an offensive attack, which was the trailer wire. So we'll see a bit more about that in a minute. But they just really configured these for duration. This was presumably configured for height. And there was also an oil reservoir, I think probably used with the wire ones on their own, where what happened is that would drip out oil after the end of this 5-hour period, and that was intended as a height stabilisation device to keep the balloon at a constant height. So here's some other pictures from National Archive, etc. These are the phosphorus. These are beer. that's jelly, and that's socks. And that was intended to open up as it fell and catch on tree branches. So
what would that achieve?
well, they wanted to do forest fires. So they
right.
wanted to start forest fires. So the key targets for the incendiary devices were forest fires and crops. So they wanted to destroy food crops and start some forest fires and tie resources up in fighting those fires. So that was the key part really of what we're aiming at. So this gives you an idea about these canisters and how these controlling canisters and how big they were. And this lady here is setting, it's actually sort of like lighting the fuse. And I imagine they lit it in a particular place to get the duration that they needed. As I say, about 5 hours it was crossing the country. So this is what I can sort of work out a typical wire flight might be as a sort of like a flight profile. Standard sort of ascent as we know of it, and then this valve in the balloon taking over and controlling its height. Now, from what I can gather, it doesn't really level off completely into a nice sort of vertical flight. I think it presumably starts to sort of leak. So I think probably because the valve operates and then it probably releases too much gas, it starts to descend, but only at a slow rate to begin with, and then eventually, after it's sort of done its crossing of the channel and
you got this up, or is this from the figures?
No, this is from the figures I've got from the documentation, and I've sort of guessed this bit from what was being said, but it's I can't find anything of this sort of level of detail in any of the documentation that exists anywhere.
What sort of length was the wire?
We'll come into that in a tick, but you'll see how that worked in a bit more detail. But yeah, they went up, they floated across, they came down, they deployed the wire on about here somewhere on the latter phase of the descent, and they then just sort of hovered. We'll see that in a minute for the wire works. I mean, otherwise they would be dropping one of the incendiary devices here and not worrying about constant sort of height.
I'm interested to see that last little bit at the end.
Okay, we come on to that. 5 hours, obviously 500 miles from Felixstowe to a bit of Germany. They reckon the accuracy was around about 100 miles, so very inaccurate as a sort of device. But really, all they were aiming for is like forest areas or next to Berlin. I think it's worth saying that on the second or I think it was third day of operations, actually believed that they started a fire next to Berlin, and from that it caused the Germans to start to send up planes to try and knock them out of the sky. So it tied up aerial resources as well as ground resources. So good from that point as a weapon anyway. So this is how the wire ones work. They were trailing about 300 foot of wire, fairly large gauge wire, steel wire, on the end of a long piece of string. So the equipment would have been up here that we've just seen, and obviously there's the balloon. What they required was at least 10 mile per hour winds at 1,000 feet to drag the balloon along with trailing the wire. And you can see sort of how it would work as it trailed along. It would be taken over power lines, shorting the phase-to-phase wires, and actually sort of like literally drawing out an arc as well. We can imagine this wire drawing over it. So pretty effective. The German electrical distribution network at the time was very poorly protected against phase-to-phase shorts. And some of the analysis that they did was that they were worried about Germans using this as a weapon back for us. But firstly, they thought our electricity network was better protected than the Germans. And secondly, there's obviously a prevailing wind that is west to east. So the chances of them doing it is very much lower. So that's really one of the reasons they started doing it, because they felt that the Germans wouldn't be able to do the same thing back. Say 300 foot of wire, the average sort of power line might be 150 foot, big ones. So plenty of wire sort of dragging over the power lines. I reckon that these would do damage for about 30 miles. So not just a single power line. Any power lines along the track would be shorted out one after the other.
Are there no trees in Germany?
Yeah, there are trees, but they expect them to sort of like drag through the trees.
Yeah, you run across the tops of them, wouldn't
Because it just sort of like
Exactly, neatly bring it lower.
Yeah, so the height stabilisation device was intended to sort of like balance off any hydrogen loss during this period. And so these sort of like come down, deploy the wires. The wire was looped inside a big can, which was on the outside of the other can with the sort of like controlling device in it, and then it would drop back down at this predetermined time, and all the wire would drop out along with the string. And as I say, really the idea was to sort of like sit at about 1,000 feet, dragging with plenty of air movement at 1,000 feet.
Why the complexity of keeping it tied up at first? I don't see why.
I think it may be a worry about planes catching our planes on the outward trip. So this was sort of like a thing that was deployed at the end.
It adds a lot of complexity, doesn't it?
Yes, it does. Yeah, but don't forget they needed the time bit anyway for the pyrotechnic.
So it's a dual effect balloon then. Pyrotechnics first.
Yeah, I mean literally it was the same mechanisms but being used for both weapons.
Your first multi-role combat balloon.
Indeed.
Multi-role combat balloons.
Yeah.
MRCBs.
And is that weight drag on the ground that actually holds a balloon at a certain altitude?
Yes, that's part of it as well. They arrange for what they call like 1 to 2 pounds of negative lift. So you've got about 1 or 2 pounds of weight supported there. So that's dragging along the ground bit, and then it sort of like levels itself off, along with dropping this iron out at the appropriate time, dripping it out. So yeah, pretty darn clever really, given the limitations of the time. Actually did quite a bit of damage. So this is a little summary. 99,142. Very precise about the number of each type of weapon. There's a breakdown even of the incendiary types, and right down to the one. Majority really incendiaries, but very close second is the steel wires for power line damage. The overall cost of the project is £220,000 in 1940 money, obviously. Each balloon cost £1.75 in today's money, or 35 shillings in those times. The 1.1 million damage is just one event where, because they shorted out a power line, the power line then knocked back to the nearest power station. The power station's protection equipment failed, and the whole power station was burnt down as a result. So so the 1.1 million is just that. The rest of it must have done millions and millions of pounds worth of damage, but they just couldn't put a figure to it. There was no records. They did some analysis at the end of the war. You can find that in the National Archive, but it really wasn't. There wasn't a lot of information that they could go on to work out exactly how much damage it had done. But at least it certainly paid for itself. It was at least a factor.
How much damage was done to the UK in the process, though?
There was some damage done to the UK. Yeah. Unfortunately, some of the balloons blew. They were very good at weather modelling, and some of the balloons blew back in there.
Those cheap ones probably popped as soon as they took off.
It's probably worth saying that working with hydrogen, you're launching 100,000 balloons, you might have the odd event, spark. So they had several events where the balloons caught fire, and that was as a result, they thought, of the balloon being taken out of the tent and rubbing along the top of the tent,
static,
causing static.
Angel suntan's coming.
Which is where the instant suntan comes.
But this is good because we talked about doing this a while back, and obviously we were worried about what the security was. But if no one died doing this with a few 100,000 launches, the chances are we're not going to kill us.
Nobody died. No, that's right. I don't think this is a die event, but you must be badly burned. There were a lot of other accidents with phosphorus. Somebody dropped an entire table of phosphorus bombs. And I think they were badly burned as a result. But they had things like huge tubs of water for people to jump in if you know, had an accident.
Could you imagine that number of servicemen at that time that nobody smoked?
Well, this was about 300 personnel to run this,
yeah. So there's going to be a couple, isn't there?
You know, well over half, I imagine, were rest. So yeah, you're right. I'm sure most of them smoked like that. They had these accidents with phosphorus.
There's some videos on YouTube of people setting fire to hydrogen-filled balloons, which is quite informative. And although there is a sort of instant suntan effect from the burning off hydrogen, that's quite rapid. But what tends to happen is there's fragments of burning latex get thrown out, which look far more dangerous than the hydrogen metal would be, because they're sticky and very hot. If you get hit by one of those, it's not going to be nice.
Yeah, so most of the heat will just go upwards with sort of fire dripping down bits of burning latex.
That's the thing to watch out for, I'd say, is the burning bits of latex. That's really going to give you a nasty burn.
Yeah.
But we're not really the hydrogen.
This beekeeping. It does look like beekeeping. These are actually, this is the full protective outfit that they wore when filling and launching them. And that is there's a mica sort of view thing there, and there's some mesh, I think it was copper mesh, so they were aware of static and stuff. So you know, they were set up for it, but as I say, even then they had. But you'd think with 100,000 you're going to get the odd accident. So any other questions on this? It was just a complete surprise to me. This is what the same place looks like today. There's the same observation post. This actually appears on that photograph, but it's been clipped off by the particular version I've got. So you can see that, and this would have been where the fault is. The lorries would have been situated along here, and the photo would probably have been taken more over here. So this area exists today. Next year is 75 years since the first flight. Well, so I've been in contact with the landowner, which is Suffolk County Council, with the idea of doing a commemorative launch, and I'd like to try and recreate that photograph that we So we just need some volunteers to come and launch some balloons. Just bring your own payload and tie it to the balloon.
You told the Germans what to do.
Obviously, I'm not sure where the balloons will end up. We're not really aiming, I don't think. We're just trying to recreate the launch event. There's a really good description of one of them in some of the documentation about the wrens thought they looked like pearls going into the sky. And if you're launching, I think something like 8 or 9 balloons at a time. You can imagine.
It's because of your blue business.
I'm happy to sponsor the balloons for this. Okay. I'm trying to get gas from Unibok or Air Products or something. So obviously we probably won't be using hydrogen because it's likely to be a public event. So.
Steve, you mentioned that valve for regulating the height. Somebody on the IRC channel in the last week or so put a link to I think she was an American scientist.
Yes.
Gone to South Africa. They were using a ping pong ball.
Yeah.
Suspended from the top.
Yeah.
Down, I guess, in the
Joe, I can't remember his name, has done it.
Yeah.
And also Bill Brown's done one. And the idea was taken on by a lady that James knows.
I didn't know. I read about her.
You read about it,
I
didn't
didn't
you?
know her.
Jean,
Died
something like
about
that.
That's the people last week on IRC?
Yeah.
You're like, oh, look.
Yeah. So it was used as a technique afterwards. And it must give you some form of height control. But I think when Joe did it, had exactly the same problem where it came down as although he said it went way before he thought, in terms of leveling off. But I can't really explain that.
Especially on balloons, though, you could get balloons with the top would have a little knot which you can tie into.
The idea that Bill came up with was to use magnets. And I think that's quite a good idea if you use some neodymium magnets that are really quite strong, put one on the outside or even just a bit of plate of metal on the outside, put the magnet on the inside, tie the string to it, bring it down to a valve in the neck. I think the balloons had these diagonal chords in them. And I'm pretty sure that must have been for a reason. I imagine it's possible that the balloon doesn't expand as reliably in that direction as it does in that direction. I don't know, but that would be a guess. It would be something to try.
The way they form the balloon as well, perhaps, when they make
Maybe,
it.
yeah.
Also, the payload would vary, would drag the shape of the balloon.
Yes, it would tend to make it does tend. But as the balloons spill out, they tend to get closer and closer to spherical.
Yeah, you would get acceleration events in that direction, so it wouldn't be as reliable as the.
Possibly, yeah. Thank you. Well, So yeah, that's the plan. If you're interested in coming and launching some stuff on a free balloon, then come to me, or catch me offline. I'm going to try and make some large windbreaks. I've got one that I feel because I think it's pretty windy there. As you can see, it's very open. They moved from here to Felixstowe Golf Club. So this is the first. In the first few months were done here. And they moved down the road to Felixstowe Golf Club, I presume because it was a bit bigger. I think the site is a little bit limited in space. There were lots and lots of houses here. You can still see the foundations. You go and walk around there. And this whole area is just like a nature reserve, or it's get dog walkers in it, so they can't be that concerned about the birds. But there's lots of birds and rabbits and things that run out of you.
When you get a removals company involved, they can swing one of the big vans on.
You just fit it from that and use it as the windshield. Could do. Maybe that would be a good idea.
Do you have a date yet?
I'd ideally like to do it in March of next year, which is when they first started. But they've said to me that it's a bird nesting season or something, and so it's not likely to be then. Plus, I just don't think you're likely to be able to do it on the exact day because of wind. You just don't know what the winds are going to be. So I'm not really aiming to get it on the exact anniversary, but I'd probably do it more towards the summer, to be honest. It's much nicer.
How many balloons are you planning on launching?
At least 9 or 10. So good. A simultaneous launch of 9 or 10, just to give that effect of
pearls in the air.
Yeah. So that's my idea. If you're interested, catch me some other time. What I have done is this is actually I'll just talk about this. This is Operation Albino, which I mentioned earlier. You can see they were using the same balloons for this, or going to use the same balloons. And this is the floating minefield in the sky. And the idea was that there's a device up here with the thing goes bang in it, a parachute dangling down here. A German aircraft came wandering along and caught on the line. That forced the thing to detach from this item underneath the balloon with a little drogue parachute. And because the drogue parachute's got less drag than the big parachute, it gets the thing that goes bang gets dragged towards the plane, and then when it hits the plane, it goes off. That, to me, it seems like a brilliant idea, but they never ever did it. As far as not in. I think they tested the idea out 2 or 3 times and then gave up. So to me, it seems like a good idea. What I think does happen is if it doesn't hit anything after a period of time, it just releases and the whole lot just parachutes to the ground. I think it disarms itself. This is really what the RAF were most worried about, and I think this is what they confused with Operation Outward, and they had this in their minds because there's an awful lot of let's say banter went on between Navy. You can imagine the Navy and the RAF are not going to be completely aligned. Anyway, so that was Operation Albino, and that looked like a really good idea to me, but never did it. So I snuck this in on the agenda. Does anybody know what this is likely to be about? You don't. Okay. Okay, just one then. So the law has changed. The air navigation order, which is the piece of law that governs aircraft flights or flying in the UK. A new one came out on the 25th of August, and it doesn't include a section on balloons anymore, and that is because they've adopted SARA, which is European directive, which is actually very, very similar to the ICAO rules that we all probably know, but those rules categorise balloons into one of three types: small, medium, and large, basically, light, medium, and heavy, and apply different rules to it. But it won't really affect us, particularly if you keep below 2 kilos and your line isn't particularly thick. But if you're going to apply these rules, then you must. We'll have to look at this regulation in a bit more detail and see exactly what it means to us. But it doesn't look like a big change. But I haven't really been able to assess it in any great depth. I just found out about it a couple of days ago, so I thought I'd stick it in on the agenda. Heavy balloons, definitely. They in the ICA rules they talk about carrying an ADS-B transponder, and so that's anything over. Well, it's actually anything over 2 kilos that don't conform to the area density rules, which are sort of really quite complex. The rules tied together, so anything over 2 kilos could fall into the category.
Yeah, you don't need an ADS-B transceiver, only a Mode S.
A beacon.
Only a beacon, not GPS enabled.
Okay. But that really is for larger flights. But I mean, if you keep below 2, you shouldn't haven't had that worry. But you know, it's just something to bear in mind. Things have now got a little bit more complicated in the UK than they used to be in the UK. We didn't seem to have to worry.
What was the document number again?
It's CAP 393, which is the standard one for the air navigation order. But you can look that up online. But as I say, it's been changed to really just reference out to this SARA document, which is.
And it is valid only in UK or all the European?
I believe SARA's been implemented in all of Europe, or being implemented in Europe. But I think in terms of Germany, for example, it's already the same. I think Germany.
For 1 or 2 years.
Yeah. So there you go. And it's worth us knowing that things have changed. Really. That's my worry.
I think I'd look at this a while back, and I think one of the rules is if you've got a flight going between countries, you have to get approval for each country.
You do, I think that's always been the case, to be honest, Dave. But what it says is that if it's categorised as anything other than light and not used for meteorological purposes, then you've got to do that. If you're using it for meteorological purposes,
of course,
and we all laugh. If you're using it for meteorological purposes and it's light, then you don't need that.
Sure, we're all meteorological, aren't we?
Well, yeah, depends, I guess, on what you're doing. So, you know, that's a concern, but I think we'll just look at that, and you know, it won't really affect very much other than the larger flights. Yeah.
No complaints,
No complaints so far. Right, it's tea time. Excuse me. So, teas and coffees are out there. Be back in about 20 minutes or something like that. As I say, it's all self-service, so you have to do it yourself. Oh, honey, I'll do that at lunchtime. I forgot about
Where do you get your t-shirts done?
Online. I can't remember the name of the company now, but there was somebody sent out an email and said this is a really I want to try them. They want to keep it. Yes.
Unfortunately, 2 days notice.
Yeah, it's all working. So what's actually happened there is instead of having a tea break, had lunch. Basically, the food turned up early and everybody couldn't just sit around with it sitting there. So we're now going to break the afternoon up, perhaps with a couple of tea break sessions, but we're going to keep the same order for the rest of the presentations. So next up is Dave again.
Okay.
Do you want to turn as well?
Oh, blue thanks.
Think
Same Dave Aikman as this morning.
Slightly older now.
Yeah, slightly older now. Yeah. So this is about recovery. It's the bit that everyone forgets. I certainly did with my first one. So it's easy to forget about. You spend months writing the code to your tracker. You find out how to fill a balloon and the type of parachutes on, all that stuff. And then you let it go, and you telemetry's coming in, it's moved on an app, and pictures coming in maybe, and you get so excited and then think, oh, I've got to trace it now. So this is really to get people to think about it before then, and some of you have done some launches, and the more you do, the more you find that every single flight is a different chase afterwards. So some of this is just recollections of chases I've done. It's always fun. Sometimes it's easy, sometimes it's much more fun and it's challenging. This is the only bit my wife comes out on. She loves the fact that you don't know really where this is going to land. You can meet interesting people, sometimes angry. So you need a plan you should have a good idea where the balloon's going. So you should have a good idea where you need to, if it's going to be 10 miles down the road, you can wait at the wrong site. If it's going to be 100, you need to get going. But you need a plan of where you're going to go to chase. You need equipment, you need radio receivers, obviously. We'll go on, talk later about all the other bits and pieces you might need. You need preparation, charging mobile phones, there's loads of stuff. So my first flight, none of this happened. I did forget about chasing. I saw this balloon moving along. I saw people in Ireland and Holland and other countries like Yorkshire picking it up. And I was just so impressed that eventually I thought, I need to go and chase this thing, and by which time it's too late. So I didn't notice that the balloon was coming down a lot quicker than I planned, because the parachute got tied up. We went out to where I thought it was going to land, it landed somewhere else. The last position, this was before we had a really wide tracking network, was at 4,000 metres, which is pushing the expectations of how good the predictor is to fight to get within the last mile and pick up the signal. And the tracker bug, which was actually had two, you may remember, but the thing was bouncing back and forth as it went meridians, so that made life fun. Struggled to get online because I needed to go online because other people online were fixing the position for me, and I really hadn't got a clue where this thing was. So it all went well, apart from and then what happened was we had an idea where it might be, and we drove along, and there was just mush on the radio. Then all of a sudden there was a second burst of RTTY. Stopped the car, got the yard out, got the position, dropped. Planning. So if it's a fair distance away, you need to get to the general area, which may mean a fair bit of driving. But the main thing after that is get the last final position, because that gives you the best chance of finding out where the landing position is, which is the next step. Once you've got that, then you need to find the payload, physically find it. Sometimes it's not as easy as having GPS coordinates. When you go there, you can't see it. We'll do some of those later on. And actually physically getting there could be challenging as well. And then we cover the payload and then have a drink. And not do these in the opposite order as one or two people have done. So a bit of chasing. So I've come to the conclusion these bendy mag mount aerials are not very good. When you're driving along the wind's blade, you can hear the effects of the wind on the signal. So if Darkside is watching on the live feed, I've decided 1/4 waves are much better. And you can make one just by cutting things like this. You need stuff to receive it. I have an 817 in the dash. I take a laptop. Matt's all-in-one Android app is brilliant, so I use that a lot. For Laura, just run a Pi. That thing there. Enough to get online. So I found the 3G, 4G dongles are getting better and better. The one I've got now from EE gets a much better signal on its own, just sat on the dash, than the earlier ones I did with a 3G aerial on the roof. So those are improving. But if this is just one flight, you don't want to buy anything, just use your phone. But charge it up, and have a car charger, and a spare battery. Because by the time you've got 3G and Wi-Fi and everything running, and GPS on your phone, it'll last 4 hours. And online or offline mapping. So if you're online, it's great because you've got Google Earth and you can OSM mapping and everything else. But if you haven't, there's no 3G where you are. You either have to drive off and find some, or you need offline mapping. So it's really good to have offline.
Good offline mapping tool?
Come to that, but Backcountry Navigator Pro I use on Android.
Well, it's a paper map you're coming to.
Sorry, on a paper map. Oh, I've had a flight where nothing electrical was working. Or we had no phone signal. The sat nav said, I don't know where I am. And we ended up with a paper map to translate the thing. But everything in the thing will file sooner or later in the car for long chases, especially. I'm not a fan of using a mains inverter, but you can get 12 volt power adapters for laptops, and most things these days are USB, but laptops you can get 20 quid, you can get an adapter. And if you've got 2 of them, take them, because things fail, all sorts of stuff goes wrong. So that was my wife's car a long while ago, and that's a basic thing. If you're doing a one-off flight, you can do this. That's just a netbook. On a, it came with it's a thing for attaching to the dash, and the box explained what you could be doing while you were driving.
Anyway, I cannot see your steering wheel.
No, I can reverse the picture for you if you want.
Thanks.
Then there's a tablet there with a knob holder of some sort. So that's my seat type. That's my show done a little while ago. It's the Anthony's neon and everything. So a lot of what I do is geared to me chasing on my own, because sometimes I do flights and my wife's not around, so I do it in the week, and I try to be independent. But most people, I think, you have someone else, in which case the driver just drives, and the other guys can do the navigation and receiving and everything else. The thing That one there is a 150 quid touchscreen for a car PC. So in this case, the car PC is a mini ITX motherboard, 12-volt power supply in a boot next to an acid battery. I'm trying to replace all of that by this LoRa thing, Pi thing, which can do ICTY as well. So I don't have the PC. There's loads of ways you could mix and match it. So that's why I have it then. And that's what I've got now. So that's in my 24x4. And that's the same as that box I showed this morning. And a nice piece of Perspex, basically stuck with magnets on the dash. And that's the whole thing. And that was a picture we saw on one of the chases of a firing range. But at least we knew some trick. So knew some information. Chase down. So once you've launched it, see what the SO mate's like. If it's not what you were thinking, rerun the prediction. So at least you've got a prediction now. But you may get updated prediction data depending on the timing. So now you've got a better idea where it's going to land. Once you've done that, go to the general area, find a McDonald's or something with Wi-Fi if there's no 3G around, and just wait in the general area. And I usually go for a crossroads between two major roads, so whatever happens, you can go different directions. But this kind of thing, it's very difficult to plan. I can give general information, but you need to look at where the balloon's going to go and where the roads are, and try and make a decision about being in the best place, regardless of what happens. This balloons won't burst early or all sorts. So after burst, the prediction should settle down, and then your point then is not to go and see the thing and maybe cut it, which everyone seems to want to do, but to get the last position. So being nearby on the top of a hill may be a lot better than trying to be exactly where it's going. And also the exact way it's going will move around a few miles. And it's really, really easy, I've done it a few times, to go down all sorts of narrow lanes to, right, it's going to land here, just in front of me, and then the prediction goes over there. And that 3 miles now takes you 15 minutes to get to, and it's landed by the time you get there. So it's much better to just go for an area with a good view on a hill, maybe. Yeah, do not commit. Yeah, and find a hill with internet. So if you get online and see everyone else's data, not just yours, and then you can see snapping and everything else. And get that last final position, because the lower that is, the more accurate your landing position is, and the more chance you've got of finding the landing position later on. So you want to get that. You may need to find a hill. For example, in a minute, I didn't know the landing position from the road, because there was no part of the road network in the UK that had a signal. So yeah, you may need to find a hill and climb to the top, which when I had bronchitis at the time was quite hard work anyway. And you write it down, just in case the kit goes. I had one chase, and the 817 radio, the battery dropped halfway through a sentence. Now the battery on the laptop could have dropped halfway through a sentence, and we've lost it. So write it down as soon as you get it, in case when it goes pear-shaped. And also, is it still moving? So I've read one chase where we wrote the position down, and then I read it back to my wife, said it's this, and she said, no, it's changed. Oh, okay. It kept moving. You'll see why in a minute. SSDB, I had one where I wrote down the position wrong, and went with the farmer to this particular place, and it wasn't there. And then we went back to the car, and I showed him the SSDB originally, and he said, oh, I know what that is, and he stopped it. So that's the hill. The road at the top is the closest one. You can see by the contour lines, there's no way of getting a position of the balloon, which was down here, from anywhere up there. So I climbed up this bit, and as soon as I got to the ridge, the signals are strong then, like it was right next to you. That's the one that moved. And that's why it moved. They picked it up and took it around. It was actually during a competition. And as far as they were concerned, this was just in the way, so they picked it up and took it down. So fortunately, it was an amateur competition, but we got to the clubhouse, found who was in charge, and he said, yeah, you can go on there, but try not to get hit by a ball. And then we were instantly spotted as not wearing golf gear. And the people with this came over and said, yeah, we've got it. Good. Well, there's a really, really easy way of getting the landing position, and that's to do what I did last year and fly 3 balloons, or 2 balloons at the same time. So you use the second balloon to get the position of the landing. So I can imagine if you've got an expensive payload, you really, really, really need to find it. You could send a cheap balloon afterwards, and then get that to receive via LoRa, or whatever you want, the landing position, and then relay it down. So the curves here, the red one is the first balloon landing, the green one is the second. So the yellow is the direct signal that Phil Crump received from that balloon, so it dropped out just there. And then the blue ones were all the repeated packets we received from the second balloon. Here, all of these ones between here and here are ones after it landed. So we have the landing position on the screen. So you can see up here we have like 10 or 12 people receiving a landed balloon. So once you've found out where it is, recovery plans, trying to find the easiest route from the road network, which may not be get as close as you can. Maybe there's a public path that goes from somewhere, and you can walk along that rather than travelling across someone's farmland. Is there a nearby house? 2 reasons. One is they may know who owns the land, or they may know own the land. The other is if there isn't a nearby house, maybe just sneak on the picture and get it anyway. Is there public right of way, which is good to get you really close. Tap the location into the direction of finding out. There's one I use called hand GPS, which will just say 100 metres that away. The compass on it's a bit dodgy, so it'll tell you 100 metres, but you go that way and then it's 101 because it's that way. But it's basically keep walking till the number comes down to 0 and then it's in front of you-ish. Hopefully there are better apps, but that one seems okay. If you get OS maps, because sometimes the direct route from road to the payload is not the one you want, because there might be a ditch in the way. Maybe there's somewhere else you can go. So if you can get OSM mapping, that's a lot better. Obviously Google Earth as well. Or go on IRC, because what you can see on a small screen in a car with the sunlight on you is a lot less than everyone else can see with multiple big screens at home, cup of tea and everything, and can go online and say, oh yes, there's a better route here. On the other hand, some of the, I always have a look at the IRC logs after my clients, and some of the suggestions are, why is Dave going around the field when it's just there? Well, Dave's looking for a bit without my blind in the way. That's what interesting. But it's not always obvious, and Google Earth doesn't always show you what you find in real time. As we found here, so this is one of several of Anthony's flights, and the information I got from IRC was, so basically the balloon had landed, we got position, it was a long way from where we were, we couldn't see a short balloon. And Anthony said, well, it's 50 quid worth of electronics, I'm going home, so I got off home. I went online, and then the IRC message said, no Dave, it's only 100 metres from the A34, there's a lay-by, and the rain, which was bouncing this high off the ground, is going to stop in 10 minutes, because they looked at the radar. None of these things was true. Well, the 100 metres was close, but we waited, I think, about 45 minutes waiting for this rain, and it got from there down to about there.
So the question is, does your wife use DAS?
So all I can see on the imagery, because by then we had internet and everything, so I can see on the imagery, okay, there's bushes there, and the other side there's a field, except there's a field of maize, 5.5, 6 feet high. So I had to go through that with this hand GPS thing, walking along, till eventually it said 0 metres, I went, can't see it, and then I walked into the line. It was that close. It's the only way I saw it. And it's really easy when in the summer when there's props, even a full prop, and the payload will disappear into it. So usually a parachute's the first thing you see. So, yeah, off-road equipment, jeans are quite a good one. Packer Max and things maybe to keep dry. I've lost count of the number of times I've gone out chasing with shorts on, and the next day feeling all over my legs because I got stung. A phone and a basic direction finding app, or that handheld LoRa you see that I had earlier. Ordnance survey mapping if you've got it, and a radio and a small Yagi. Because sometimes, if you're working from one GPS position, it could be 10 metres out quite easily. So you could go to a garden, with one of the Sky Academy ones, we went to a garden thinking it was in the garden, but we had 1 point, but actually it was in next door's garden. And the way we found it was by aiming at the Yagi tool, we've got a null. Where, oh, that's away. You can then move a few meters, do the same thing, triangulate it, and it's next to a skull and in there well. So it's always worth taking a small, you don't want a big Yagi to be casting across the field, but small one's good. Ah, yes. Or even a boat, as happened, or snow boots. So now we're getting on to more of Anthony's flights. So this is one of mine. This was for Arden a few weeks ago. That's my recovery hook. These are about a quid in B&Q or something. So that tied to the end of a mast is a marvellous tool. That will, if you can reach the thing, that should put it down. It'll take as much as you can pull. Basically, it doesn't come off. So that's us trying to snag the payload line and pull the thing down. If you can't snag it, if there's no way of pulling it, if you pull and it's not coming out, it's really stuck in the tree, just put a blade in there and try again, just cut the line and let it drop. I mean, you're going to leave the parachute behind, but at least you've got the payload back. This was an interesting one. Flight number 3 or 4 that we ran out of gas when we filled the balloon, so it landed half a mile out. But it came in on the tide and the wind was handy. So we had quite a while to wait, and the IRC came to rescue again and recommended we wait there. We did. And then later on, here you are. Turned up. There were 2 trackers. That one died actually, it got wet, and seawater just kills it. But so the other one's still working. This is one of Anthony's. That's a lovely shot. So the parachute over there. Is that your payload or is that from your?
That was Josh's.
Okay.
Mine. What do you think about the camera?
Yeah. So yours was the camera on.
Yes.
Okay. So that photo was grabbed after. It'd be great to do an SSDV, by the way, with a repeated balloon of this. And that's where Steve was the recovery vehicle. So that's, I don't have one of those, but everything else. And then the final, and I noticed when I was putting these together that all of Anthony's really interesting recoveries, he was nowhere near. He just goes home. So this one landed 1,800 metres up a hill. When I say hill, I mean that sort of hill. These guys went out with snow boots and spikes and nails and everything, which is why we did the logo, but the icon. Anyway, Superman going up the hill. So we watched all that, and that's Anthony's payload back. And that's it. Any questions? No, good stuff.
What's on next then? John Underwood.
Hey, what's your least favourite recovery?
Least? Oh. Well, all the ones I didn't get back. So landing 10 miles out to sea, that wasn't good. I don't know. I think if you get it back, it's fine. But yeah, I don't think I've released actually.
My balloon landed at RAF Lakenheath, which was good.
Yeah, I did farming range. I didn't do Lakenheath. Is that what you did? Actually, the farming range was the best one.
They're right. Yeah, it was fine in the end.
There's actually a video on the website of the gate being wrecked to get out.
No, that's Dave's one. On my story.
The fire range one was balloon burst too early. So the picture was nowhere near the reality. So it landed near Thetford, and at the moment I heard my passenger say Thetford Forest. Oh no, where that's going.
Yes.
And, but yeah, it was outside the active part of the range, but it landed. We got there backwards past 4 after they finished firing, so they left on.
Steve and I pulled a tree down once to get a shot, which we drove across the firing range about the same one. And the guy, the army colonel, offered to get one of his helicopters to try and blow it down. This is after he got pretty upset with us. So they're quite used to it now.
Yeah. Well, the Thetford team, we turned up and there's this guy, and he looked like Robert De Niro now, and he was just saying nothing. And he said, why are you here? And we explained, You're from Cambridge. Yeah. And all the other guys were Barclay Pike from Cambridge. They all go, say yes. I'm going, no, say no. And then they said, you've done this before, haven't you? You opened up, and that was it. It was fine after that. Apart from, he said, I'll leave the gates unlocked. And he'd go where you like, on my offer, go where you like. Great, sort of old 4x4, go where you like, got thing. Went back and he'd lock the gate. So that's when we had to phone around and we got the security guy that came along. And I thought, oh, he's going to have a key. And no, he had a hammer. So I rushed back to the car because the car was pointing to the gate. Turned the dash cam on sharpish, so get the
We didn't cut you down, we cut down. We cut down.
We cut halfway through it, didn't we?
We cut way halfway through it and we dragged it down.
Tied a big line on top of the tree and tied that to the back of my Land Rover. And it just it didn't need much.
I mean, we did get investigated by it. And that's why they didn't mind, because they now realise they didn't realise that the Met Office were launching within like 10 miles of them. And their worry was about the fact that balloons were passing through their airspace. And we were like, you know, the Met Office launches every day from New York to Mars. And they were like, no, we didn't even realise it. So we helped them out, really.
And there was one where I was trying to figure out where the thing was. And the farmer, the landowner, found me first and said, what are you doing on my land? That took a while to calm down. But just as we were, it looked like regular public land, road. There was a cul-de-sac, there was a sign up there saying fire.
Carry what was watching the car?
No, actually we carried a 14-year-old, that worked. It was a school thing, and once he saw the kid, once he got me to apologise, and then he saw the kid, he just relatively was fine. Because we started a school thing. See, proof. And then it was fine. But yeah, it's always good to find them before they run you.
You didn't have that in your list of things to take with you?
No, I really did.
Or maybe add a pair of bolt cutters?
Yeah.
For cutting padlocks off?
Well, the thing is they had our phone number, so I didn't want to do that.
We got the mic, radio mic.
I've got the radio mic.
Yeah, can we try and get the volume up on that slightly, because people on the internet are saying they can't hear it via that stream, so I've suggested there's a second stream, by the way, 2 streams running at the same time here. One is off the internal system, so it's got a much better picture of the slides, and the other one is the camera at the back there with Darren behind it, which is like focusing on people as they talk. So that camera or that stream, the audio goes a bit low, so you can get your microphone up a bit closer to you.
Okay.
Hopefully pick that up a bit better. Oh, by the way, Ian's donated a number of nice honey. So we've got one for you, Phil. There's one for me, Andy Esther, Matt Breezer, and Adam Greg. What's this fuzzy lemon? Oh, okay.
The Lakenheath hero.
And then some more, so we'll give those to other
That's
people
your discretion.
Presentations. Brilliant. Phil.
John.
Thank
you. Right, I'm going to talk not so much about balloons as about parachutes. The balloons are merely collateral, really, in this story. I've got the fortunate job of playing around with things that I enjoy doing all day, every day. I've been working for about 25 years as a parachute engineer, not really Earth parachute, but parachutes around the solar system. So my first project was sending a parachute to Titan as part of the European Space Agency mission, and since then I've sent several parachutes to Mars. And there's one there due to arrive in October this year, currently on its way there. So, why the high altitude ballooning with Mars parachutes? First, I need to tell you a little bit about parachutes that we've used for Mars. We've sent things to Mars for a long time now. The first ones were the American Viking landers in 1976. The Americans were working for about 15 years before 1976 to perfect a parachute that would work for a Mars landing. And they carried out a series of very expensive tests where they used high-altitude balloons, big high-altitude balloons, and rockets to get the test parachutes up to about Mach 3 at high altitude. And they tested 3 types of parachute: disc gap band, a ring sail and a cruciform. This is the disc gap band, this is the ring sail and the cruciform. The cruciform is a very simple parachute. And they tested all these parachutes, and in the end they decided, after 30 odd trials, that the disc gap band was the best parachute. And those tests cost an absolute fortune, as you can imagine. So much that no one's really tested a parachute at high altitude since then, and we've all said, well, the Americans decided the disc gap band was a good parachute, so let's just use one of those, save ourselves money. So the disc gap band's been used for the Viking, for the Pathfinder, for Polar Lander, for Beetle 2, the UK space Mars mission, Mars Exploration Rover, and the flying on current missions as well. So, what are we looking for in a parachute for Mars? Well, first of all, it has to be efficient. You have to get the most drag possible for the weight of parachute, because every kilo that you take to Mars costs you many, many kilos in terms of launcher. We have to have a parachute that's going to open at supersonic speed. There's not very much atmosphere on Mars, so we need to open the parachute really early. We need to get the drag working as soon as possible. It also has to inflate at very low dynamic pressure. Now, you imagine Mach 1 at sea level on Earth, that's a huge dynamic pressure. In Mars, it's very, very low, so there's very little pressure to actually open the parachute. And finally, you want stable flight of the parachute. This was a very stable parachute. This was the Mars Science Laboratory parachute, and that was actually taken when it was parachuting down to the surface of Mars. The difficult thing about these parachutes is we need to test them. We need to verify that they're going to work very nicely on Mars. The trouble is you can't do that on Earth because we have 100 times the atmosphere that you'd have on Mars. But we can look at testing in components of the performance. So we can look at the drag of the parachute, we can measure its aerodynamic coefficients. We can use a wind tunnel to do that. The difficulty is wind tunnels are generally designed to test the aerodynamics of streamlined objects. Parachutes aren't. Parachutes cause a huge blockage which affects the results, and if your parachute is too big, it can stall the wind tunnel, just completely stop it. So you need a big wind tunnel. This is a wind tunnel in Ottawa, in Canada. This is a 9-metre square working section, and even a wind tunnel that size, we could only test a parachute which was just over 1 metre in diameter. We did 2 sorts of tests in this wind tunnel. You can just fly it freely, or you can actually constrain the mouth of the vent of the parachute, and you can put on a huge turntable, and you can force it to fly it and it doesn't want to fly it, and that will then give you the aerodynamic coefficients because you can measure the force on the parachute. But it's always a subscale parachute. I've only seen one test of a full-scale space parachute in a wind tunnel, and that was in the NASA Ames wind tunnel in San Francisco, and that has a working section of 80 foot by 120 feet, so a big wind tunnel. And you always have to correct the data. You can also look at free flight. So these were some tests that we did in Devon last year. So this is an 8-metre parachute, and you can drop it from a helicopter, and you can look at how it inflates, although only at very low velocity. You can measure the drag coefficient, but of course the Earth has a boundary layer which makes it very, very difficult to get good, accurate drag coefficient data. So it's not ideal, and none of this tells us about how the parachute works in a low density atmosphere. Now, if you're NASA, what you would do is you would take a huge balloon, you would take it up to the edge of space, you would fire rocket motors to get up to a good velocity, and you can match Mars conditions in terms of density, in terms of Mach number. But if you want to know how much it costs, it's expensive. So this was a balloon, it's a supersonic drag device, and that was very briefly a ring sail parachute. They do say, though, you'll learn a lot more in a test that goes wrong than a test that goes right. This one went wrong very, very quickly. But at least the next time they did the test, it was slightly better. It still didn't work, but it was slightly better.
How fast was that?
That was, I think, Mach 3, something like that. And that was a 30 metre or thereabouts parachute.
30 metres?
Yeah. So that's a seriously big parachute. That's a really difficult thing. I'm not so surprised to have problems with it. That was the low density supersonic decelerator program, and you can find all the videos from that on YouTube. They've done 2 flights of that. They've hopefully got another flight to come. So what we undertook to do for the European Space Agency is to look for alternative parachutes for use on Mars. Maybe we could improve on this gap band. We didn't have the budget, unfortunately, so we had to come up with clever ways of perhaps doing the same sort of test, but with a budget maybe 100th, 1,000th of what NASA were willing to throw at it. So we looked at a number of different parachute types, both existing and new types. I want to do a low-cost program to test how they would inflate, what the drag coefficients look like, and the dynamics in a low-density atmosphere. Now, inflation, drag coefficient, you can look at those. Stability coefficients to some extent, you can look at. But the dynamics in low-density atmosphere, that's the difficult one. And there's a number of different parachutes. This is polyconical parachute, cruciform. This is our old friend, the disc gap band. That's a Russian version of a cruciform that's good, supposed to be good at supersonic speeds. And this is our new parachute that we tried out during this program. And the first thing we wanted to do was determine whether a gliding parachute might be useful. Because if you have a parachute that glides, it gives you 2 advantages. Firstly, you can home in on your landing site to where you want to be. So if you've got a particularly interesting part of Mars you want to head for, you can fly there. Secondly, if you're only interested in the impact rate of descent at impact, if you're gliding, you can reduce the rate of descent without having a huge parachute. But you do have a forward velocity you have to compensate for. So our initial tests were done in the UK, and a lot of you here helped us listen to the signals. So we launched from our headquarters in Chalgrove, just outside Oxfordshire, and as with all parachute tests, or balloon tests in this country, they landed in East Anglia. So this was our payload. So we've got the usual sort of tracker, we've got an antenna underneath, and this is our test parachute. In the early days, we tried flying with a pre-deployed parachute. The difficulty is it tends to tangle itself up during ascent, and there's a good chance that you're going to come down with a bit of balloon still attached to it. And if you're trying to get the performance of the parachute, a bit of balloon attached to it really doesn't help the performance. So this was our entire flight train. Our payload was just that little bit down the bottom. We also flew a school payload on the same flight. These are miler balloons with a little bit of gas in them just to see how they inflated as the altitude increased. We have one of Anthony's backup trackers there and our recovery parachute in case the whole thing went wrong. So we flew that, as I say, from Chalgrove, landed in Cambridgeshire, and we had an upward-looking camera on the payload, and this is what we saw. Just before release, we had a pyrotechnic release which cut us down at 25 kilometres. A little bit of tumbling, and there's our test parachute. Now this was a parachute that we knew would glide at 45 degrees, so we wanted to know how that would behave in a low density atmosphere. It doesn't look too bad, but you've got to bear in mind this test was done pretty much in the middle of winter, so the sun would have been no more than a few degrees above the horizon, and you look at the top of the parachute, you're going straight through the sun. So this parachute is actually in a death spiral, and the angle between the horizon and the vertical is probably over 45 degrees. The interesting thing came when we looked at the data from that parachute, and we calculated the drag coefficient of the system just from the rate of descent, because we don't know how fast we're translating. And we found that the drag coefficient looks really low. Actually, that's what you'd believe for a parachute, about 0.6, until we got down to 15 kilometres, at which point, click, drag coefficient goes up to 1.5. What's happening is at that stage, we get to a dense enough atmosphere, that parachute's now gliding. So initially at high altitude, the payload, parachute's going round and round the payload, combing in a death spiral. When we get to 15, it's over a period, literally seconds, it starts gliding. And this is a phenomenon that we predict to occur as the density of the atmosphere reduces. So for an atmosphere as dense as Mars, you want to be in this regime, so a gliding parachute is really not going to work for you on Mars. Same thing is if you try a ram air parachute at high altitude on Earth, you're going to have real problems in controlling that. So we also tried on one test putting a cluster parachute to see whether that would cure it. And of course they both flew at 45 degrees and they spun around each other like a top. So that was a learning experience. So now we know that gliding parachute is really not the sort of thing you go for Mars. So we came up with a number of potential parachute types. And before wind tunnel tests or anything like that, we wanted to do some real cheap tests. So we built ourselves a very little test vehicle, and we flew it up to about 400 feet under an octocopter. And that gives us some really good free flight data, much cheaper than using a wind tunnel, much cheaper than using a balloon, and we've got all the data we want. So we down selected to a couple of parachute types like that, and then we went out and tested them. So the first test I'll show, this is the 9-metre wind tunnel in Ottawa. We've got 2 high-speed cameras in the bottom. You don't see the parachute until it gets into the high-intensity lights. That's what it looks like on normal speed video, and we measured the inflation force of the parachute. So really good data. This is a 9-metre wind tunnel. In the space of 2 days, we deployed about 20 parachutes of different types. Got some real good data, but it's in a wind tunnel. The parachute's constrained. It's not in free flight. It's high-density atmosphere. Same wind tunnel, we also looked at forced incidents, where we are forcing the parachute to fly somewhere it doesn't necessarily want to fly. So we're looking through the side of the wind tunnel here, and the parachute's actually on the wind on the turntable, so this is the wind axis going through here. So you see we're quite a high angle of attack. And this parachute, this is the polyconical that we used for the initial drop tests, and you can see it's stable at about 45 degrees incidence. That's really quite a high gliding parachute for a parachute that isn't really designed specifically for glide. We also did some low-altitude helicopter drop tests. This is a full-size version of this parachute. This was an 8-metre Huygens parachute. So we've got an upward-looking camera, a downward-looking camera, and a ground camera. And managed 3 drops on this day, and every time the helicopter pilot dropped it directly over that hedge on the ground, that if you drop it on the hedge, you're never going to hit it. Luckily, this was the last drop of the day. It landed right on the hedge. Those parachute lines are 32 metre long and less than a millimetre diameter. After we took it back to the workshop, it took us a full day to untangle those lines. Then the next thing we want to do is look at how this parachute inflates at Mach 0.8 in the low density atmosphere. So we designed a little test vehicle, probably a very similar sort of thing to what Ed showed you a couple of years ago. This weighed 6 kilos, so it's technically a medium payload. We built a little data acquisition system into the middle of it. We have our test parachute in the back and a spring drogue to deploy it. We wanted a pitot tube on the front of it, so we thought the pitot has to be a long way away from the payloads that we're measuring in real free-streaming conditions. So we've got a long rod here to move it in front of the vehicle. So we thought, well, we've got 30 centimetres doing nothing here, so let's make it out of copper tube, and that can be our dipole antenna. And that worked really, really well, because we picked that up with no problem at all over huge distances. But because we're dropping it from 29 kilometres without a parachute, we thought it perhaps better not to do this one over East Anglia, just in case. We did do one test in the UK, which was our precursor test, again from a few hundred feet in the air using an octocopter. And this is the only time we ever saw the sequence operate. So we drop it from the helicopter, and it free falls for a few seconds, spring drogue comes out, test parachute comes out, and we all breathe a huge sigh of relief. So the next time we dropped that was from 29 kilometres over northern Sweden. The power lines are actually a lot further away than So we felt pretty good about that, so we took our test vehicles up to Sweden. Now we had to go for slightly bigger balloons. This is still quite a relatively small balloon. And because we're using one of these rather than a net balloon, we thought, well, let's put 3 on the same flight at the same time. So we had a bar with 3 of these test vehicles side by side. They're completely autonomous. They look at the altitude, they look at the position. When they decide it's safe to drop, they release themselves from the bar. We actually launched them from, this is a map of northern Sweden. To give you an idea of scale, that diamond, the length of each side is about 100 kilometres. The yellow line there is the border with Norway, that's Norway. This is all Sweden, and that's Finland up there.
Were you up there because there's a lack of people up there?
it's a dedicated test range, so if you drop there, the only thing you're going to land on is moose or reindeer. But you're not allowed to test in September because that's when all the Sami go in there to hunt the moose and the reindeer. So we released our balloon from somewhere just near the Norwegian border, and it came up, and when the vehicles sensed that they were above 29 kilometres and were in the drop zone, they released themselves. So release of the first one there, and you're allowed to drift outside of the drop zone if you've got a parachute. It's not a big deal. Anything without a parachute would have landed in the drop zone. And we had very limited assets there. The UCAS listening network really struggles to get Northern Sweden. So we had the frequencies very, very close together, so I could actually pick up all 3 vehicles on one instance of FLDG with one radio, which worked very nicely. What we didn't take into account is when this thing's dropping at Mach 0.8, you get quite a Doppler shift on that system, on that signal. So they start walking across each other. But we managed to track them all down to the ground, which is, we thought, quite an achievement. The other thing I should point out is that talking about roads to get close to where you want to go. Well, there's one road there, and there's one road that goes up the border there, and that's it. So there's one thing that Dave didn't mention on his recovery talk. What you really need is one of these. That's a fully equipped recovery vehicle. In the boot under there, they have a chainsaw, which is really useful to look at some of the stuff. You don't have to land over in this position, you just take the chainsaw and put it down. The guy on the recovery was really upset that we didn't land in a tree because we were looking forward to chopping them down. If you do go chasing a helicopter and you plan to take your magnum antenna with you, be warned that these things are made out of aluminium and they don't stick very well. But this is what the recovery area looked like. I thought it looked like, when you look at the map, it's tundra, there's nothing there, but there were some quite serious trees there. This is an interesting photo. This is the test vehicle where the parachute failed to open. This one hit the deck at 100 metres per second. We got 3 strings on the way down from 28 kilometres. The helicopter pilot did a really good job in spotting it, because all you could see sticking out the bottom was a little orange disc out of that hole, which is about that diameter. And if you look carefully, you can see 4 lines. But what happened is when the front of the vehicle stopped, the fins just kept going. And you can see one of them still embedded there. The interesting thing is we did get data off that. We recorded everything on a micro SD card and it survived. After that parachute failed, we thought, well, we want to improve the system, so we're going to go back the next year, want to improve things. But this time we flew a separate technology research program, and this time we're looking at potential entry vehicles for Earth return missions, so bringing samples back from Mars. One of the requirements for vehicles like that is that you can't have a parachute, because they want a really high probability of the system working. And a parachute only going to work 99.9% of the time. You want an error rate of 1 in 10 to the 6 when you bring in potentially astrobiology back that could kill everyone on Earth. So it's quite a high bar. So you can't have a parachute. So what you want is a system that's going to be stable all the way through entry. Well, how do you test that? Well, what we did is we had some full-scale vehicles. If you drop that from 30 kilometres, that will reach about Mach 0.8, so it'll give you a good idea about how stable it is subcyclically. But we wanted stability right way up to Mach 1.5. So what we did is we took a little vehicle, that's about 8 inches diameter, and we put in a streamline fairing. If you drop that fairing from 29 kilometres, that will reach about Mach 1.5. That's more or less where we want to be. And this is what a little instrument module looks like. That's 8-inch diameter. All the mass concentrated in the centre. These are the batteries, a couple of circuit boards, GPS antenna, and I have a little parachute in this because while the real mission would just impact, we wanted to get our data back without damaging it. So I had a couple of little pyrotechnics that popped an instrument canister out of the vehicle just before it reached the ground. Okay, now we're starting to talk about real balloons here. So we have our balloon that we're inflating there. Our gas cylinder, well actually it's a double-sized container trailer of gas cylinders. We managed three launches off that one ISA pack of cylinders. That's a lot of helium, that costs a lot of money. Our test vehicles hung off the top of this thing, they call that the Hercules. It's a modified tractor. And the idea is that you release the balloon comes up over the back of the Hercules, they then drive around this huge launch pad until the payload's directly below the balloon and let go.
Did you use hydrogen or helium?
Helium.
Pretty expensive.
Very expensive. They're working on going over to hydrogen, but the problem is during inflation, hydrogen can permeate through the membrane of the balloon. So hydrogen is perfectly safe within the balloon, but once you mix it with oxygen, it's a bad combination. And it takes 20 minutes, half an hour to inflate this balloon. So for safety, currently helium. But yes, one of the things that Swedish Space Corporation are looking at the moment is use of hydrogen.
What's the cost per launch?
The whole programme was into 6 figures. 7 figures.
7 figures.
And of course, to hold your balloon down, it's no good having a string tied to your gas bottle. You need something fairly substantial. But when you see it launch, that's quite a launch. And this is all balloon all the way down there. So this isn't extensible, it's polythene balloon. So once you get up to 30 odd kilometres, that is a sphere about that sort of diameter.
Sorry, what is the sort of moustache bit?
Excuse me?
What is the sort of moustache bit? Is that?
Oh, there.
Yeah.
That's the fill lines.
Oh, right.
They have huge industrial size fillers, and then they just tie a knot in it. So you see he's driving across the pad until he gets directly below it. This is actually a rocket launch silo in the back, and the one of the tracking stations down there on the balloon pad. And this video is taken by one of my colleagues up at the top of what they call Radar Hill, and you've got a good view for hundreds of kilometres over the tundra. And there you go.
Nice release.
Nice release. It didn't swing because it's very easy. You don't get the balloon above for this. Just swing down, wipe out the payload on the ground, and you can just watch your payload. Well, the remnants of your payload going into the distance.
How do you get data as still as
that? Okay, so this launch was in June in the north of Sweden. So one advantage is you can launch any time of the day or night. In some ways it's a disadvantage because the lowest winds are always at about midnight local time. So that launch wasn't about midnight. We spent a month waiting for good weather. We had 2 days in that month when the winds were low enough to launch. So with difficulties outside. So this is our telemetry station. This was on the one on the balloon pad. So I've got the laptop. There's actually a phone cube dongle in there, and that's what I used to turn to receive on that particular listening station. I had a total of 4 stations, 2 at the top of Radar Hill, 1 on the launch pad, and 1 in the chase helicopter. And here we saw the flight. It goes right out over Finland. It came back as soon as we were in the safety zone. Parachute test vehicle released itself, and then one of the vehicles, remember that's the big one, the little one, and then the other one, and they come down towards the ground. And then we go out on our helicopter and hopefully recover them. And we're pretty successful in recovering those. So what does it look like? This is the full-scale vehicle releasing from the balloon. The vehicle is just off the left-hand side. We're a down-looking camera. This one's a bit boring. So we release it, click, and it goes, and that's 0 to Mach 0.8 in probably about 15 seconds, and then it's stable all the way down. But we want to recover the instrument module. So again, we did precursor tests. So we took one of our instrument modules in a drop test vehicle, and we dropped it from a helicopter. This one only reached about 50 meters a second. So we've got a heavy vehicle that we dropped from the helicopter, and as we get down towards the ground, you'll see the instrument module ejecting. So there's the vehicle dropped. Again, this video was taken by one of my colleagues on the ground. He did a very good job because that was actually a lot closer to him than it looks. There's our instrument module, and what you don't see is that big vehicle landed about 50 meters away from him. And this is what it looks like close up. So you see quite good with the pyrotechnics. And the idea is the parachute opens and gives a soft landing. We have concrete here, so we have someone catch it. Subscale vehicle. So this is the streamlined one. This is off the right-hand side of the video. Again, you release it, and it's not very exciting. It just goes down. Now, 25 seconds after that's dropped, it's doing Mach 1.5. You were 30 kilometres away from the drop, and that happened, and we heard a treble sonic boom from it. That was very, very impressive. And then when it gets to Mach 1.5, it pops the fairing. So again, we tested that at low altitude. So this is our test vehicle, the fairing release mechanisms in the nose, and then a couple of little springs. And that's it. That's all it needs, because when you got Mach 1.5, a little bit of pressure inside that fairing, and it opens pretty quickly. So we did some numerical simulations to just predict how quickly it would open. And this is very much slowed down, but you can see our little test vehicle and the fairing opens very nicely. And by this stage, the vehicle is pretty much doing its own thing. So we had a tracker on that vehicle. We didn't have trackers on the fairings. We actually got a couple of them back afterwards, but the majority of them just, they're probably found by a reindeer someday. And again, our little instrument capsule which ejected. It wasn't quite as good that time we dropped it. And this is what it looks like in slow motion. So you see a parachute at the top, instrument capsule at the bottom. Those were very, very good. So all we had to do then is recover them. The full-size vehicles after the instrument capsule had been ejected, they were slightly damaged, some more than others. The subscale vehicles, again, no tracker on this one to be ejected the instrument module, but a nice bright orange. These were actually 3D printed. So we found 2 out of the 3 of those. Despite being in the Arctic tundra, we managed to find quite a few puddles. So these instrument modules weren't waterproof, so several of them we got data to about 300 feet above the ground and then stopped transmitting. And the reason is they landed in a puddle. Some of them landed in a tree. These were the better ones, you could go straight to them. In June, though, in this part of the world, you do have hazards, which are mosquitoes. You think Scotland's bad, this place is dreadful. If you stand still for 5 minutes, you'll be eaten alive. And I think that's the last slide, other than the thanks. First of all, to the European Space Agency for giving us money to enjoy ourselves like this. 37 listeners we had for UK flights. Several of you are here in this room today. Any of you who haven't got QSL cards for the flights, please come see me, because I'm pretty sure that I've got cards for you. 1 or 2 from Holland, Belgium and France, and 3 without call signs. We actually had 2 listeners for the Kiruna flights, which we were very impressed about, and they were hams from the middle of Finland, who just got strings once got above 20 odd kilometres. But we'd like to try and establish a listener network in Kiruna in northern Sweden if anyone's interested. Anthony provided a couple of backup trackers which were very useful on the UK flights. So it's very easy to lose a tracker and we really didn't want to lose these parachutes. And finally, Steve, thanks for providing some of the smaller balloons that we used in this test. And that's it, thank you.
Any questions, Lloyd?
Did you get to use your saw on that last one?
We didn't. Not sure we did.
On the 1.5 supersonic flight, presumably it was just the object inside, the subscale vehicle you were testing.
That's the only bit we're interested in. You're watching how stable that is.
How long is that actually travelling at exposed to 1.5 grams?
It started decelerating immediately. It was down to Mach 1 within about 6 seconds, I think it was, and terminal velocity within about 15 seconds. But being subscale, it oscillates a lot more quickly than your full scale would. So we had about 20 oscillations supersonic, so we got a lot of really good data out of that. Yeah?
The simulated fairing disposal, how much was that slowed down?
A huge amount. The whole thing took about a tenth of a second, I think.
Right.
Yeah. So So that was a food structure interaction CFD simulation, which took about a week to run.
I was thinking that the fairing would have opened a lot quicker than that.
Well, let's say it was gone in a tenth of a second. So, very, very quick.
It's very symmetrical, it's not likely to be the case in reality, or that's the modelling parameters, because it's almost perfectly.
It turns out that, well, first of all, that shape is going to go in a straight line. It's very, very stable. But we looked at the simulations with angles of attack of 1 degree or 5 degree, and it still opened very nicely.
Uniformly on both sides, wouldn't there be variance in the size of
The big thing that opens it is the pressure that you get inside it, rather than the aerodynamics of the outside. So once you get that pressure inside, it goes. Okay. Thank you.
I think, I think we'll have Adam up next with.
Can we have a short break first? Because A, I need to grab stuff, and B, I need to get some backboard off you.
Sounds good. Okay, we'll have a tea break then. About 10 minutes. Just probably the wrong place. That's on U5, so Curtis yeah, that's the way. Printed. What remote control? Yes. This is also for PDF because I have the PDF. I think so. Yeah. But we'll see. So, yeah. Do you want to give it a try now?
It's very big.
Yeah.
Weight on the
Well,
make sure
Oh, that's the what you wanted to call for.
Yeah, hi, I'm Emma. I'm very interested that your planes landed in East Anglia.
They all do.
Really?
Turn it down a bit.
Hey, I think you turn it down on here.
Are we going?
Right, yeah.
Okay, cool. Hi everyone. So this is a talk about a whole bunch of rockets that I've worked on recently. It probably should have been called See You Spaceflight Learns About Tolerances, which is kind of the story of the last 7 years of building rockets. So by way of introduction, I'm Adam Gregg. I'm a student here at Cambridge. I'm doing a PhD now, and I'm involved in Cambridge University Spaceflight, which is a student society here, and we work on, some of you may have heard of us, we do like the predictor, habitat, also a lot of balloons in the past. Recently we've been focusing quite a lot on rockets because they're faster, mostly. So this story really starts with a rocket called Martlet 0, which I don't know very much about. It's a little bit before my time, and it was someone's 4th year master's project. And it was really a prototype to be launched from a balloon, so this whole raccoon idea to go to space. It never got launched from a balloon, but it was the only Martlet rocket to be successfully flown and recovered intact. So everything you see after this. Anyway, so it was a lovely rocket, completely carbon fibre. There was a beautiful mould machined out of a solid chunk of aluminium, taller than I am. A lot of faff to make, and it was, by all accounts, a really lovely rocket. But the next one we did was Martlet 1. So this is the same guy during his PhD, kind of modelling with it. This is Martlet 1 in its 2-stage configuration. It was designed to be 3 whole stages, but in the end we could only fly it with 2, and honestly that was quite enough. Martlet 1 had fun new features over Martlet 0, like 3 stages, and the complicated launch rail and everything else that goes with it. Tip-to-tip carbon fibre. The screen's kind of dim. Not sure what's going on with that. Okay, adjusting. Anyway, maybe it'll get better. So you can't really see in this now very dim photo, but the fins had carbon fibre laid up tip-to-tip across them to make them incredibly strong and rigid so it wouldn't flutter during flight, which can cause huge issues. But what we learned was that was a really faffy, difficult process that we never wanted to do again. Huge pain, swore off it. We installed cameras hidden in the fins, looking down, which kind of started a trend for cameras in stupid places because it's really hard to find a good place to put a camera on a rocket. And scary motors. Okay, it's a shame that you really can't see the photos well. It's Ian holding these boxes that are 1.3C explosives and grinning like a maniac. And to get these, I took £3,000 in 50s out of our bank, walked across the high street, went to the other bank and said, yes, I'd like to pay this into this account number. The guy taps it in, on the screen comes up rockets and things. And he gives us this look, like, seriously guys. And we're like... So anyway, we've got the motors. Funny problems with this size of rocket. Like remote launch sites, this is very up north in Scotland where you probably won't damage anything if you come down badly. Huge launch rails, we built this one from scratch and it's a pain because it's expensive and large and it has to take a rocket going very quickly off it. Difficult car packing, this wasn't so bad, everyone fit in 1 or 2 cars and it just gets harder and harder as the rockets get worse. And quick running away, which is essentially the sort of thing. The design for this rocket unfortunately meant to arm the top stages, you had to be at the top stages, which meant a step ladder, Ian wearing motorcycle levers and a helmet, leaning over the rail. The fins are razor sharp, right? So if this thing takes off by accident, and bear in mind because it's 2 stages, it has to ignite itself, it will go straight through your arm as you're leaning here, arming it. So hence the quick running away. Anyway, we did get to launch it. So this was in 2012, and it took off beautifully. There's it streaming up. The top stage burnt out. Everyone's counting the 4 seconds until the next stage kicks in. It's nothing. And everyone's like, oh shit. And then 11 seconds later, you hear the roar of a second motor kicking in because it's so far away, the time it took the sound to reach you from the ignition, which no one had really contemplated. So it did work beautifully, but we didn't realise until we suddenly clicked, of course, it's miles away. So the second stage took off, that was great, and then it landed. Unfortunately, none of the main parachutes came out, we never found the top stage, and we found the bottom of the bottom stage, slightly worse for the wear. Probably the rest is lost in a peat bog forever. A couple of problems with this. 1, a sudden blizzard rolled in just as everything started landing, which was unfortunate and made finding things very difficult. 2, Scottish Highlands. And 3, the cameras were all in the top stage, including the fin cameras, so we didn't get any video footage back from the launch, which was a real bummer. So we thought, right, well, we've learned a lot of exciting lessons. Next time, we'll do something much better. We're going to go out to the States, where you can launch, I don't know why the photos were terrible, in this huge open desert. This is Black Rock Desert. You can't hit anything for miles and miles. It's completely flat. You can see forever. You can drive in a straight line. Easiest recovery you can imagine. Unfortunately, it is incredibly inhospitable, and also the desert corrodes anything metal that it touches. So we didn't keep the rocket in this position for long. Anyway, so more fun new features. We decided, okay, scratch the tip-to-tip carbon fibre. We'll weld the fin can together. That sounds good. But to make it stiffer and lighter, we'll drill loads of holes out of the fins and put carbon fibre inserts in, which means black panels that you can't see very well. And then it'll be really strong and tough, and we did a bunch of analysis and decided this was a fantastic idea. We even put strain gauges in the fins so we could measure how much we were fluttering, which was a big faff, but you get there. And same old problems, inhospitable launch sites. Here's it's a beautiful sunset, you can imagine the rest of the desert that you can't see. But it's a 12-hour drive from San Francisco, non-stop. And then you get there and it's 3 AM, and you realise you don't have to set up this ridiculous yurt-like tent that you need to survive, and it's going to get minus something scary overnight. And then in the daytime when you wake up, you're sweating buckets, and you need to bring all the water you'll need for 4 days or you'll die. So packing was difficult. This was our attempt at boxing it up before shipping it out to the States as unattended personal effects, which didn't go down very smoothly with customs. The launch rail we had to design to take imperial fittings, which we're building it in the States, which was a gigantic pain, don't really do metric, and it was much, much further to run away. Anyway, oh my goodness. Well, we had exciting new avionics. You can kind of see the silhouette. So, I don't think it's the mouse, because the top is a nice white.
So it's classified.
Yeah, maybe it's the classified.
The connector's alright, is it?
Yeah.
I think you saturated the projector.
The bottom part is all fine. So I think it's just doing something really stupid. Who knows what?
Is it worth crazy?
That's maybe. Oh, I'm not using the project center mode anyway. Let me just try starting this part again.
We're going to upload the presentations later, because if you do, I hope they have that fixed.
Yeah, the projector is glitching earlier.
Yeah, I don't think there's a projector issue. Right, okay. Time for backup down. Okay, no, it's definitely a projector issue.
We got the connection.
We got the connection.
There's a connector actually.
Yeah, it's a PGA cable.
Bad connection.
Let's try the other VGA.
Like banding or
Yeah, VGA2. You're on VGA2.
I'm on VGA2.
That's
That's up to you.
Steve Young.
Or video system. Super well. It's like the other VGA.
Worth a try.
It looks more like an LF. Lack of LF response due to a bad connection.
This VGA is doing the same thing.
Is it the resolution?
Maybe.
That adds your own projector.
It'll be a bit of a short effects. Take on step version slides on PDF. Got a step stick. Okay, cool.
So this is it, piece, what type of presentation?
PDF.
PDF, okay, we can write the same. Put it in that. There.
Stick on yours, Steve.
Yeah, well, this is a Mac here. Nine should pop up on there any second. Okay.
That's just a receipt. Yeah, it's just a
Okay. Okay.
Then it's full screen. Okay, that's still reload. Run the screens on.
Okay, well that'll do. Okay, we'll quickly. Oh no. Okay, it's not actually doing a pretty animation, so unfortunately all the pictures are just on top of each other. Never mind. Exciting new avionics. So we decided for this one we'll just have one amazing flight computer for video things. So it's got like a whole bunch of strain gauge channels, driving couple channels, big STM32, several different IMUs, serial link, SD card. Everything is isolated, a bunch of IoA channels. It was a huge, gigantic faff to make, and no one could help because if you've ever tried multiplayer PCB routing, it doesn't work very well. Separately, we had a radio, old classic radiometrics module, nothing particularly fancy, and we were like, well, it'll probably be good enough, had a little beeper. For ridiculous reasons, there were two of these in the rocket that had to talk to each other over this XP serial link because it was poorly designed. We took it to the States. The first year we went in 2014, we were all excited and ready to launch, but really we weren't ready at all. We got through till Sunday when we realised A, we probably weren't ready, and B, the weather wasn't good enough. You can't fly unless there's like less than 50% cloud cover, and we had 100% overcast skies. So we went back home, tails between our legs, came back for a year later with some upgrades, and eventually got to launch it. So this was a beautiful rocket. It's the biggest motor you can buy commercially. It's an O8000 for people who know about amateur rockets motors. It's about 40 kilograms wet, it's about this tall off the ground, quite big, 8,000 newtons of force as it takes off, which was 20 Gs of acceleration on this rocket. So it's doing Mach, I mean it's not a 60, it's before it leaves the rail, and it's Mach 1 is I think a second in, and by about 3 seconds it's doing Mach 3, at which point it's 2 kilometers up. So it's a speedy rocket. Unfortunately, as it turned, well, do we get the...
You have to run quite quickly as well.
Yeah, you have to. I think it may have actually...
No, that's not the explosion.
Oh, that's just the slideshow. Okay, there were some YouTube videos, but... Okay. I suppose I can probably pull up YouTube videos separately and just weep without PDFs later. It's worth saying because it's the only video in the whole presentation, so you're ashamed to miss it.
You think on IRC can actually log in at the same time?
So there was a lot of there's not much video because it goes quite quickly. There was a lot of faffing around on the pad, and unfortunately it means 4 of the 6 video cameras we had watching this thing take off ran out of battery before we got to launch. It was one of the many lessons we learned. It took off. In the next video, you can get a bit more impression. I don't think sound's working. It's a shame. So we were about 500 meters away at this point and kind of biting our nails. Anyway, it goes up. That's all beautiful. And about 3 seconds into the flight, we see this, which is very rarely a good thing. What we actually see is that it stops going straight up and starts spinning violently while emitting a lot of smoke. And then that bit at the top is something that went flying up. So it basically self-destructed as soon as it hit Mach 3. And obviously this isn't really what we wanted, so we had this sort of, oh no, okay, well you can't see the other spare photos, which is a pity, but probably for the best. Basically, everything got totally destroyed. Parts were ripped off the flight computer. Everything was exposed to Mach 3 airflow very quickly. So literally stuff was being ripped off that was soldered down. SD cards were flung into the desert. We had a couple of those 808 keychain cameras you can get on eBay in various parts of the rocket, and we found various parts of them, like half the case, the lens module, a broken PCB. Sadly, none of the SD cards. So this was the desert where we spent the next day walking for 3 miles in a straight line, and then you make a small angle and walk for 3 miles in it. And you keep crisscrossing, and you keep picking up bits of debris. So we found over 120 bits of carbon fibre which had been smashed up from the rocket as it destructed itself in flight. And we are pretty sure we know what happened, which is that the incredibly clever fins broke, basically. The glue holding these carbon fibre inserts onto our lightweight aluminium fins failed, possibly because all the little holes full of air that pushed out when it got to low pressure, possibly because it heated up, or possibly the glue just wasn't properly applied. In any event, as soon as that panel came off, the fins started fluttering. We all immediately regretted not doing the tip-to-tip carbon fibre we'd sworn off last time. And when the fin goes, that's it, you lose the rocket. So we went back home, tail between the legs again, thought, right, let's do a much simpler rocket. We'll keep this one really easy. And then about half an hour later, we're like, right, it's going to be a boosted dart with 2 side boosters. So we built it, actually. So this is Marlet 3, which is what we've been working on for the last year. Here it is in Scotland like a week ago when we were on our first launch attempt. Well, this is a conundrum because there are several pictures overlaid that you can't see here. But basically, it's a boosted dart. It's very nice. You can actually look at it because I've got half of the dart down here. And also, there's a new avionics stack, which you... I'm going to plug it back into my laptop because otherwise it's just not going to work.
Do you want to describe a boosted dart?
Yeah, so the gist of this flight is, as I guess you get to... Okay, well here's the crash landing, so you can kind of see what happened here. Those 3 fins all got bent around mid-air by the air forces. So it turns out at Mach 3, air is no longer a soft thing you can push your hand through. It's now like these 10mm fixed aluminium plates just got bent around the vehicle. No trouble. All the carbon fibres obviously popped off. The vehicle shattered. The carbon fibre tube that was holding the motor is broken horribly. We found all the large components. Most of it just got sheared straight through. The parachute was a tangled, tattered mess. So the parachute is stored in the top part, and it's meant to come out the top, but instead it came out the bottom, inverted itself, and then shredded. At Mach 3, which it turns out is too fast for this parachute to inflate. One of the flight computers realised what was happening before its batteries were violently disassembled, and tried to fire the parachute release, but at that point the parachute was very released. The other flight computer lost power immediately the thing started spinning round. It was all in all quite a bad day. We did manage to find one SD card from the entire thing, which was one that didn't get violently ripped off because it was quite deep inside. And this is one connected to a strain gauge on the fin, and it turns out the fin it was connected to was one of the ones that bent all the way around. So we're looking at the signal on the strain gauge weeks later, and the rocket takes off and there's a little bit of strain, and then it starts oscillating, and then there's this huge spike, and then that's it. There's no more data after that, as the rocket self-destructs. So it really did a number on itself. You can see we had some expensive stickers on there, but they're all just white bits of paper now because the artwork was just ripped off. The electronics were thoroughly trashed. I think, oh yeah, so this is Jack with his parachute system. This is the trashed electronics. This is the one where the SD card survived. You can see the holder is still on. On the old board, the holder was just ripped off wholesale, but the connectors didn't do so well, and there's a lot of like bent, mangled aluminium in the lab now. And searching. Okay, so Mark, 3 fun new features. 3-stage boosted dart. So the idea with this is, after your motors are burnt out, you've got a lot of mass which is just drag and it's slowing you down, and if you just cut it away, you'd go much higher. So we have this heavy streamlined dart at the top, which is as heavy and dense as you can make it, but really narrow and streamlined. And as soon as the motor's burnt out, you let it go, and it just coasts. And it coasts for ages. It's terrifying. When this thing launches in its full config, it coasts for like 90 seconds, just going up to apogee. And its apogee is very high. Like, we should comfortably beat the ballooning record. And we'll do it a lot quicker. 90 seconds. To make it more fun, we have 2 more of these rockets strapped on the side. So they take off a pad, they boost off to the side, then the middle one ignites, and then it releases the dart. Like I said, it's as simple as we could make it.
What kind of altitude do you reckon you might hit?
We're aiming for 50 kilometres.
But could do.
Yeah, could do that. We'll see. It has conformal antennas, which was a complete nightmare, but actually worked quite well in the end. So if you're in a metal rocket, in this case it's all metal or carbon fibre, there's nothing that's radio transparent. You can't put your antennas inside. And when I suggested to the aerodynamics team that we just have the antennas sort of sticking off at an angle like this, because that would be quite good, they shut me down. So instead you have to do what they do on missiles and other scary vehicles, which is have an antenna that wraps around the outside of your rocket. It uses the rocket's metal body as its ground plane, and it's like a patch on top. So you'll have seen GPS patch antennas, which are a little metal bit, and then some kind of funky yellow stuff and then a ground plane. This is the same sort of idea, except conformed around the body of the rocket. So we designed these, and I'll talk about them more in a bit. As a boosted dart, I mean, we really enjoyed it as a boosted dart. The new avionics stack, which I'll also talk about in a second, and yeah, it's a really pretty dart. So the avionics stack, we had to build new avionics because the last one was completely totaled, and also has to fit inside this dart, which is 40mm in diameter. So, you know, we designed the avionics to be 40mm PCBs, and the mechanics team designed the tube to be 40mm. And we learned about tolerances. We learned about tolerances by putting sanding paper on a drill and sticking it inside the tube until it was 40mm. At the bottom is the baseboard. This has connectors for all the arming switches, the umbilical, everything else, plus it does USB to JTAG, so you can JTAG, debug, and reprogram every microcontroller in the entire stack while it's inside the rocket from the ground. And it does USB to CAN. We have a CAN bus, which is sort of like I2C or serial, except a bit nicer for this application. So you can plug into the rocket and do everything. Next up, there's like a thermocouple interface, also strain gauges and other things. There's a data logger board, which has an SD card and saves everything that happens in the rocket to it. Power supply boards are kind of unnecessarily complicated. We have 12 DC-DC converters, each of which is individually monitored, regulated, has telemetry, and also you can like program them, you can current limit, they can auto rebrake. It's kind of fancy. Battery cell, it's 2 18650 batteries, and you can charge them and balance them and all the other things you want to do. Flight computer works out when to fire the parachutes, the most important part. 4 channels of pyros, you can't really see. There's a radio, which is a standard sort of radio. It's a U-Blox GPS, and the radio transceiver, the idea is we can uplink to it, so if need be, we can remote fire the parachutes when it all goes on. Most of the stack can be broken at that point. You can send a command to the radio board and it can send it directly to a pyro board, even if like the flight computer has gone down and the data logger has gone down. You want to think about how that would happen. And then at the top there's an inertial measurement unit, so it can kind of work out its attitude and collect other data. For the boosters, the dumb boosters, we just have a little chip, but for the dart we have this 700-pound box of magic. It's like 2 by 2 by 2 centimeters, so well worth its weight in gold. It's weighted in gold. And apparently it's very good. So yeah, there's loads of avionics. Basically, we spent ages designing all these tiny PCBs. They'll have interconnect in the stack and have some here that you can look at afterwards if you're interested. Conformal antennas. This was one of my favourite parts of this. Like, antennas are kind of interesting. On HABs, we mostly stick to the things we know, which are these quarter wave whips. And they're okay, probably fine for HABs. Conformal ones are fun if you really need to fit some weird design pattern. So what you can't really see here is, this is in KiCad, there's a Python script that generates whatever antenna network you want. If you have multiple of these patches, you just kind of stick them together in a tree, and it works better. Then, having done the design, you print it out, you hold it up to the sun because you're too cheap to buy a UV light exposure box. And actually what happens is you've got 3 days until you need to drive to Scotland, the antenna's still undone because someone let you down and the PCB manufacturer doesn't want. So you've bought a panel of flexi PCB and you decided to home etch them, and you're holding it up to the sun just a few minutes before sunset, and you're like, I've got enough exposure time left. And you do, it develops okay, you get chemicals all over the lawn, you stain the patio with ferric chloride, you end up with these lovely antennas, and they're very flexible, you can wrap them around the rocket. You take your rocket parts, we used Kapton as a dielectric, which was a poor choice, don't do that. But it is very easy to stick on, that looks really good, like some kind of sci-fi crop. You wrap the antennas around them, and you have these beautiful conformal antennas. The VNA says, try harder next time. But the U-Blocks gets a lock, so you call it good. Possibly they'll be really neat for HABs. So this is an 868 MHz patch antenna. It's about this big, and you could put it on the bottom of your HAB payload, and its radiation pattern would be a hemisphere straight down, which means you don't have a null directly below the payload, which is nice, and it's flat, which is nice. So you don't have spears of death, and I don't know, it could be worth trying out sometime. So possibly this would be a fun thing to do on a HAB, and you could just get it made on a normal PCB if you didn't need to wrap it around a rocket, which would be a lot easier.
Did you look at slots at all?
Yeah, so we looked at a lot of things. It seemed really difficult to get slots to do what we wanted on a rocket. Probably that'd have been fun, but the nice thing about this is the rocket is still solid steel all the way down, nothing going on. And we can kind of just stick the antennas on the outside, screw them in. I don't know, it seemed like a good idea. It's what people tend to do in sort of applications.
Slots even, especially with flexi, anything like that with IG could be interesting. Very slot width.
Exactly, it wouldn't be much fun, whereas this...
I would have thought the Kapton tape was probably a good, good...
I thought Kapton was a great choice. It has a really well-defined dielectric constant, but because we need about 0.5 mm thickness, you have layers and layers of Kapton tape, which is actually 50% silicone goop by volume. And that has a less well-defined dielectric, but more importantly, varies dramatically with moisture. So we cut them and tuned them on the VNA, and so everything's perfect. We came back a day later and they were way off, like 10% off frequency. So what we were meant to go and get is real serious business dielectric from Rogers, and they didn't ship it, and they still haven't shipped it a month later. So anyway, cool. So that brings me to the live demo.
You could maybe strip the silicon off the Kapton tape.
Yeah, but then it wouldn't stick, and it would be awful. I mean, it was bad enough sticking it on, honestly. I think you buy the sensible dielectric and you can just about conform it. So one of the many stupid problems we have to solve on this is the parachute deployment is obviously critical. In the dart, you've got something, I mean, you can see how long this is. The actual dart is more than twice as long, and the top of it is just this horrifying steel spike, solid steel. If that comes down on a person, I mean, it's immediately curtains. It's landing velocity even on the parachute is 5 meters a second or so. It's landing velocity without a parachute is too scary to contemplate. You won't hear it coming. So the parachutes have to come out, and we've got quite a good system to eject the drone, but to hold the main in place and then release it, we use this kind of lazy line idea from sailing, I guess. You have a line that goes to the top of the main parachute, and it's quite short. So the main parachute can't come out because this line is holding it in. And then at the right time, you just cut the line, and the parachute can come out. This is basically the HAB cut-down problem, in that you have a short piece of wire that you want to cut at the right time. And we came up with what we think is quite a nice solution. I'm not sure if anyone's done it in HAB. Almost certainly someone has, because people have done everything. But you can buy these things to ignite fireworks called Talon igniters, and they cost 30 pence each, and they're really nice. They're quite reliable. And what they do is melt through nylon cord that we use for HABs immediately, every time. So we use that, and it worked beautifully. So what I have is a little bit of a demo. Because everything else works super well so far. So let's play this. So what we have here is the very janky dashboard we cooked up. That's probably okay. Yeah, so we did this very quickly in the field. It's connected to the avionics stack inside the Star, which is currently running via this really nice umbilical cable, these really nice Limo connectors. And it's reporting on everything status. Most of the data is turned off right now, so not much is going on. But for example, if I go to the flight computer's power channel and turn it on, the flight computer boots up and starts whining about the pyro not being armed and everything not being ready, and it's not happy to fly right now. I'll just turn it off again. There we go. But what is on is the pyro board controller, which is in the top right, and it's very happy with life. It says right now it's disarmed and supply isn't connected, but we do have continuity on pyro channel 1, which is good news. So if I turn the arming switch, then the supply is now live, and we see the supply status is now 7.8 volts, which is battery, and then we arm it, and it's now sort of armed at the top, and then I need a volunteer to hold this while I press the fire button. And no, in all seriousness, I need a volunteer to hold this. Or I can press the fire button, that's fine, I can't do both at once.
I am happy with the pyrotechnics.
Oh, the good news is it's not even technically a pyrotechnic, it's just a hot wire. So, if you just suspend my backpack from this rope, you need to hold the dot.
Hold the dot, okay.
Nice. The backpack models the parachute under the drone
It's on
floors.
and it's spring mounted.
Sorry?
It clips on and it's spring mounted.
Spring mounted is a strong word, there's a rubber band.
Okay.
And we go to channel 1 and we say fire a talon. Just like that. So yeah, I think it might be worth trying in the house. It's the same cord we use for house. It works every time, they're 30p a shot.
Is that what you were going to do in the pub last night?
No, it happened in the pub last night, so I was bringing them from the lab and decided to go straight through. But yeah, about half a second. We fire it for 2 seconds, just to be sure.
Yeah, sure.
And now we can disarm the fire board.
No bang. Annoying.
Not safer for kids.
So yeah, a lot safer for the kids, and also for the people flying the house. Anyway, that's the end of the talk. Weirdly, it got my Twitter handle in white, but the rest of it is still greyed out, so that's nice. So yeah, I'm happy to take questions. Also, you can come and look at the hardware now or later or whatever, if you like.
When you launch the hardware?
Oh, launch, yeah, I didn't mention that. We took it to Scotland to launch, but it wasn't ready, so we didn't launch it. We really wanted to, but it wasn't safe. So hopefully January, February in Scotland, and then we take it out to the States next summer, as in 2017, to do it with a big, scary, serious business motors, where it goes too fast. It hits like Mach 4 peak velocity before it lets go of the dart. So this horrifying thing is doing Mach 4 up, and then it just keeps going over a minute.
So if you go to the States with it, what will you be doing in Scotland?
Scotland is a test launch. It only goes, well, the highest we're allowed to go is 6 kilometres, so we have this horrifying ballast. It's 8 kilograms of solid steel, just a giant lump that we just put in the bottom, and that keeps it heavy enough, and then you hit 6 kilometres on the way.
At which point, if there's anybody under it, they get brain.
Yeah, I mean, honestly, seeing some of the things people are launching in Scotland, don't know. It's going to hit at most one person because it's quite small. I mean, in all seriousness, it should, like, we only launch when we're happy the parachutes come out, right? That's why we didn't launch in Scotland 2 weeks ago. The parachutes, we weren't 100% sure. So we don't want to hit anyone with our rocket. That'd be really bad.
What's your annual spend?
Oh, lots. So the total budget for this is about £10,000–12,000 so far, just for this one. I mean, okay, it's lots for us because we'll have to go begging to sponsors. The Model 2, which is now completed, albeit destroyed, was about 14,000 in total.
That including your launches in America?
Mostly, yeah. It doesn't include, so a lot of us got travel grants individually to go flying to the States, so it doesn't include people flying to the States. But it does include like renting an RV and petrol for the RV, which was horrifying.
Are you sure that the flutter problem was due to the carbon fibre separating? You said that you saw sort of exponentially growing oscillation in the strain gauge.
Yeah.
Did you pick up some event on the strain gauge from the separation of the carbon fibre?
We think we're pretty confident we saw the carbon fibre disc come off before it ever went poorly.
So why did that cause the flutter to start?
As soon as carbon fibre is off, the fin is now much less rigid.
Oh, okay.
The carbon fibre is there to keep the fin rigid, so as soon as it's off, the fin can flutter.
I was thinking it was there just for aerodynamic sort of.
Oh no, it's to keep it stiff enough.
I see.
But which is like I say, yeah, Model 3, we fixed that problem. Everything is now solid aluminium. These fins were milled out of solid, and the booster fins are welded on, and they're much tougher and smaller. And we did a lot of clever maths about modelling the fin flutter, including a bunch of really horrifying Mach 4 simulations.
A bit horrifying.
So when will the cameras be mounted on
So they're poking through various things like inside the antennas. Someone was like, can I drill a hole through your antennas? But the camera, no, you can't put a hole through the... In the dark, there's a camera looking down through this really ugly hole in what would otherwise be an unblemished boat tail at the bottom. And then there's another one that looks out sideways. The booster has one sort of looking up at the dart as it separates. And we're hoping to catch the side boosters as they come off, but we haven't quite figured that out yet.
Do you have any stability control at all?
No, it's entirely passively controlled. People get really nervous when you build active controlling. It's much harder to get permission to launch.
It's quite actually stable in a straight line.
It's really stable aerodynamically, so it will absolutely stay in a straight line. It's still like 3 caliber stable at Mach 4 is kind of horrifying.
When you start dynamically controlling it, they tend to start thinking
Homicide.
about it.
It doesn't have a payload, right? There's not even, so one of the nice things, there's no black powder in all this. All our pyrotechnics are like either very well contained, or there's hot wire, or there's a CO2 ejection system for the main parachute. So unlike a lot of rocketry, there's not really anything in the way of serious explosives inside, except for the many kilograms of rocket fuel. I mean, it's still a kinetic kill vehicle, right? It hits your Mach 4. You lose.
Twice as fast as a regular missile, and that could be carrying explosives.
There you go. Yeah, it wouldn't be good. All the air traffic gets diverted before we launch.
What kind of fuel are you using?
It's all commercial ammonium perchlorate. Is it? So like saccharine.
So what was this again?
No, solid. Ammonium perchlorate. That's it.
What the solid fuel boosters were on the shuttle?
Yes, same chemical, but smaller. So the way these motors are rated is like an A motor is the sort of tiny thing you launch in your garden, and a B motor is twice as much total impulse, and a C is twice as much again, and so on and so on. The space shuttle is like a ZZZ. It's kind of on the end of that scale. The ones we're launching are O's, which are still kind of horrifying. It's the biggest you can launch while getting incredibly scary waivers from the FAA to fly them in the States. So it's also the biggest you can buy, really. You can't make your own because it's very illegal here. Alas.
Not in some states.
It's legal in the States, yeah. We fly out several weeks before
In
and
some
learn how to make
states,
solid
some
rocket
states
motors.
you can make your own rockets.
But not in England.
Not in England.
No. So we'd have to fly them off in advance and then learn how to do it and then build it. And it probably wouldn't go so well.
What's the biggest rocket you can fly in the UK?
Sorry?
What's the biggest rocket you can fly in the UK?
You can fly an M
motor,
an M. You can fly an M motor. Well, that's as big as they go, and then you have to start informing the CAA special, to get a special permit.
So the Scotland launch, this was an M1450, which is a lot smaller than the full scale one. Like the motor we're going here is about this big, and the one in Scotland is in the States is much bigger.
I mean, M, N, O, so you're only 4 smaller.
Yeah.
Factor of 4 smaller.
What's the total weight of the boosted dart itself?
The dart itself is 7 kilograms,
Oh, wow, okay.
most of which is in the nose cones.
Yeah. So where's the centre of mass, or is it even?
I mean, the dart goes out to about here, and I can't remember the centre of mass is. It's surprisingly stable, though. The centre of pressure is very nice.
Have you considered doing a raccoon, or have you just ruled that out?
Instead of a platform.
So we decided rockets from the ground is much better. Although getting to 100 kilometers is still really hard. I mean, the rocket maybe helps with that, but you have other problems.
Yeah, I'm still working on a raccoon, but other day job came in the way.
But children come probably worse.
That's planning to use a D motor just for comparison. So I think I can do it with a D motor.
From a balloon?
From a balloon, which is kind of the opposite end of the scale. The total mass are 27 grams at
I think there's something like 60 or 70 kilograms of fuel when this thing's flat on the pad. As much as
When are you planning to launch?
in September 2017.
Oh, okay.
For the
So,
Swiss launch.
hang on, the launch in Scotland, that was just going to use a...
That's just a small single stage.
Oh, just a single stage. I
systems.
see, yeah.
There's an mass behind it.
Yeah.
Okay, on time. So, Yanis, you're on next. Cheers. There's the microphone, and there's a mute switch on it, so it's muted. About the same. Have you got plugins? HDMI would be better, wouldn't it? Yeah, sorry.
I'm just going Cool. Okay. No rocket science now, I'm afraid. So I'm Johannes, and up there are Emma and Andy. We're from the University of East Anglia, and I'm going to introduce air cores to you, which is one part of our project to better explore the stratosphere. Before I tell you about what air cores are, what they do, I thought I'd give you a little bit of a background on what we're doing when we're not launching balloons. And actually, in fact, we haven't launched a balloon yet, I should say. So we're here also looking for advice. So what we normally do is we're interested in trace gases in the atmosphere, which typically, as the name says, have low concentrations, but some of them can have quite large environmental impacts, such as the greenhouse effect, and we're particularly interested in hydrocarbons, so hydrocarbons that contain at least one halogen atom, fluorine, chlorine, bromine, or iodine. And so what do they do? So next to the ground, in the troposphere and in the stratosphere, which is also where the ozone layer is, which is quite of interest to us. So the hydrocarbons are typically emitted from the ground or near the ground, and you can get quite high concentrations there, especially if you're in a confined space, and then some of them can be quite toxic. Anyone heard of Teflon fluid before? It's partly, partly fluorine, but it comes from Teflon in frying pans and stuff. That's mostly HF, but also some hydrocarbons as well. And the troposphere, they're most of the hydrocarbons are quite strong greenhouse gases, so more than 12% of the man-made part of the greenhouse effect, and some hydrocarbons, not all of them, so basically just the ones that contain chlorine, bromine, or iodine, destroy ozone if they reach the stratosphere. Well, not the hydrocarbons itself, but basically their decomposition products. So where did they come from? Actually, there are quite a few natural sources, such as seaweed, and Emma has worked with seaweed quite a lot. And there's some rice fields as well. These are, whilst biogenic, are not necessarily natural sources. And then there's a whole raft of man-made sources for hydrocarbons, from fire extinguishers to asthma inhalers and fridges, and quite a large chunk is also used in foam blowing, so insulation foams, which we have to keep in mind if we want to take any samples in the stratosphere, because they can have high concentration. So typical concentration for hydrocarbons in the unpolluted part of the atmosphere, you get from a few 100 parts per trillion, so 10 to the minus 10, but that's the upper limit essentially, and then you can go down to 10 to the minus 15, like a part per quadrillion, ppq. So, and the most famous, or rather infamous, helicoms are the CFCs, fluorofluorocarbons, developed in the 1920s by Thomas Mitchell Jr., and then they were sort of wonder chemicals at the time, used in all sorts of applications, especially fridges.
Is it the same bloke that put lead in fuel?
Yes, no, he has been called the one individual that has caused the most damage to the planet. Yes, which wasn't his intention, really. Poor guy. So then, basically, later on, what emerged is that the CFCs, they don't break it down at all in the troposphere, which is why they were so good. But once they reach the stratosphere, they do, and then they deplete the ozone layer, which protects us from UV light, and that's why they have been, in an international effort, replaced with other compounds that are less ozone depleting or actually not ozone depleting at all. And industry does continue to introduce new compounds, and we try to see how much of them is in the atmosphere and reconstruct their atmospheric histories. So what we do is we get air samples from all over the world. So this is our dungeon. Basically, we've got an air archive from Tasmania, so that's sort of as clean air as you can get. So the wind is typically blowing from Antarctica there, a place called Cape Grim, and it is, yeah, I was there. If the wind's blowing from Antarctica at 90 miles an hour, that's not very pleasant. It's very hard to hold the camera. And then this is the Jungfraujoch station in the Alps, 3,500 meters high. Been there in winter, it's equally unpleasant. You can't go outside because you've got like several meters of snow outside the door. And then this is basically a drilling campaign in Greenland where you can drill into a glacier, and you've probably heard of ice cores. So drilling into the ice and then extracting air or ice that's 100,000 of years old. On top of the ice, you get what's called firm snow, which is very hard snow, and there's a layer of up to 100 meters deep, and that can get you back in time up to 100 years, which is enough for CFCs, because 100 years ago there weren't any in the atmosphere. If you want to reconstruct the atmospheric history of CFCs, you drill in there, and the deeper you drill, the further you go back in time, essentially. And then we also get regular samples from Lufthansa flights around the world. So they collect samples in sort of a typical 10 to 12 kilometer altitude range, which is not quite where we want to be if we want to be in the stratosphere. This is sort of scratching the bottom of the stratosphere. If you want to go higher, you need this. This is it's a former Russian spy plane, which is now a European research aircraft. And that can go up to 20 kilometers, which is quite nice. And then actually, this bit has already been spoiled before. So the big balloons, these are the ones, well, this is not launched in Kiruna. But they're typically, that's the only place in Europe you can still launch those large balloons, which can have up to a ton of payload. And the rest of Europe is now too densely populated. They used to launch them still in southern France, but once it crashed through the roof of a farmhouse, regulations got a little bit tighter then. Yes, and I, having seen Hercules vehicle earlier, I have actually been to a launch in Brazil, where the Hercules, which has to really sort of release the balloon, went halfway up because there's quite a bit of wind. You typically don't get low wind conditions in Brazil, or very low at least. So it was sort of off the ground, even though it's quite high. It's a bit scary. So once we've got all those samples, they come back to our dungeon. So this is our big mass spectrometer. So what we do is we separate the trace gases from the main air components like oxygen and nitrogen, mainly in the noble gases. And then we still have a bunch of several hundred trace gases, so we have to separate them from each other using gas chromatography, and then the big part. So this is the gas chromatograph, and this is the big part is the mass spectrometer, which can detect up to 1/10 of a part per quadrillion, so 10 to the minus 16 parts in 1 part of air, essentially, or 1 part in 10 to the 16 parts of air, which comes down to basically as an example, if you have a gas, the volume of a sugar cube, sorry, I haven't got a sugar cube, but it's about this much, and you dilute that volume into the size of 11,000 Wembley stadiums, give it a good stir, and then take out a couple of hundred mils, we can still find it. So this is sort of what makes us stand out, really. So this is how we can find new molecules, and we recently found a new CFC in the atmosphere, this molecule, and reconstructed its atmospheric history. So this is sort of time. This is from the Australian Air Archive, or Tasmanian, that starts in 1978. And you can see its concentrations have been increasing all the time. The dashed lines is basically a reconstruction from Fern air, which follows quite closely. Which was quite surprising, because CFCs have been controlled quite successfully, apart from this one. It turns out we thought this must be illegal in the first place. It turns out it doesn't have to be, because the reporting to the treaty does not have to include any substances released or produced or emitted in the production of other chemicals. And someone seems to have quite a leaky factory there, because the red line on the right-hand y-axis is the emissions. You can see this, these sort of soar up to 2,000 tons per year in 2012. It's quite a decent amount to be leaky, especially if you actually want to make something else.
It started leaking recently. Is that in 2010 or whatever?
Well, we were quite puzzled. It sort of went up slowly, and then sort of 2010 is actually the year which was the total phase down of CFCs. So total production in the world should have ceased at this point.
It implies it might be correlated though, there's some change in industrial processes as the CFCs were completed.
Yeah, well, it is. We know of several chemicals which actually are being still produced quite a lot, which use this CFCs in their
Maybe that was
production.
when they were finally getting rid of all these old fridges.
Well, we see quite large amounts coming out of China. So, yeah, it could be old fridges, but it's more likely sort of fresh production.
It seems a lot worse in the period where we're meant to be looking after it all. It's scary. It's just massively gone through the roof.
Well, to be honest, this is quite a low mixing ratio. So the other CFCs are in the tens to hundreds of ppT. So this is an early warning, essentially, which is good, because we didn't have an early warning the last time with the CFCs. But it's not sort of a big threat yet, as of yet. So we got quite a bit of press coverage with that, got into the Wall Street Journal. And unfortunately, as the news spread around the web, they got slightly out of hand. So we can't really do anything about that. And then a second example, basically, of reconstructed histories is PFCs, perfluorocarbons. It's quite simple molecules, just carbon and fluorine. They don't deplete ozone at all, but they are very strong greenhouse gases. And once released into the atmosphere, they're like a permanent addition. So there's almost no breakdown processes. Most of the actual breakdown processes are in the upper mesosphere, so the range 60 kilometers and up. There's not a lot of air that gets up there. And then before 2012, there were 4 PFCs known to be in the atmosphere, and we added another 4, found another 4. So these 4, essentially, they've got a variety of uses. The lower 2 especially are used as heat transfer fluids, so if you want to make a main board or a chip, and you burn into material, you have to transport the heat away very quickly to neatly burn. And you have to have something that doesn't break down in the process, and these are sort of ideal for that. So, and these are the atmospheric histories from Tasmania, going back to 1978. You can see that there was very low concentration there, and they all have been going up. They're still increasing. There has been a recent slowdown in the increase for actually 3 of them. And that's actually because industry is making an effort trying to not release those to the atmosphere, because once released, there's no way back really. And then you might think, if these were tiny concentrations again, but because they are such good greenhouse gases, this sort of, if you calculate the equivalent of the CO2 released into the atmosphere, you end up with several 100 million tons of CO2 equivalent released into the atmosphere irreversibly, which is not what we want really. And then finally going back to the stratosphere, so it's basically the region between roughly 10 and roughly 50 kilometers, although this is not quite accurate. The stratosphere is actually, the tropicals is actually lower down in higher latitudes and higher up in the tropics. So it can be as high as 19 kilometers in the tropics, and can be below 10 kilometers, or sort of 8 in the high latitudes. So what you have in the stratosphere is you've got the ozone layer, as you can see here. And because of the ozone, basically you've got this turnaround in temperature. So as you go up, temperature goes down, but once you're in the stratosphere, the temperature is increasing with altitude, which is how the stratosphere is defined. And then basically we release lots of CFCs and other ozone-depleting substances, and then because of that we know we have depleted the ozone layer, and that has led to a cooling of the stratosphere in the last few decades. And in return, this actually has had quite a few impacts on global climate. So we know, for instance, that the ozone layer has changed the location of the jet stream in the southern hemisphere, so it's actually moved. And because of that, the whole precipitation has shifted, rain, and it has even affected ocean circulation, especially in the Southern Ocean. What we don't know is actually how this has in turn, apart from ozone and temperature, changed the circulation and the chemistry in the stratosphere. So the stratosphere is actually not very well known. It's, NASA also call it the ignorosphere. And then this is a quick glimpse on stratosphere overturning circulation. So what you typically get is you get upwelling air in the tropics, and then it turns over into the extratropics and towards the poles, and then descending again. And you typically get in polar winter, you get like a vortex where air is coming down again. That's the overturning circulation, and you can use this to you can use trace gases to track the circulation if they don't break down. I'll tell you a little bit more in a minute. So if there's an inert trace gas that doesn't break down at all, such as a PFC, basically the air takes several years to get from here to here. So what you might not be aware of is every time you launch a balloon to 30 kilometers, or 25 even, you go several years back in time, because there's like this is a very, very slow vertical movement of the air. So what we call that is the stratosphere residence time. We call it the age of the air. And we're going to investigate multiple traces, inert ones and non-inert ones, such as the CFCs. And so we can track the large-scale mixing with inert ones, and the non-inert ones tell us something about the changes in the chemistry, because it will make a difference, because they break down at different altitudes. So if air comes in here and moves sideways here to arrive, say, here, you'll get a different content of this CFC as if it goes up here and then here. That's what we're going to do. And one example for an inert gas is SF6 or sulfur hexafluoride, which makes your voice go very deep if you inhale it, as opposed to helium, which is what it's most well known for. And we've got like an atmospheric history of it, which is this from various observations. So you can see it's increasing all the time. What we find in the stratosphere, basically, if this is plotted against altitudes, the higher you get, the less SF6 you find. It's basically going back on this trend. So this is in 2010. So this is going back from here to several years. And because we know the history so well, you can actually find out how many years we've gone back. So it's like get back up to 5 years in time from 2010, and that basically gives us our, if we plot that against the CFC, so the age of the air, the older the air, the less CFC there is, because it does break down. That's what we do. And it looks really bad, much worse than on my laptop. So the plan, basically, or the problem, is that the observations from aircraft, from large balloons and from satellites are very expensive. So typically we're talking about research aircraft on the order of £10,000 per flight hour. Large balloons are at least £100,000 per launch. And satellites, well, you're straight into the millions there. The other problem is observations are quite sparse. So you get an aircraft campaign, for instance, with the former Russian spy plane. There was a planned air campaign earlier this year from northern Sweden, and they got slightly delayed because the scientific instruments weren't working very well. And there was basically the Swedish Defence Ministry. The army had a big planned exercise. Thank you. So they chucked the Russians out of the country, and there was no campaign at all. Which was and about 100 European scientists, which was pretty bad. And now we just had a campaign in southern Greece, which actually worked quite well. We had 3 flights at least, and the 4th flight, the whole site got flooded by heavy rain. Several people died, cars got washed into the sea, and campaigns cancelled. Or the rest of the campaign, at least we got 3 flights. And yeah, so a lot came wrong with those big campaigns. So the solution is air cores, essentially. So NOAA invented this technique. They measured the more abundant trace gases successfully. So carbon dioxide and methane. What it is it looks quite simple. So you've got your hab, and you've got like a piece of tubing, 100 meters long typically, empty and open on one end. And basically what happens is it goes up on the balloon and empties out because the pressure in 30 kilometers is fairly low. And then the balloon gets cut off and comes back down again. And this then collects air as it comes down, floats back up again, and collects a vertical profile of the atmosphere. So you can get stratospheric air that way. And because it's such a long, thin tube, diffusion is quite limited. So if you're quick in analyzing this air, you still get the vertical profile. It will eventually mix after, or it starts really mixing after one day, but if you get to it within a few hours, you're fine. So this is obviously very, very lightweight and only costs a lot less per launch than aircraft. It's for a 45-hour flight, and can actually reach 10 kilometers higher than aircraft. The 90% recovery, well, that's for the US. It's probably not true for the UK. From what I've heard here today, recovery rates tend to be limited by the North Sea.
You shouldn't lose one if you do the prediction.
Yes, we'll try. we'll certainly try. Yeah, and then we've got this big instrument and the atmospheric records that can basically get us more than 30 trace gases in those air cores. And we've planned 45 flights in the next 3 years, starting early next year. On a cycle like each season at least twice. That's the plan. And then this is the bit, but the technical details. So the planned payload will have some super thin-walled stainless steel tubing. So like a 10th of a millimeter, is like paper thin. You need to be very careful to touch it because it just breaks. But that's sort of the weight limiting factor, because all of this, the valves and this, end up to 3.5 kilograms. So we want to stay below 4 kilograms, because that's the idea. And then the electronics, we mainly followed UCAS recommendations so far as we got. Yes, we'd be very happy to take advice on that, to be honest. Before we buy some more parts, and bought a Cartier or power source for board. And we haven't actually thought too much about other sensors on the payload. We still have a few grams to play with probably, but we definitely want to go for ozone and temperature and pressure, sort of, to get some altitude lock on. And for the ground tracking, we will go with the dog collar thing, which is basically what the Americans do. Because we need to not just recover the payload, we need to recover it as fast as possible. Yes.
Where would you be looking to launch it from?
Well, initially we thought Ellsworth would be good, but Ellsworth or Cambridge, but it looks like the Welsh border might be more feasible.
I was thinking it's a lot further away from the North Sea.
Yes. Well, the additional problem that we have with the balloons is the problem you get with the long piece of tubing is if we're interested in a top bit where it's falling very fast. Now, if you have 100-meter empty tubing, the air that you get in there is not the same as the air outside. So the temperature and pressure reading outside will not tell us what air is coming in currently. Yeah. So we wanted the first bit to be particularly slow. So we're probably going to go for a 2-balloon technique. So only cutting off one balloon, floating for a while, and then cutting off the second. But that complicates the staying on the island problem.
Do you mean 2 balloons, one that doesn't have sufficient lift? So
yes, exactly. One that makes it go down slowly.
Yeah, got it.
A balloon. I think technically it's a balloon, isn't it?
A what?
Balloon parachute.
I think a balloon floating with air is floating with ram air, so I'm not sure.
We will also have a parachute then because from I think below 20 kilometers maybe or 15. We might be able to use the parachute instead. Because we want to, if we keep the balloon on, it'll definitely go to Europe.
Could you use a release valve to give you your negative buoyancy?
It's an option there. We haven't decided on whether we go for the 2-balloon technique or the
It's more
release.
complex than 2 balloons. 2 balloons seems the simplest way to get negative buoyancy.
Yeah.
You can measure out exactly the amount of lift the second balloon will give you on the ground.
Yeah.
Cut it away, cut the first balloon away.
There are some dangers with valves, because it gets quite cold up there.
And just getting the gas out is quite difficult, because it's not an awful lot. It's not a huge amount of pressure inside. It's it's very undense. It's very.
So it'll slow down as it's coming down, essentially.
Well, yeah, I don't think there's a problem with it. Maybe trying to force air into it, but just getting it out quickly through that small neck is quite difficult. And I've tried some balloons with a release valve, and you need a fairly big hole to get gas out in speed.
Okay, 2 balloons it is. I think that's it, to be honest. Oh, I know, there's one more bit, sorry. Despite us having not launched a single balloon, we've got some results. because the Finnish Met Office has launched the balloons, and basically their analysis technique leaves the air unaffected, so they basically run through the analyzer and sample out the other end. And they send that to us, and this is sort of, for Finland, this is as good as a landing ever gets, I think. There's quite a lot of forest. I mean, you've seen some photographs from northern Finland, and a lot of lakes. So they had several lake landings already. And this is sort of the profile to get. So in red and blue, and basically we have to plot it against the CFC as our altitude, because we haven't got final altitudes from the Finnish yet. So you can see grey is what we got from a former aircraft companion, and red is what we got, and blue is what we got from the air core. So the blue one still had some problems. We had some, there are some small leaks in there. That was all fixed. You can see it fits quite well. And this one only appears to not fit well, but this aircraft companion is from 2010. These two gases haven't changed much in the atmosphere since 2010. This one has, it's increased. So we only expect the gradient to be similar, not the actual concentration. So it is. Apart from the two uppermost samples, which basically, because you still have a tiny amount of fill air left in your air core at 10 or 20 millibars, this is probably what it is. So that's zero gas.
Your sampling tube, did you say it was 100 metres?
Ours will be 130 metres long, yes.
Will you be uncoiling that in air? Or
no, we're not uncoiling it. We're setting it up coiled. Absolutely, yeah, it's like a coil.
Right, so these staying as a coil just filled over time?
Yeah.
Right. So launching of 130
No, that would be, oh no, with this paper thin stainless steel, it would rupture.
Whereabouts is your analysis?
Pardon?
Whereabouts is your analysis machine?
In Norwich. In Norwich.
In Norwich.
Yes.
So if you ideally want to get it a few hours, you want to be launching somewhere where you can collect it quite close.
The closer the better, but we will have a technique to basically push the contents of the coil over in a sampler, so get like segments, and that will help, because the mass spectrometer itself is not very fast. Yeah, we'll probably need several days to analyze one of our air cores. I think that's it now, hopefully. Yes. Thank you.
So, should we have another one or a break, guys? Which do you want? Anybody want? Who wants a break? Hands up. Oh, Sean. So, it must be Mark. Mark B. It's on the stick.
So I'm conscious of the fact that I'm now standing between you and a cup of tea, so I promise to make it pleasant as possible, and also I promise to keep the maths out of it, which is great for me as well.
Could you put the mic up a little higher, please? No.
No, it's one of those.
How's that done, right?
Yeah, it's better. Right, thank you.
We're looking for nothing there. It's in here, isn't it? What's it called?
Radar points. I'll get my laptop and we'll speak to you now.
So that. I could have sworn I put it on here. Let me just quickly look on here. If it's anywhere, it's in the. No, it is on here. I'll just put it on something. Yes. Well, the other thing Oh,
that's the one.
That's the one there. It's a proper PowerPoint, it's on the Mac.
So back in the guy's shop now. Right. Yeah, I saw it.
Hey, thanks a lot. You actually get go forward and back with the
Okay, good afternoon, ladies and gentlemen. We good to go? Yeah, brilliant, thank you. By way of a quick introduction, my name is Mark Bassford, and I would like to start off by saying a couple of quick thank yous if I may. First of all, to Anthony for the excellent tutorial, because without that, I would not have got the chance to be able to do what I'm going to be talking about here today. And in particular to Steve, again, without your assistance and support, then I guess this would not have been more than a conversation in the office. So thank you both very much, and also to the rest of the community.
You're on mute, Mark, or is that, because I can't hear you through the...
Okay.
I can hear you.
Can you?
Yeah.
I said thank you.
You don't want to? Excellent. Don't worry. It's working, it's fine.
Are we good?
Yeah.
Okay, right. So the presentation is going to be in two halves. First of all, a little bit of theory, a little bit of background to what this is all about, and then I'll get into the detail of what was actually a concept demonstrator. So just to explain what's meant by the title there, when I'm talking about radars, I'm talking about radars where the information is used for providing advice or control to aircraft, to managing the airspace, and the reflector carried by HAB. I've subsequently found out this is not a new idea. There are patents close to this out there already. What we did do is we did do a concept demonstrator. A little bit of background. Just a bit of history. Winding back a couple of years, my son is very much into electronics. Was surfing the internet one day and said, "Hey, Dad, I found this great website. We're putting up balloons, build trackers, chase all this kind of stuff." I was thinking, "Yeah, that's great. Wow." Didn't actually take it much further than that. But went to work, and the department I was working at the time had responsibility for radars and also radar assurance. And the way we assured radars in our organisation was to use aircraft for flight check-in. We were having some pretty tough challenges to the point where we went back to a whiteboard moment and sort of said, right, what is it we're trying to do? What's the best way to measure how a radar performs? And from that stemmed the idea of, well, instead of using an aircraft, and I'll talk a little bit more detail about that in a moment, why not just put a radar reflector onto a balloon with a tracker and take our measurements that way. So after that conversation in the office, I went back home, went back to my son, and I said, "Michael, can you show me that website again?" And things kind of like spiraled from there. Oh, by the way, I'm quite happy to take questions at any time, so if you want to sort of shout out your hands up, please don't feel the need to wait to the end. So there's a quick overview of what I'm going to go through just now. So I'm going to start off with a quick radar in 30 seconds. The top diagram there is reference to primary surveillance radar, PSR, and that is radar in the simplest form, if you like. A transmitter will transmit a pulse of RF energy, and it will be reflected from a target, and doing speed distance time calculations and also position of where the antenna is. You can get range and bearing information from it. There are two families of primary surveillance radars, 2D radars. They will just give you the range and bearing information. You also can get 3D radars where they'll give you range, bearing and height information. The second one below the middle, sorry, wrong button. The one below it, the SSR, secondary surveillance radar, is it's slightly more. So it transmits RF energy, but it transmits a message. It could be a broadcast, or it could be specific. And what you need is a cooperative aircraft, an aircraft fitted with a transponder, receives a signal, processes it, and then transmits a message back. So it actually transmits data back to the receiver. It's great, it's more modern, and it gives you a whole load more information. And it's information from that that's used on, you see on pictures of air traffic controllers, and there's tallies over a target, and it gives you, height, call signs, and all that kind of stuff. That sort of information is gathered from secondary surveillance radar. For the purposes of this brief, this is going to be just about PSR, primary surveillance radars. The secondary surveillance radar work is kind of work in progress. All right, so today is just going to be about PSRs. What is it we need from our radars then? So some key points, and this is not exhaustive. This is just some points that I've put down to discuss today. Reliability in terms of when a radar is sweeping a bit of airspace, you want to be sure, as much as you can, that it's actually going to see something that's out there. Now, there may well be instances where there's an aircraft and for whatever reason there hasn't been sufficient energy to actually initiate a response. But you want it to be as reliable as it possibly can in terms of being able to see something that's out there. Moving down to frequency. So what do we mean by frequency? If you're looking at a piece of congested airspace, you want to make sure that nothing's hitting each other and aircraft are being flown safely. You want to have an update of sufficient frequency that it allows you to manage congested airspace. So typically, if you're flying aircraft no closer than 3 nautical miles, you would want a radar that gives you an update every 6 seconds, for example. Okay. If you're looking at en route, aircraft flying over the Atlantic, for example, where it's not quite so congested, aircraft are flying further apart, let's say 5 miles, 10 miles apart, then it's possible to tolerate a slightly reduced frequency, so once every 10 seconds or longer. And accuracy. This is a key point, and this is relevant to the presentation today, is accuracy. So when the air traffic controller is looking at the screen, she wants to be able to know that aircraft is actually where the screen is saying he is, rather than it being like half a mile in that direction, another aircraft being half a mile in that direction. So I'm just going to make one more point, that linking accuracy with reliability, there are instances where there will be a no return from an aircraft. So an air traffic controller will see a dot on the screen, and then for whatever reason, the next sweep it doesn't see it. If you imagine that there are errors in there anyway, after 2 or 3 sweeps without seeing an aircraft, the air traffic controller knows is there, then there's a risk. Well, where is it? Has it turned? Has it gone down? Has it gone up? So that's one reason why we want to make sure that our radars are accurate. So the information's there when they see it, and when it's not there, it's kind of predictable where the aircraft is. How accurate do they need to be? Well, I promise you I won't go into sums and numbers, but I've just cut and paste some figures from the Eurocontrol standards. So you can see, we're talking of the orders of fractions of a degree, hundreds of meters, fraction of less than 1 nautical mile in terms of accuracy.
Have these parameters changed at all since the disappearance of the Malaysian flight NH370? The one that was somewhere in the Indian Ocean?
So not to my knowledge, okay? Now, let me explain the job. This is in relation to a job I was doing a couple of years ago. I'm now in a different employment. So if there have been any changes to Eurocontrol standards, it's not something I'm aware of. These standards were written and published in 1997. Now, when I was doing this work a couple of years ago, I did say, well, 1997, that's like years ago. Are they still extant? And it happened that the editor, or one of the editors in Eurocontrol 0147, was one of the guys who was involved in producing the 1997 standards. And I was informed then that yes, those were extant a couple of years ago. But have they changed as a result of the flight that you're talking about there? I don't know. Okay, so moving on. Yeah, and that kind of reinforces the point again. So what we've looked at here is there's a Virgin 747, I think that is. Say again?
Not a 747.
It's a what?
37 maybe.
You got me nervous now.
Just a quickie. I guess when you're looking at en route, because you're looking at a longer, larger distance, then will you not be rotating your antenna, slower anyway, so that because the return signal is going to take longer?
Okay. Yeah, absolutely right. So I'll answer that with two bits, if I may.
Yeah.
So we talk about en route services. So aircraft that are many hundreds of miles away. There will almost certainly be areas where there aren't no coverage, because if you want in a radar to see 500 miles, for example, then its rotation rate is going to be really, really slow. And do we need to? Well, you could argue the point that maybe we do. But the point that was being made there was if for an aircraft to look further away, then bear in mind it's all done with speed distance time. If you transmit a pulse, you've still got to wait for it to come back and then do the processing. So you can't have a refresh rate of 6 seconds and then expect the radar to see the kind of volume of airspace that would cover a 400-mile range, for example. That's enormous. So there are constraints from just physics and RF propagation. So answer your question.
Yes, cool.
So this is just a build-up of what I've been talking about the last couple of moments. So on the first sweep, the air traffic controller sees the aircraft on the left. She knows it's there. The second sweep, it got a return from the aircraft. They know it's in that second position. The third sweep, there was no return from the aircraft. It could be just from clutter or obscuration or whatever. But we know that the aircraft's going to be somewhere in that circle. The next one, the fourth diagram along, again, no return, but you know the aircraft, the likelihood is going to be in that bubble, but that bubble gets bigger and bigger and bigger. That is a problem where you've got two aircraft, and that bubble, those bubbles are now represented with that red and blue square. Those bubbles grow bigger and bigger until that point where you cannot be sure that those aircraft are not flying together. All right, I think I've made the point enough there. So just to come back to the concept demonstrator that we had, we had their responsibility for measuring radar performance. But there are a number of ways of doing it. You can use radar target generators, which is a receiver, a processor, and a transmitter. You put it in a field on a mast, a mile away, half a mile away, whatever. Expensive piece of equipment. You need a lot of training to be able to use it. And essentially, it receives the radar pulse, it processes it, and it transmits a pulse back. Now, it can do other things. It can add a delay to simulate a target that's further away, and it can also attenuate the return signal so it can simulate a smaller return. So that's one way of doing it, but again, there are limitations in terms of cost, and you're only measuring the lower part of the radar beam. There are other ways that you can do it as well, using markers at the end of the runway. For air traffic controllers who want to talk an aircraft down using radar data, an essential element is to have a marker at the end of the runway, and then on the screen, the air traffic controller can see, well, actually the radar is seeing the end of the runway where I think it is. So that's all part of the assurance process. I mentioned flight checking. That was our preferred system of providing performance assurance. What we have is an aircraft with an accurate GPS fitted, but some of the problems associated with that are, you might not be able to fly because aircrew sickness. Again, it's not cheap. Johanna's mentioned some of the costs. I think they're a rough order about £10,000 an hour, £50,000 for flights. That's kind of ballpark of what our costs were as well. So you can imagine, it's a lot of money for doing flight checking. You're doing lots of these flight checks on different radars all the time. And I also like to pick up on a word that the lady up on the left mentioned earlier on, I think during the presentation, about repeatability. One of the problems we've got, I say one of the problems, one of the things to consider with an aircraft when it's reflecting RF energy, is the radar seeing the end, the nose of the aircraft? Is it seeing the tip of the wing? Is it seeing the tail? What part of the aircraft is that RF energy coming back from? So one good having an accurate GPS, but if you've got an aircraft 10, 15, 20 metres across, and we've seen some of the tolerances that we're expecting our radars to perform to, it all adds to that measurement uncertainty. So to reflect back to that whiteboard moment, well, how else can we do it? Well, we can put an optimised reflector on a hab, measure it, and then compare what the radar sees with what the balloon, or the flight from the balloon flight, the data from the balloon flight. Has it been done before? Well, balloons have taken up targets for many years. I think the one on the left, if I recall right, was because there was a mandatory requirement to fit a reflector for some reason. The image in the middle is taken from what I recall was being a Met Office release in the 60s, and that was a way that they tracked the Met balloons back then, or one of the ways they tracked them was with a radar reflector. And the image on the right is taken from a calibration using an aluminium sphere suspended from a balloon tethered, measuring performance on the NEXRAD weather radar, next generation radar. So similar stuff has been done before. Okay, so what were we trying to do? We were trying to A, think of ways to reduce costs, B, ways to reduce measurement uncertainty, C, two reasons is good enough, but the rest will come to me. Hopefully in questions in due course. And I'm thinking about that cup of tea as well. All right, so the way ahead for us then was to build a tracker and logger. And if you want to ask questions about that in due course, I'll explain why I went for a logger as well, but I'm trying to keep it pacey. And also to build a reflector. So you'll recognise there two Atmel 328 microcontrollers, fairly standard stuff to most, if not everybody here. And some fairly rudimentary calibration. So there's Shay Mark on the right there. So I'll put the tracker in the window just to see how accurate it was, to get some rough order figures. And over a couple of hours, took 12,000 plots. So for the altitude out, I've got a mean value of 17.1, and from Google I've got 17, so that's not bad, with one standard deviation of 7 meters. So the variance isn't that bad, for a GPS.
What mode was the GPS in?
Say again?
What mode was the GPS?
That was an airborne. There are limitations with this. This is calibration with a small c. So this is like in my front window, partial obscuration.
I was thinking, obviously with your radar, you're probably not interested in anything over what altitude?
So yeah, so there are limits to.
No, what is the sort of the maximum altitude you're interested in?
Right. So what's the maximum altitude I'm interested in? I'll avoid answering that for the reason that what I want to do is to be able to fly through the upper beam and then back down again.
Right.
Because at the moment, with flight checking, we just measure on axial.
It figures if you're in flight mode, then you'll get the altitude.
Yeah.
Otherwise, you lose it at 12 kilometres.
Yeah.
On the other hand, it's coarser.
I wasn't aware of that, but thank you very much. Yeah.
So pedestrian mode, you would probably have got it a lot tighter on the ground.
Yeah.
I may be wrong.
Thank you.
Yeah, that's because I think that's because it assumes it's on the ground, doesn't it?
Yeah.
So you've got vertical error as well.
Yeah. But I take your point, and thank you very much for that. That's something that I'll consider. Again, something else, another criticism of this, as I say, it's calibration with a small c, is the fact that this is being stationary for several hours. It's not mobile either. But again, it's useful for rough order calculations. And you can see on the right, or the middle on the right there, what I've done is just clamped the height information down to ground level, so I could look on the top and just get a rough order of where all those plots are. And again, one standard deviation of something like 5 or 6 meters. So, at least I have got a ballpark appreciation of how accurate the balloon information is going to be. Okay, to come back to reflectivity now, and this is some of the background to the design of the reflector that we used. So looking at the image on the left there of the aircraft, you can see that RF energy is reflected in a number of different ways. From the tip of the nose, it's diffracted, provided it's a reflective surface. It could be from the wing. Bear in mind you've got the main spars at the leading edge of wings. There's something called creep around, where lower frequencies, higher frequencies, thank you. High frequencies, the RF energy actually, if you've got a cylinder of an aircraft, the RF will pass around and then come back out. And that's important because there are ratios of the target size to frequency that creep around merges constructively and or destructively with the reflective energy and can either give you an increased response or a reduced response. But I'll come on to that in just a second. The image in the middle is useful in as far as it's a polar diagram of the reflectivity of an aircraft to illustrate that it's not a nice, easy reflective surface all the way around. There are peaks and knolls as you go around it. It's like a three-dimensional hedgehog in space. And the image on the right is from a manufacturer's website, a manufacturer that makes corner reflectors used for sailing. And again, it's a polar diagram of the reflectivity. But what you can see there is there are peaks and knolls. So it's not a nice, smooth, reflective surface. So we decided to optimize it to reduce errors as far as we could by building a spherical reflector. That's not the actual one we did, but it does illustrate the point of why we chose it. I think it's Merrill Skolnick in his book Radar Principles, who refers to an idealized spherical reflector being like a ball, taking a flash photograph of a ball bearing. If you take no matter what orientation the ball bearing is in, if you take a flash photograph, you will always see the flash coming back from the center of the target. So that's why we chose a spherical reflector. The graph to the right, I'll keep away from numbers, but the x-axis along the bottom is a ratio of wavelength to diameter, and the y-axis is a ratio of sigma, which is your radar cross-section, to diameter as well. The region on the left, the Rayleigh region, is if you're using a small reflector and large wavelength, you won't get a lot of reflected energy. If your reflector is relatively large and your frequency high, so a shorter wavelength, you'll get quite a lot of reflected energy, or is referred to as the optical region. But in the middle, you get that combination of destructive and destructive interference from creep around and mirror.
Sorry to interject.
No, please.
Doesn't that graph apply for scattering objects? I mean, if you go into the optical region there, you've got a scattering cross-section that's equal to the projected area of the object, which would be true if we go to the optical regime. It would be true if it was a white scattering object, but not if it was a metallic sphere, like you see on the left there. The metallic sphere is almost completely black because it's only scattering from the illumination source.
From that point?
Yeah, because that's not a scattering reflector, it's just a metallic reflector.
Okay, so the background to this is we were trying to, so ideally what we would want is a 1 meter plate, reflective plate.
That's angled straight back at the radar.
Correct, but as we know, you would never be able to control that to the way that we want. So this was an attempt for us to normalise a spherical target to what we were trying to get to use calculations. In terms of the point you're trying to make, if I'm honest, I would need to mull over my answer. I'm quite happy to go over it over a cup of tea, if you wouldn't mind, but I'm trying to keep on my train of thought here as well.
So in actual fact, that a corner cube reflector would sort of maximise the return but be very notchy. This would sort of give you a lesser return but a more consistent model.
Correct, yeah. So again, to use the word that was used in an earlier presentation, the repeatability of the measurement device, measurement system, rather than the problems that you've got with using an aircraft with its inconsistent reflectivity. But can you hold on to that, Lawrence?
I think I might know the answer, which is they're operating it around a circumference of the order of one wavelength. Is that true?
Well, ideally one wavelength, multiples of, or certainly where there is a large difference. So if you've got a large circumference, but a very small wavelength, then the effects, as you can see, do diminish.
Yeah.
Yes, no?
Well, I would say maybe 1-2 wavelengths, well, in 1-2-3 wavelength region, then...
So this bit here?
Yeah, that bit here, then the effect I was talking about, it doesn't really apply. Once you start moving further to the right, then the actual details of the surface reflective, the diffuse reflectivity starts to come more into question.
So hold that thought.
Yeah.
When we did the calculations, the region we were working in is around here.
Okay, yes.
But we'll talk about it.
Yeah.
Cool. So thank you. So building a reflector then. We had a few attempts. There have been a few flights. So this really is sort of garage man den stuff. So I needed to keep the costs down, make it right. We started off. It just so happens that an exercise ball from Argos, I'm sure there are other suppliers, costing about £5, was a good template to build this around. We used papier-mâché, cooking foil, cut it around east-west, lifted the parts apart, took the ball out, put it back together again, make sure there's electrical continuity all the way around, and use that for the first reflector that we built.
Was it away?
Say again?
Was it away?
So the reflector weighs something like 400 grams. So all in with the tracker, Mark 1, it was something of the order of 1,200 grams. And that was a problem. Again, we can talk at length about other things that I considered, including fabrics from balloon manufacturers and thermal insulating blankets and that sort of stuff. But moving on. So after the first flight, we decided to go about it a slightly different way. We built a plaster of Paris mould, which is the image in the bottom left. And then what we did there was we plaster of Paris mould, put baking foil on the inside, and then with a fiberglass kit from Halfords, I'm sure there are others available, we added some mechanical rigidity, put in a disc of fiberglass in the bottom for mechanical strength for the strings to go through, and also some strips around the outside where we're joining the two halves. And you can get a that's a 12-inch steel rule, so you get some sort of idea from the dimensions from that. Okay, so we built the tracker, we've tested it, it works. We built the reflector, we've done some, drawn some graphs with Mars bars and kind of like, yeah, it should work, whatever. But it gets to a point where you want to fly it. So just out of interest for a bit of fun, who thinks the first one worked? One of you. Well, that's good. That's two. Thank you for the confidence. I appreciate that. All right. You're all right. It did work to a point, and it didn't work. So the image in the top left is the planned flight path. The image in the middle and the bottom is the actual one. The flight lasted about 20 minutes. You can see in the bottom left there the launch, the actual thing going. You can see the reflector right in the bottom with the tracker, with the transmitter below it. The GPS antenna was actually on top of the reflector, so it wasn't obscured. But the giveaway there is if you look at there, you see a bit of blurring on the screen. All right, that's a raindrop. All right, papier-mâché. All right, you're getting there. All right. So the LIs from that are avoid stuff that's going to absorb moisture as it flies up through clouds and rain. Hence why we went to the fiberglass option thereafter. So I think the rest of the images are fairly self-explanatory. Don't need me to sort of waffle anymore. Okay, so this was the second flight. Some of you may recognise the Ellsworth site there. So the predictor this time top map and the actual flight path on the bottom there. So you can see, well, actually it took off and landed pretty much where we thought it was going to land. Anything to take away from this? No, there's no further points to make.
A tree.
Say again?
Didn't land in a tree.
It didn't, no. There is a story to the landing, but I'll not hold you up for a cup of tea now, but I'm quite happy to. I will happily talk about meeting Ewan and Stu in a few moments, but that was a really nice experience. Okay, so it did work in terms of, it flew, we got telemetry from it, we got the onboard data, and I will just say, well, I put a logger on there as well. We used the 50 board RTTY, right? In order to have strong statistical standing, I wanted as many plots as I possibly could, using a minimum sentence of call sign, time, that long out, and checksum. It was taking about 10-11 seconds per sentence. With an onboard logger, I was getting a plot every second. So to do the statistical analysis, if I have that 10 times as many plots, it gives it greater standing. So that's why I have the onboard logger as well. Okay, so we know that the tracker and the logger work, and it flies, and it doesn't absorb moisture on this flight. Did it work? Okay, just out of interest, who thinks it actually worked this time? Oh, it's a bit more confidence. Oh, that's good. Thank you. Yes. Okay. The news is it does work. So that is a slightly distorted because it's a screenshot from a different computer, and it had to be stretched slightly to match the sizes of the presentation. But what you can see is there is a correlation between what the radar saw and what from the space near image as well. We did do some statistical analysis with the data that we got, and we found that using the M3003 standards, and I'll just refer to my notes what that actually is. It is the expression of uncertainty and confidence in measurements. So there is a standard M3003 which we refer to, and when doing the calculations comparing the data provided by the flight checking aircraft to our system, we actually found it was very comparable in terms of reliability and measurement confidence. The key difference being on an aircraft, as I've said, you've got at what point of that aircraft is the reflecting engine coming from, albeit an accurate GPS, whereas with ours, you've got an optimized reflective surface with the GPS antenna literally centimeters from the center of it. So it was helpful in that. It is helpful in that regard.
For which frequency was the reflector made?
So it wasn't optimal. Bearing in mind that what I didn't have was a sphere of precisely the right dimensions that I needed in order to be able to make it. So the exercise ball is 65 centimeters in diameter, which, and I forget the precise radar frequency off the top of my head, but it was between 1 and 2 gigahertz.
L-band?
Sorry?
L-band? Be about 1400 megs?
Yes.
Airfield radar, Washington type stuff. Target, yeah, 3 gigs, 3.2.
Yeah. So low gigahertz.
So you can even put do it a bit smaller.
Yes. Now to go back to the graph where I need to kind of mold my answer for a lot later. Yes. Now you could predict it. Now I'll go back to the particular slide in due course. But you saw how it went into constructive and destructive interference. You could, if you wanted to fly against a single frequency, you could reduce the size to get it to unity as far left as possible, and then reduce the actual reflector size quite nicely. Or even go further down, but just reduce your probability of detection range from what might be 100 miles down to 60 miles. So, yeah. Does that answer your question?
Yeah.
Cool. Okay, observations then. We've already touched on the fact that there are other measurement systems out there, but doing it this way is significantly cheaper. Requires a different way of use of training. You're not training pilots and people to do fly aircraft and stuff. Again, thinking the environment can be reused if recovered. I've got stories about losing stuff in the sea, but I'll bore people with that later on. Potentially more accurate. Certainly, in fact, there's an error on there. It's not MS3003, it's M3003. It's certainly with the rather rudimentary concept demonstration we did, it was comparable to the systems we're currently using. And the bottom point there, on the fact that it travels from ground level to above beam limit allows us to sort of see where the limit of coverage is before it comes down again, rather than using the traditional method of flying aircraft on radials to and from the origin, or circular flights. Notes, I've already spoken about calibration with a small c, and also the precise reflectivity of what we built. We were constrained by what was available and costs and so on. What we haven't done is put it into a anechoic chamber and measure precisely how reflective is it. Crumpled baking foil, is that a good reflector or not? I don't know, but we've got evidence that it does work. Ladies and gentlemen, that concludes what I was going to say today. Are there any questions?
Yeah. Dave will be able to answer the question. At the moment, you're using 50 baud radio teletype.
Yep.
If you're using LoRa, question is, would you perhaps get the rate that you wanted and save yourself the expense, perhaps, of bothering to go and recover?
That is
yes, quite easily.
That is a very good question, and one of my motivations for coming here today was I know nothing about LoRa, and I was making notes from what you were saying earlier, Dave.
You can easily do 1 hertz.
Okay.
What you want to get the effort involved in making that payload up is far more worthwhile to effective than I could get £7 at tracking and just chuck them out and not worry about them, but you've invested probably £100.
Oh yeah, and so again, my motivations for doing this were manifold. It was a nice project with my son. I wanted to learn about stuff as well. I still need to learn a whole load about writing script. So there were personal motivations for doing this as well. But you're right.
You can do 18 samples a second as well on the GPS chip by setting the parameters.
Okay.
You can log at 18.
Okay. Again, I'm still working my way around U-blocks and U-center and stuff. So, but thank you. So there's a question about that.
I was going to say as well, you can up the sample rate on U-blocks to 18. 18. Yeah.
Okay. Thank you.
So it's like a lot more samples.
Thank you.
Which outdoes LoRa, so then you can't get to LoRa. So then you can't get 18 samples a second out.
The other thing with LoRa is you don't have to have a communications receiver.
Okay, good point. Sorry, yes.
One flight of questionable kind of track, questionable altitude, not questionable in that you don't know what it is, but you can't determine before you launch. I mean, in calibrating radars generally, there's multiple radials flown over origin to plot the dead spot on the different feed holes on the antennas and.
Yeah. So sorry. What you're saying there is with a reflector like this.
Go on. Well, how many flights would you need to calibrate say a Heathrow?
So that's a good question.
You actually calibrate something like Heathrow with that, so with all the other air traffic in the area that you've got no control over your balloon when it's launched.
So that's a good question. So I don't know if you heard over here, but the question was, how many flights would you need to do in order to be able to get sufficient evidence that the radar is
calibration on that?
The answer to that is I don't know. The answer, truly, I don't know. What you would need to do, there is still further work to do on this, of course. This is a concept demonstrator.
I mean, because in Afghanistan,
so yeah?
we're brilliant in Afghanistan where you don't want to fly straight and level for any length of time. That would be perfect.
And that's a very good point. So not only would it be useful in a threat environment where you might not get a contractor to come along and fly.
Because they don't like doing it.
Absolutely. Absolutely.
But it still has to be done.
No, I would challenge that. They don't like doing it, or they wouldn't mind doing it for the right price. But also there may well be remote locations. So in the UK, it costs 50k for doing the kind of stuff that Johannes was talking about. Let's say there are airfields in more Siberia or something like that, where it may take the contractor 2 or 3 hops to actually get there.
Yeah.
All right, so it all has costs. No, so but you're absolutely right. Certainly, the threat environment is very useful.
If you've got a Herc or something flying at a nice low level in a threat environment, then yeah, I suspect that the cost advantage of the balloon might go up.
Absolutely. And to answer the second part of the question was, how do you calibrate something like Heathrow? There are other methods and systems in place.
That wouldn't be the optimum one, I guess.
For example, you know, if you've got something like ADSB, you're getting certain information from that. Now, I'm getting lower on my level of understanding here, but I am aware that there may well be systems of continuous monitoring of radar performance using information from other systems like ADSB, where you'd get that SSR data, and if you see the SSR plot diverging from where the primary plot is, then there's an indication there in what we're closer to real time. So, but that's a good question, and the answer is I don't know, but thank you.
Yeah, I think just to answer the previous question, maybe you're talking about different types of errors. I think with this you're talking about, well, certainly on one level, you're looking at sort of systematic errors. Is a systematic error somehow creeping into the system, giving you incorrect range information out of the radar? So it's not like, oh, we have a null from our feed point at this position. That's like a different level of calibration.
Between names.
Yes. Yes.
And then another point, as far as the data rate on the downlink telemetry goes, I think you could probably pre-process the data on the balloon before it goes through the telemetry, such that you could interpolate between each piece of telemetry and get a fairly accurate idea where the balloon went from the telemetry. If you just send the raw packet every sort of 10 seconds or so, and then try to interpolate, you probably get some errors from the GPS creeping in and things. But if you run the GPS at a high sample rate, and then try to add an inertial measurement unit that would fill in the gaps and filter out the noise, well, not fill in the gaps, filter out the noise from the GPS when it's giving you those high rate fixes, and try to estimate the balloon at a sort of...
or some averaging.
Well, maybe, but the balloon is moving quite quickly as well, so you have to be careful with averaging. But if you can know where the balloon was with high accuracy at some arbitrary point, say at the beginning of each telemetry string, and you can say, or maybe the end, I don't know, probably the end, because that will be the easier to timestamp. So at the end of each telemetry string, and then you can log the time at which each telemetry string went into the log file that you're saving down on the ground, and then you can import it into, I don't know what your shape of the program is, say MATLAB or whatever, and then you can just interpolate all the points, and you can get, assuming the balloon isn't sort of shaking violently or something, it's generally moving in a more or less straight line between the 10-second points, you can get a much more accurate idea for where the balloon is over that course of time than if you're just doing simple every 10 seconds telemetry.
No, I'll take your point. Thank you, Lawrence. Thank you.
I'm going to have to move this along because we've probably got an hour now to do at best, really, 2 more presentations, and probably everybody wants a little quick break. So can we have a 10-minute break? Great, thank
All right, okay.
So the service teams that go out, you can easily flight check after the major service system.
I have to be honest with you.
Well, it's John. Yeah, John. Well, no, it's John.
Yeah.
Thank you very much for your talk. I was very happy.
Yeah.
I was here as it was, and I branded 90 SU.
Yeah. So I went out. Yeah, so it's around
Yes.
But this is the first time. Buzzing more.
Oh, no, yeah. Trying to calibrate and watch one on the roof making that deal. I think like, probably not quite got it, but certainly for a confidence check in theatre.
Well, the fact
that has been brilliant.
So the two trips that I did, first one was with flag.
Yeah.
With the white one, but they had nothing except flight controls. We were flying goalposts, bags,
all sorts.
But without any kind of assurance. If nothing else, this gives you some assurance.
I just arrived at sea shortly after there was an incident with a watch from Christina.
Yeah, it was about 90 degrees outside, wasn't it?
By the time the screen's there, don't control from it. But it gives you an additional indicator just as a confidence.
So why wasn't that in why wasn't that in 73?
They should have switched it off.
Absolutely. But there's still the same pressures.
Oh yeah, you do. And after a while in that cabin, you're looking at the screen, you start to believe everything you're seeing. It's not the ground overlays or where the mountains are in relation.
Yeah, well, the time that I was out there with three was Jeff Carter. Okay. Who's the readings? Anyway. So I was SO3 Airports. Yeah, I'm there still doing.
Right.
I got my stuff. So we had the. In fact, we did get the flight check because we had. I can see it now. He left the area to go and sell all the flat lines in the north.
Yeah, one of the pilots I used to talk to a lot is out of York or somewhere.
Yeah, that's where probably
tucked on into that airfield. Because we're responsible for all the servicing of all the radars, every time one needed a recalibration after a major service, Muggins here had to try and organise the closure of an airfield for a morning while they flew zigzags and all their radials and circuits and everything else. So it's like, goodness Christ, you want to do this where? No, we're not doing that kind of thing. You're not. It's not going out here.
That's cool.
Yeah.
Well, as soon as you started talking about
that's why I dropped that in, because I kind of figured where you come from. To look at.
Cool.
All good stuff.
Good questions, crikey.
You're in the right place though for playing this game.
Stop asking you different questions.
I think I might know the answer. That was, where did you get that image from? Was that from the
that one, no, that came from RF Cafe.
Okay, it might have been for a dielectric sphere. I'm wondering if it was a dielectric sphere.
Right.
The radars work on multiple frequencies anyway, so...
Yeah, I think I've seen it in the Merrill Stolnick radar principles.
Yeah, it's in that as well, definitely.
But I do welcome observations. Really, because this is something I believe in for reasons you've spoken about.
It has this sort of genuine... I think they ended up using a helicopter in the end, just to fly around using TACAN as well as everything, basically every nav aid you can throw at it, and fly as much as you can, record as much data as you can, and then analyse it later. So I think the guys were actually filming, camcordering the screens in the radar cabins, but there's no record facility.
That's right, because it's all video.
Yeah.
It's just not data. Yeah, that's right.
Getting the pilot to announce different waypoints and...
Yeah, but how accurate is the aircraft?
Exactly. And this is one of the, he said, well, what am I over? Right, I'm over this settlement, I'm over this, I'm over that. Get the hell out of there quickly, because it's,
It's just not good. Well, more accurate secondary radar there?
So that's a good question. That's a good question because
I'm sure they're getting smaller.
But if the message from the aircraft is its position, the question is how accurate is the aircraft's
mode S, not ADS-B.
Okay.
It also depends a bit on how accurate its response. There will be a little bit delay.
Yes, yes.
But this is maybe termed by a special document, by DO 260B maybe.
Yeah, but the Euro control standard that I showed there, that cut and paste to give you a flavour of the kind of accuracy that they're asking for, that does also articulate what's required from an SSR. They are similar, but they're not the same.
So maybe a tenth of a mile.
I think it's less than that.
It is less than that, I think.
Yeah.
Well, it can be. I mean, SSR can be.
Yeah. But again, you know, if it's less accurate than that, it's not a problem as such. It just means that the people using that information to control the airspace can't fly aircraft that close together. Instead of being a 3 mile separation, it has to be a 5 or 10 mile
generally, what you get anyway is the SSR tag on the screen, very precise, call sign, all the other bits and pieces, and then there'd be like an eyebrow across it, which would be the primary painting, which actually covers quite an area when you press into an airplane. And it's quite a large, well, it could be an inch on the screen when you're looking sort of 20 miles. It's quite a, you obviously see this sort of stuff, it is quite a lump on the screen. You know, that could be, that's a huge amount of space.
Yeah, massive.
So I probably might ask, well, I'm on the next.
Oh, are you? Oh.
Yeah.
Well,
It's
okay.
solar balloons.
All right. I'll remember you asked me difficult questions. I'm going to be thinking now. Things are really hard.
Yeah.
Things are really hard. I'm really joking,
we did this cubic looking reflector. I didn't know that you can even do a sphere before. And we have done this, but it was only paper and not so perfectly aligned. So I didn't ask traffic control yet. Anyway. So they can provide me some image data maybe.
Yep. So in terms of getting permission to fly the reflector, I didn't ask the question of Dave Miller, but I've got colleagues working in this area as well, and their advice to me was, when you're putting in a request for permission and stuff, just say it will have a reflector fitted, more likely to be seen by the radar. That's all it's
Well, they just required us, well, put a reflector in the 05.
Fine.
Yeah. They didn't.
Everybody's going to walk away with it.
I recognise you talk about
I like motorbikes, but I do have a curiosity. Biggest problem is the interspersed for some reason.
You're back on?
Yeah, we're live.
As well, when? Any idea?
No one would have known. There were rubbish. No, I'd like 80 up.
Did you give me the presentation?
Yeah.
I might not put it in. That was
Oh, okay. Stan? Yeah. This one which ends in 4?
What?
Rob? Okay.
That shows the approach.
Okay, so we got some sweat on. I don't know how to pronounce your second name.
Yeah, great. So, okay, thank you very much. This has been our Gemini free flight, which has been done by Ersine. It's a group of artists in Berlin which came to me about 2 years ago. It's a crazy group of artists in a good manner. And they've asked me if I can help them with tracking because they can build balloons, and I told them, well, I can build trackers, but no balloons. So this has been our last flight with our 60 cubic meter solar balloon. It has been actually 2, which we've launched. And yeah, as I told, there are some artists out there which asked me for some help, and they've created an organization which is called Ersine, which stands for free for non-carbonate flights, which are only flying with air, which is hotter inside, so we can actually fly. So we've built these balloons, which are pretty large, and this one is one of the balloons which we have flown on the 27th of August. This one is particularly made of mylar, and plastic. You have to be so big because otherwise you can't lift it. And 8 meters is a particular size you can really fly. The other reason why we have built these balloons so big is because of the new rules. We are only allowed to fly 4 kilogram balloons with payload and no further. As you can see, the surface area is really large, and that's also the reason why we don't need any parachute, because it's so large that when the sun is gone, we won't fall any further than 2 meters a second. So in the beginning, it's floating almost 1 or descending in 1 meters per second, and then it starts to increase maybe 2, 2.5. So not really fast. So our first balloon we have built was made of polyethylene, which is simply plastic, and we have found out that it's really thin and the wind speed has to be very low, let's say maybe 10 kilometers per hour at maximum, so it won't rip apart. So we had been in Braunschweig in the middle of Germany, and we had this huge balloon filled up with air, and we were ready to launch, and we had very strong gas, and it ripped apart in thousands of pieces, unfortunately, so we couldn't launch. And the other launches were rejected because of rain. We had many issues with the air traffic regulations because they said, launch your balloon at this point of time. And there was always a problem because at these days it was always raining and we couldn't foresee the weather because we have to request the flight at least 2 or 3 weeks before. But this time we asked for 4 flights, for 4 free flights on 2 dates. And they've sent us a permission which says you may launch 4 balloons between August the 27th and September the 5th. So this was really fortunate because if the weather wouldn't have been so good on the 27th, we have launched on the 28th or 29th, whatever. So we have used polyethylene in first place, but then we found out that we can also use different materials. So this time we also flew coated ripstop, which is really strong. It's also the same material of which parachutes are made of, and it doesn't rip apart very easily. Even at landing, it doesn't rip apart, which happens for the polyethylene balloon. And this, for example, is Dyneema. It's also, unfortunately, really expensive, but also doesn't rip apart very easily. And it's even lighter, so these are the materials of which we are building our balloons. So our 2 balloons had almost the same size, about 8.5 meters of size. We always used to build the tetrahedron because it doesn't produce much waste. If you do a sphere, you have to cut pieces like this, and you have a big amount of waste. So tetrahedrons are really good for us for this stage. So these balloons flew at about, well, it also depends on the payload, but these balloons float on 15 to 16 kilometers and yeah, are driven just by the wind and by the sun. So what are the considerable sizes? So this time we flew 8 meters, but I've made some calculations. Maybe for a 10 meter diameter of a tetrahedron, we can get a lift of 8.2 kilograms. We always calculate, well, the plastic may take 20 grams per square meter. There are no cables included, and we may get a lift of 60 to 70 gram per cubic meter at ground level. So this is a calculation which we have used to calculate if the payload would be lifted by the balloon itself. But as you can see, a sphere is even better. With a diameter of 6 meters, we can get almost the same lift. This calculation over there, the green one, is incorrect, but I can't change it anymore because I've got the PDF right here. But the big point is that you get minus 34% less rate, which is even better. So I thought about what is the limit we can build. And it turns out that's roughly at 2 to 2.5 meters of diameter. So we can still get a bit lift, which is almost 600 gram, and we might have a surface of 400 gram. So the balloon won't be that heavy, but the volume, the lift is still good enough for us. Yeah, so for launching we moved a bit outside of the city because we didn't want to have any more restrictions by the air traffic control. There's an area in the middle of Berlin which we are not allowed to enter. It's a restricted area which has been created almost 10 years ago, or more than 10 years ago, while an aircraft was crashing in front of the Reichstag, which is the governmental building in Berlin. So, and because of this reason, they've built the restricted area, unfortunately. So we moved away a bit out of Berlin, so they wouldn't tell us if the wind is blowing between this and this direction, you may not launch. So this is again big. It would be also good if we are not so close to the orange one. It's a closer air traffic control of Berlin, where the aircraft connects to the tower for the final approach. So we have a big surface below the balloon to increase the albedo of the balloons. So we will have more lift at the launch, and also to protect the surface of the balloon from the rough ground. So we had two payloads on each balloon, which has been connected by a 30 meters wire between, and was, compared to our actual balloon launches, quite expensive one. Maybe not to the rocket one or to the other balloons one. We had one GoPro looking up and one GoPro looking down, and one Pico 7, which is one of my small boards which can do SSDV. We'll give it this way, maybe. And then we had a spot tracker for backup, which unfortunately didn't work as well. It has only a couple of LEDs, and if nobody knows how to interpret the LED blinking scheme, it does only transmit at the first time and then doesn't transmit anymore. So no tracking with the spot tracker, unfortunately. And then our second tracker, we had Bionics, this one, which was transmitting APRS data and with 5 watts. And we had another GoPro at the side looking to the side. So the idea was we've connected both payloads to each other, so we may not provide 2 rescue teams. Just one rescue team which is concentrating just on one balloon couple. And the other reason was that we wanted the GoPros to film the other balloon. But it unfortunately didn't work that well because one balloon was had more lift and was lifting the other balloon, so we were almost all the time on each other. So this has been the time when we filled the balloon with air. We have ripped them apart a bit, and then we could close them again together with part of the balloon, which I don't know remember the vocabulary anymore, unfortunately. So you have two pieces which you can stick together and they will hold together.
Velcro.
Velcro, right. And so we close them, and then it's all about rating. It takes roughly 20 to 30 minutes, so the balloons will have enough lift to lift themselves up. And this is what it looks like. They are almost like big sails, so you need at least one person dedicated to hold the balloon, even at 10 kilometers per hour. And then we came to a final point that switching on all the trackers and GoPros, and the lift initially is really low because the field is also, the air above the field is also really hot already. So the balloons will only have a lift of maybe 10 centimeters per second. So you will need a really long runway. And you also need a couple of persons who are holding the payloads. We had two people who were holding the payload, and some of them were holding the wire between, and some of the guys watch that the balloons don't touch the ground anymore. So it was a really critical point because some seconds before the balloons haven't been really close to the trees, maybe with a distance of 1 to 2 meters. And behind there were also the windmills, so it has been a tough time. And then it flew higher and higher, and yeah, like almost all other balloons, we got some nice images. We had one rescue team, and this is a point which Dave had not on his list. We needed a camping van, especially because the balloon almost flew 650 kilometers through Poland, and some of the other people were watching it from home. So we had Thomas, KT5TK, who was chasing the balloon with another guy. And these are some images from 16 kilometers of altitude. So you can see they are not completely airtight. They can use air a bit, which is not bad, because we want to get them down anyway in the end of the day. Otherwise, you would open the balloon a bit on the bottom part, so they can, like a greenhouse effect, they can breathe air again. So another idea is that if you want to keep them longer in the air, you make them a bit bigger, so they act more like a really big parachute. And if you are happy, they won't descend all the way to the ground through the night and pick up some sun in the morning and lift again to a higher level.
What was the descent rate on it?
You can see this very easily right here. It started already to descend, here, but at a really low level, maybe half a meter per second. But in the end, it really increased to almost 2 meters a second. So I was a bit scared it will end up maybe in the sea or in Russia or in Belarus, because this has been a point where we couldn't go, unfortunately.
I wouldn't try to recover it from Belarus.
Why?
Try. Some of a Polish balloon landed 600 meters above the behind the border. They recovered it for about 6 months with our ministry involved and so on. I want no one has some courage to cross the border and take the balloon.
Because it's their property.
Because it's Belarus.
What about farmers, yeah?
No, no, soldiers with guns.
So, unfortunately, we already lost the last signal at around 13 kilometers when it was fortunately already descending and couldn't get any signal anymore. So, what has happened? We found out that later that because of the high power of the bionics tracker, we couldn't receive it anymore because all 8 batteries went flat. But fortunately, our beacon tracker was still working with maybe 1 milliwatt. It has some power issues, unfortunately, and this has been the reason why Thomas was searching it by a direction finding, and they finally found it. For one balloon was tangled up in the tree, and the other balloon was on the other side of the street in the grass field. So the first time they drove along, they didn't see it and drove right over the balloon, or actually the cable between the balloons. And they found it, by the way, thanks to the habitat predictor inventors. They put the data into the habitat predictor and predicted the descent, and it was just 500 meters of the prediction. So we may maybe launch another balloon in 2 or 3 weeks maybe, and yeah, anybody who wants to come is invited to Berlin if he wants to. So, thank you very much.
Richard's up next.
So, any questions? This is some footage of the balloon, which is with no sound, so yeah.
Rather than having the radar reflector, have you thought of having a metallic coating like the early echo balloons in 1960 or 61?
No.
There, the aluminium thing was a few microns thick. It would save having a radar reflector.
Not at the moment. Not at the moment. We just put the box like reflectors on the balloon, you know, which look like a cross in the middle. But I don't know if they've ever worked. So maybe I will ask the.
Well, they worked in the 60s. They were a bit bigger, of course.
But I know thought about using maybe a Quadratex balloon from the last presentation. That's a good be an option.
That was close to the tree, huh?
Yeah, really. There was another GoPro video which, when one balloon pulled the other a bit up, the one GoPro was looking sideways, and there you could figure out that it was only 1 or 2 meters apart from the trees.
That's beautiful. Nice day. Very fun.
So, any other questions?
What was the maximum altitude?
The maximum altitude was 16,000. It's in the video. 16,200
kilometers. Yeah.
So I think if the payload has been a bit lighter, we would have flown even higher. So this one was maybe half a kilogram each.
Are you not allowed to pump warm air?
Again?
Are you not allowed to pump warm air?
Warm areas, well, I didn't have thought about if this could be a point. We just we just ask a farmer if he can launch there. This has been another point. The air traffic control, or actually the officials wanted to have wanted that the farmer knows that we are launching from this field.
They won't violate the artistic purity of the project.
So,
will the GoPros recording continually?
no, this was just, well, the batteries has been one problem, and the other point was that 64 gigabytes is not enough for a 12-hour flight.
It's supposed to be able to script GoPro cameras, but it's always been a bit unreliable when I've tried it. It's supposed to be able to script.
Well, we also figured out that the GoPros occasionally stop recording, even if they have enough power and enough memory.
Yeah.
They get too hot.
Huh?
They get too hot.
Maybe, yes.
Yeah,
they are getting hot, quite warmer than your hand is.
They will stop. They will stop if they get too hot.
It's interesting that the send rate sort of didn't really level off as you got higher.
Well, I can maybe show later.
This is probably due to the higher solar radiation as you get higher.
The ascent rate was almost stable, except on the ground. It was increasing when it was flying over the trees and the forest. So I can maybe later show you a vertical profile of it.
What's the theoretical limit? Do we know how high these things will go on solar power?
Huh?
Does anyone know how high these things will go on solar power? Are we still better off with
I've heard about that some other guys already launched a balloon which went up to 40 kilometers.
On solar?
On solar, yeah.
40? That's going to 40.
I don't know.
Well, it's just theory.
It's just a hot air balloon, isn't it, really?
But yeah, it's like a bit not differential.
There's not an awful lot of lift from hot air in comparison with air. We have to sort of move along because we've only got one more presentation to do now. And we're going to overrun anyway, but I don't want to overrun by too much. So, thank you very much. Richard.
Yeah.
Right.
So where did my tracker go?
Hey, good afternoon. My name is Richard Meadows, and I'm supposed to IRC as well, so that's my IRC nickname up there. I'm part of a university group called Bristol SEDS. So we do things like model rockets and going to air shows and various aerospace things. One of the things I've been leading over the last couple of years is ballooning. So we did our very first balloon launch just over 2 years ago with help from Steve, which was very useful at the time. And since then, we've been building super pressure balloons, which are a bit different to the normal meteorological balloon. And just as I note for this presentation, you can find all the kind of resources and images if you want to see them bigger at that link. So, superpressure balloons. So you need, with superpressure balloon, all the gas is sealed in the envelope. So that's pretty similar to a latex balloon where you seal it off before launch. And if you seal enough gas in that it goes up, eventually it will go up to a point where the gas begins to pressurize as it reaches the volume of the envelope. So that's where the name superpressure comes from. However, in this case, we're talking about envelopes that are intended to be inelastic. So a meteorological weather balloon will stretch and eventually burst. We're trying to design an envelope that won't do that will eventually, might stretch a little, but will eventually maintain its shape. And if it maintains its shape, then it can float. So it goes up to a particular altitude and stays there. And on the right there is an example of a balloon from a US research program, nearly 50 years ago now. And the scale, that's probably sort of 2 or 3 meters diameter. And that type of balloon holds the world record for the longest balloon flight, and sort of generally flies in Earth's atmosphere at about 700 odd days, so a little over 2 years, tracked on HF. So in recent years, amateurs have been doing this too. So on the left is a plot of our very first successful superpressure balloon. So it took us a few attempts. So it went up and stayed up, and that's for about a day, which is our first flight. The longest amateur balloon flight is a flight by Leo, who lots of people here know, and that flight stayed up for 134 days, I think, if I'm correct, and went around the world lots of times. So amateurs clearly can do this, and Dan Bowen, 5 years ago, the very first one of these conferences, gave a talk about this. If you're interested, please go back to that talk. I don't really have time to cover everything he mentioned, so that resource is still useful. What I'm also going to talk about is what these balloons look like when they're flying. So this photo came back from a flight about 2 weeks ago. And that's it floating, with the balloon fully inflated and above the English Channel somewhere. It was a pretty big effort to get this image back. Thanks to Jeff and Ron for actually receiving this, and it was transmitted back over LoRa, which Dave talked about this morning. So yes, pretty impressive image, and that one is hopefully still up there, potentially turning up in the US in the next 2 or 3 days. So watch out for, I think it would be Adam 10 when it turns up. Hey Adam. Okay. How do you calculate the floating altitude? So very simply, it floats when it's the same density as the air. So as you go up, the air gets less dense, and eventually that will equate with the balloon density. So the definition of density is mass over volume. So you add up all your masses, the weight of your balloon itself, the weight of your payload, and the weight of the gas, which isn't very much, but still account for it, divided by the volume that your envelope reaches, and that's your density. Of course, the envelope isn't perfectly elastic, so it's going to stretch somewhat above the volume it was when you built it. So I've defined gamma, capital gamma there, as being the ratio between the size of the balloon is when it's floating against the size it was when it was built, and we'll come back to that later. And at the bottom is a plot of density in the International Standard Atmosphere. So to get a rough idea of what altitude you're going to go to, certainly in sort of mid-latitudes, get your density, look it up on that chart, and altitude. So when the balloon gets to its altitude, it's going to have some pressure inside it. So sort of why does this happen? There are three main components. So you had to put some extra gas in when you launched the balloon to get it off the ground. If your balloon was just neutrally dense, like just not rising or falling, when you launched it, obviously it wouldn't rise, so it wouldn't be much use. So you have to put a bit of extra gas in there in order to get up there. And also is this concept of super temperature. So the gas inside the balloon will have a higher temperature than the gas outside usually, and that generates pressure. And the final one, which I'm not going to talk about so much, is basically vertical winds. So you can get wind that goes upwards, and that will blow the balloon above its kind of equilibrium point. And that was up in a little bit, maybe 10%, something like that, of internal pressure. And you can find out more about it in that paper, which I do really like this paper by Vince Lally. So, lots of references to it. So, how do we go about actually calculating this? So, we can use something called the ideal gas law. So this works for, not in all circumstances, but works really well for the kinds of temperatures and pressures we have in the Earth's atmosphere. So you can say that the product of the pressure and volume is equal to a constant times the temperature. And this constant is NR, so N is how much gas, and then R tells you, is a number, it's 8.3 or so, that tells you how much energy you get from a gas for every Kelvin of temperature and obviously every mole of quantity. And we can write this equation for two things that are going on. So we can write it for the gas itself. So we've got the pressure of the gas, the mass of the gas, temperature of the gas. And we can also write it for the air that's displaced by the balloon. So because we know the volume of the air displaced, because we assume that the volume of the balloon's skin and the payload is 0, which is approximately correct. And so we know the volume, and because it's floating, we know density must equal, and if the mass equals and density, if the density equals and the volume equals, then the mass must also equal. So we can substitute in the mass of the system up there. So if we write that twice, and we can then equate these two things, because we know the volumes are equal, cancel R. And we use our two definitions for superpressure, which is the increased pressure inside versus outside, and the same for temperature. And if we work through a bit of algebra, I've written it up in the GitHub site, if you want to check my working. But essentially you end up with this equation in the middle. So you have two terms there. So you have this term, and this term originates from your free lift. So the actual difference there is literally just how much extra gas you put in. And then the second term is resulting from your superpressure, super temperature. So this super temperature is because the balloon is like a greenhouse, it heats up, and that's your component. Now I've said here that this second component dominates. It's not quite true. I think on some of our flights it's been maybe sort of 40% from this and 60% from that. However, this is constant, and then this may change. This is the thing that comes and bites you. So we actually want to minimise this.
I think it depends on whether you're using an aluminized envelope or not. I remember Leo on his early flights was using an aluminized envelope, and it tended to pick up damage and cracks forming in the aluminium, and then it sort of acted like an ideal black body, which caused it to get very hot.
Yes,
you got runaway superheating.
So actually,
transparent envelope, there's less superheating, hardly any superheating.
So yes, actually finding a value for this super temperature is quite tricky, because you need to consider the radiation environments, as in infrared radiation coming in. You've got to do sort of a budget for radiation coming in, the budget for radiation getting out. So that's actually quite hard to do. However, in this paper, there's a handy table. So the values in the right-hand column are what we're interested in. So this is kind of enough to get a guesstimate at this. So for typical amateur flights around 12 kilometers, maybe you're looking at 16 degrees worth of super temperature at most during the day. Actually, there's one small thing. At night, you can get a negative super temperature, i.e. the gas inside is colder than outside. And if that happens, you'll actually need the positiveness of this first term, your free lift, actually to keep the balloon up there, and mean that the first term still needs to be bigger than the second term. However, actually where amateur temperatures are flying at the moment, between sort of 10 and 15 kilometers. That's fairly unusual. Lally's paper goes into, again, a bit more detail on that. So actually going back to this photo here, you can see that the balloon itself actually isn't spherical. That's not a sphere. While the sort of more professional balloon is. So what's the difference? So the difference is here. This balloon has been made as a two-dimensional shape and then inflated. So it's the same with the latex balloons. They're made as two-dimensional. They come from a nice little package of steel. They come as a two-dimensional thing and you inflate them. But when you inflate them, it's not a sphere. So actually, it's this thing called a mylar balloon. So mylar balloon shape. So it's called this because mathematicians found this shape in the wild in the form of mylar party balloons, and therefore called it a mylar balloon. It doesn't necessarily have to be made of mylar, but anyway. So when you take these the two-dimensional shape and you inflate it, actually it takes that shape as a cross-section. And we can write, using some algebra, and we can write the equation for the length of that curve. And the length of that curve, sort of there, must equal the radius of the 2D shape. And so that constrains the shape. And this shape is well defined, so we can calculate the volume, we can calculate this cross-sectional area. Mathematicians have handily derived all these equations. And that's pretty nice. However, when you get this shape, you find that actually the surface area of the inflated 3D shape is less than the surface area of the two-dimensional shape. So obviously when you inflate it, it doesn't change surface area really. So what we get is this effect called crimping, where in some areas of the balloon the surface bunches up and gives us the three-dimensional shape with supposedly less surface area. And that actually means that only a small area in the center of the face is stressed. So the white area there is where the stress is going on. So this isn't good news. It seems like the shape isn't actually much better than a tetrune, for instance. So in the tetrune you have corners, and the corners are where stress builds up. And here we have just the same in the center of the face, how stress builds up. It's really nice for making your seal along here, because it means there's not much stress there on your seal. But this seems like a problem.
One point to consider is that low temperatures, around about minus 55 C or minus 60 or 65 that you're going to experience at float altitude, the mylar or more likely the nylon film that we're using becomes quite brittle. It's well below its
the glass transition.
Yeah, glass transition point.
So basically the size
of the area is likely to start cracking even if there isn't much stress on the crimped area.
Yes.
There's a risk of cracking starting in that area and not just the stress around the faces.
So actually the size of this area is defined by the elasticity of the material, and as Lawrence says, at cold temperatures like we get when the balloon goes up there, this area is likely really small, so this is pretty bad. So we have, however, a Treco class leaves pre-stretching. So I'm not quite sure who to attribute this technique to. Lally certainly kind of knew about it, but didn't really know that much. Obviously, kind of Leo used this. So
it was the key to Leo's long duration flights. Before he was doing pre-stretching, he wasn't having much success, and then it just amazing things to achieve once you try pre-stretching.
Yeah. So Lally talks about the top points. That's quite valid. The second thing is that it increases the volume of our envelope with no extra mass. So that gives us higher float and lower super temperature, because if you notice, obviously our density equation, volume is on the bottom, increased volume, get the density go higher. And the same with our equation at the bottom there, volume's on the bottom, so increased volume, everything gets better. But the third point is that it redistributes this stress. So when you're inflating it very slowly at room temperature, You'll get the stress in the centre, and then that area will strain, it will increase in size, and then the stress will move further out. And eventually, if you do it for long enough, you'll get actually pretty much the whole face is actually being evenly stressed. And that means the maximum stress, much less, and it's less likely to burst there. So yeah, pre-stretching is generally good. However, we've not really explored it beyond gamma equals 2, so we've not more than doubled the volume. So beyond that, you may get to changes in the material that causes it to sort of just lose some of its properties and fail. So we're not. So that's, I think.
Sorry, Richard, did you say gamma of 2? Is it a doubling of the volume?
Yeah. So, whoops. Computer's dying on me. It's living all of death. Okay.
You created this in latex, didn't you?
Yes, it is.
That was style.
Yes, it's Beamer. Yeah. Okay. So a bit about constructing the envelope itself. So this is a drawing for our larger envelope. You can find this as a PDF and an image on the GitHub site. It's too small to read. One of the problems is we have a film that's only 60 centimeters wide, yet we need to make a balloon that's much bigger. So we combine strips of the film, which we call panels, and 4 panels go together to make a gore, and then the 2 gores go together, still 2-dimensional, and then after that it can be inflated. And actually just talking about the film itself. So mylar film means PET, polythene tetrafluorate. We're not using that, we're using this composite materials. So we have nylon, which gives strength, and also does stretched in the 2 directions, and the chains kind of slide over each other and then eventually stop, which gives us really good tensile strength. We have the EVOH in the middle, that's a gas barrier, so essentially just keeps the gas in. It's pretty good. And then polythene goes on the inside of the balloon to mean that we can heat seal it easily, because polythene melts at 110 degrees or so that's quite achievable for heat sealer. And so we do all fin seals, just kind of easier. Even though going back to Dan's presentation 5 years ago, actually he talks about using sort of better seals. We've sort of got away without having to do that work. And yes, thanks to this, I suppose, small grant, we got to use the paid for the lab time at the university to actually get this cross section. So we did FTIR to get the outer layers, and we sort of guessed at the inner layers. So hopefully that's roughly correct. What else? Okay, further work. So what you could be doing? I'm trying to think of anything which is interesting. Modelling the super temperature, so modelling the radiation environment is certainly doable. And probably the easiest actually is the third one down with free lift. You can model the balloon like a parachute, just with a different drag coefficient. You get the drag coefficient looking at previous flights. And you can work out what's the minimum free lift you need to get a certain descent rates to outrun the local weather and get clear into the tropopause. And actually measuring the strain on the ground. So we kind of only find out gamma when we launch and we see what altitude it gets to and work backwards. You can actually measure this on the ground using helium. Nice paper there that describes how to do this. And if you're feeling really brave, you can try modelling the relationship between the stress and strain. Because obviously it's going into the beyond the elastic region, it's deforming permanently, and it's non-linear and nasty. I'm not a material scientist, so I don't want to go there. And yeah, I'm flying around the world. So. Cool, I have, actually going back to this last point, I've made a little bit of a start on a calculator. Actually, whilst loading, any questions?
In the pre-stretching, Richard, do you use purely pressure or is there any water heating involved?
No, so it's all just done at room temperature.
Right.
So we use blood pressure monitor. The on one M2 you can go and buy now. That's £25, I think, and that will do. That kind of acts as a pump. It takes a while for the 1.9 metre envelope. I think it's about 24 hours. Obviously, it needs to be kind of hacked to run continuously. Otherwise, it will just stop after a few seconds.
Further to Jeff's question, do you get better results in the summer or the winter?
I don't think we've done enough flights to be able to say that.
I mean, in the pre-stretching.
The pre-stretching, yes, it's hard to tell. I'm trying to think. I don't think we've actually had any bursts doing pre-stretching. We've had them fails with seals and so on. But yeah, it seems to work. Anything above sort of -20. My house is above -20. Anything above that should work fine. Obviously, it might be slower. Any other questions?
What's the camera you used?
Yes, so that was just a Raspberry Pi camera. If you want to know more about that tracker, then
message after all.
Yeah, so that's the tracker we use with the Raspberry Pi Zero, and then tag a camera onto that, and that's what took the image you saw earlier. So that weighs in at about 75 grams. So that's getting fairly heavy for a super pressure payload. But it stayed up for 4 or 5 days and is now out there somewhere, hopefully.
Those the antennas on the bottom?
Yes, so we just did a quarter wave with the ground plane and dropped down 2 verticals, one for 868 and one for 434/2 meters. The calculator should appear. It's wonderful doing it. So yeah, I need some like styling or CSS or something. But essentially, fill in some parameters. Do it for the quadrilatex. You roughly know the density from the material, so you can work out the film thickness if you're wondering how to do that. And let's say sort of 15 grams on a quadrilatex. So this shows you against gamma. So against how much you pre-stretch by what altitude you're going to achieve in a standard atmosphere, which will be a few hundred meters away from probably at these altitudes what it will be.
Matches well with people.
And also it quickly calculates this ratio as I described on this slide. So it's probably.
Will this be able to tell you how much altitude you will lose for a given volume of gas lost from an envelope?
Certainly you could do that. There's lots more features you could add actually.
That would be an interesting question.
Please submit pull requests. There's a link to the GitHub there.
What language is this written in?
It's JavaScript, I think. Oh, it is.
Thank you very much. Right, well, I think that brings the sort of formal part of the day to a close. We're going to move across to Churchill in a minute to try and launch Bloom. Any final points, Bill? Just remember, if you want some food, please take what's ever left out there because that's something that goes to waste. I'll take what I can to the local food banks. Great, thanks very much for coming.
Thanks for organising.
Thank you. Let me give you some.
Try to do a theoretical model of historically around the overall policy
Turn back.
and
we're heading over to... I have no idea how to get over that.
Down the road,
Well, yeah, it's a long way down by...